Hi everyone and welcome back to PrepFusion. I am Anish, and finally, as most of you guys were asking, where is power system? When will power system start at PrepFusion? So today we will be starting with the first marathon of power system. In this we will be covering the basics of power system, then we will discuss three-phase systems and per unit method. Okay, so first marathon will be basics, but trust me, we will build a foundation. I know many students has bit of doubts in this per unit method. They don't understand it properly. So if you just once study the per unit method from me, then you will understand in what depth we have actually gone. Like we have solved every single thing, whatever is the possible cases, right, that they can ask questions from per unit topic. We have tried to solve that. Okay, so this is the first marathon. More marathons will come. So currently the plan is that complete PSA 2, right? PSA 2 is consists of this first marathon, that is per unit method. Then we have fault analysis, that is symmetrical fault, unsymmetrical fault. Then we have power system stability, right? So it's roughly around 40 hours of content. So my plan is all this will come on YouTube, but this has some condition. I will discuss about the condition. It's not like it will just come without any condition. There are some conditions, then only it will come. Okay, now what are the prerequisites? The prerequisites, it's that my expectation is you have studied machines, right? At least synchronous machines. So for studying per unit method till the first marathon, there is no prerequisite. For studying the first marathon, there is no prerequisites except network, and my expectation is, of course, you have studied networks, right, from us. Complete AC portion as well. You have completed the AC portion from us. Okay, everything. Also there is an additional prerequisite, that is synchronous machines. Okay, so but for watching this first marathon, you don't need to complete this prerequisites, only network is enough. Okay, but when the second marathon will come, my expectation is you have completed synchronous machines till that time. Okay, now like why am I saying that we have covered in depth? I'm just showing you one example of my notes, right, of per unit system. Here we have drawn the per unit equivalent of a 3-winding transformer. Everywhere else you will see, most of the other institutes, they will only show you or derive the per unit equivalent of a 2-winding transformer, but we have actually gone a level above. We have shown it for 3-winding transformer. My expectation is one day in GATE these kind of questions will be asked and you guys will be able to solve it. So we have understood everything intuitively. If there are two voltage sources, if there is some inductive link, what will be the power flow, all these things we have understood intuitively. So we will see that once, like you will see once you will go through the lectures. Just one thing, that this three-phase systems, right, if you have already covered my network theory, there also have covered three-phase systems. So that lecture is just copied here. Few extra additional questions I have solved that is not present in the other lecture. So timestamps will be provided, right? If you have already watched the three-phase lecture, you don't need to watch the lecture, but go to the questions portion and solve the questions. Okay, because that is more relevant to power system. That's why I had to solve them in power system. I cannot solve them in the network theory. Okay, so that is one important notification. Now why you should trust me? So we have already covered the complete AC analysis, and obviously network theory DC has been taken by Himanshu. So we can go, and on those videos, right, you can go through the comments. So you will see like how much students have loved the AC portion. Okay, and every single thing we have covered in detail. If you have already studied AC analysis from me, then you know that we cover every single thing in detail. Every corner cases we take, right, conceptually there is clarity on all the concepts. So that's the motto of PrepFusion. We never compromise on quality. Quality will be always be at the highest level. Whatever content we bring, whatever subject we bring, quality will be at the highest level. So from my end, I have given you the best possible quality that you will ever see. Now what are the conditions for marathon 2 and for the next portion, like fault analysis? Then we have symmetrical, unsymmetrical, then we have power system stability. My conditions are very simple. If I am providing this much amount of content, if I am doing this much amount of hard work, then I am expecting something from you. I am expecting a bit of interaction from your side. So these are the three metrics with which I can measure the interaction. First one is you have to like the video. If you are enjoying the concepts, please make sure to like the video. Make sure to share it so that we can reach 1000 views. So my expectation is before Sunday, my target will be to reach 1000 views. And comment on the video, comment on this marathon, whichever portion you enjoyed, whichever portion you learned something new from that, you can comment that part that I learned something new, I learned at this point, I did not knew this, right? So interact on the video, then only the second marathon will come. If there is not enough interaction, I will not bring the second marathon. Okay, so because I am doing this much amount of effort, and once you go through the notes, so currently for the first few days, right, for the first few days, the power system course will be in trial. Like complete content is not there in, I will provide the link to the website, right? Complete content will not be there, but for the first few days the power system course will be in trial, so you can go and have a check on the notes. You can judge by yourself, you can compare the notes anywhere else, right? You will see what kind of level we are teaching. Okay, the quality, once you will go through the notes, you will understand. Already people have loved the AC part, you will love this one as well. Okay, so these are a few prerequisites. So machine also is covered by me completely for free, so you can cover the machines playlist is completely there on YouTube, so you can cover the machines playlist. Then after you can watch the marathon 2. So marathon 1 there is no prerequisite except synchronous. For marathon 2 there is a prerequisite for synchronous, so that's why I'm expecting that you watch the marathon 1, you watch the like synchronous, and after that you will watch the marathon 2. Okay, so these were my demands. So yeah, that's it. Let's start with the lecture 1. So let's start with our second part of power system analysis, that is PSA 2. So before starting, of course, we have all not discussed what all things are covered in PSA. So because we will start our power system analysis with PSA 2. Everywhere else you will see everyone starts with PSA 1, but I want to emphasize on PSA 2 because it is the highest weightage portion of the power system analysis and the most conceptual portion and the most difficult portion where the students are stuck. Okay, so I want to clear the doubts at the starting itself, then we will move on to PSA 1 and then to PSA 3. So basically our power system analysis is divided into 3 parts: PSA 1, PSA 2, PSA 3. So PSA 1 is the part where we discuss about transmission and distribution. So power, right, needs to be transmitted from generating stations to the loads, right, to your houses. So there needs to be a system. We need to model the system. Modeling of the transmission lines, short, long, medium transmission lines, numericals on that, inductance, capacitance, lump parameters, all those things comes under PSA 1. I will discuss the topics one by one. I am discussing the weightage. So these are rough numbers. Okay, these are all rough numbers, not exact. Please don't take these numbers by exact. Okay, these are rough numbers. So generally the trend is PSA 1 is asked for between 4 to 5 marks. Okay, around you can expect 3 questions, 3 to 4 questions. Okay, PSA 2 has the highest weightage, 4 to 5 questions you can expect. Fault and stability, it includes the fault and stability. Most of the numericals are framed from here, and the weightage also is on the higher side. Recently it has gone down a bit, but still it is the most important one. PSA 2 is the most important one, and we will cover this comprehensively, don't worry a thing. Okay, then PSA 3 is the last portion, which recently they have implemented, where we discuss about power system protection. So in this, circuit breakers and relays are integrated. What shall be the rating of the circuit breaker? How relays function? There are different types of relays. Okay, what is the working principle of relays, right? What kind of relay we should connect for proper protection of our system? All those things will be discussed in the third portion of PSA. Okay, so I will briefly talk about the topics, what is included in PSA 1, PSA 2, PSA 3, so that you get an idea what we will cover, right? And generally PSA 1 is more lengthy compared to PSA 2, but the weightage is higher on PSA 2. So that's why we are focusing on PSA 2 first, then we will move on to PSA 1, because it is a longer subject, but generally the trend is the weightage is on the lower side. Okay, but of course both are important, and don't worry, we will cover everything comprehensively, but we will first of all cover PSA 2 because that's where most of the doubts come. Okay, so in PSA 1 already discussed, we will discuss about the transmission line parameters. So from the sending end to the receiving end, I'm transmitting through a cable, through a wire. It's a long wire, it's not a simple small wire, right? It's not like only this much. The transmission line is very big. It supplies from like one end from Jammu to Kanyakumari, right? My spelling will be wrong. So it's a very long distance. So also we have to model the lines. How can I model the lines? It's a very long distance, right? So the modeling of the lines will be done according to transmission line parameters. We'll see how the transmission line parameters varies with distance. So there is resistance, inductance, capacitance, and of course conductance is the leakage between the conductors. So if I have one conductor here, another conductor here, there will be some leakage current flowing from one of the conductor to the other, because the voltage is very high. That's why there can be like due to voltage, air is a insulating material, but it has also its limit, right? So some leakage current can flow from one conductor to other conductor. Okay, that is possibility. So these are the parameters. Then we will see performance. How does the performance change? So of course you cannot exactly model the transmission line, but we can do few approximations. So there are many approximations. Like in short transmission line, we assume only it's a series impedance. In medium, it's a pi equivalent or T equivalent model. Pi is something like this, right? This is pi, or T is something like this, star. And in long line, it is hyperbolic equation. We will discuss about this one as well. Okay, so we will discuss what is the voltage regulation, because from here to here there will be some voltage drop. What is the efficiency? Because if there are some resistances in the wire, there will be some power loss in the wires, sending and receiving and power and voltage, all those things we will discuss. Then we have voltage control, because sometimes we want to control the voltage. Remember, that's why I always say that whatever we are covering is everything in sequence. So we have covered synchronous machines and we derived a formula there, reactive power. And I told you at that point of time that my reactive power is basically equals to Vt into EF cos delta minus V. So it is roughly means my Q, output of the generator, is actually depends on the delta, basically the sending end voltage and the receiving end voltage, right? So if I want to reduce my delta, so I have to reduce my reactive power, right? I have to reduce my reactive power. That means some other device should send the additional reactive power that the load is demanding. My synchronous motor should not send the reactive power. Synchronous generator, so not a motor. Synchronous generator should not send the reactive power. Other devices should send the reactive power. Ultimately, we will discuss this one. We will discuss the main key point is your reactive power is dependent on the voltage difference. So I can control the receiving end voltage by changing the reactive power. That is what we will use in voltage control. Of course, we want to improve the power factor. Why we want to improve the power factor? You know one thing that my power is constant and power is Vi cos phi for a single phase load. So if my power factor is improved, highest, right, then my current required will be lowest. Then the I square R loss will go down. So I want to improve my power factor as much as possible so that the current that I need to transmit through the transmission line should be lowest as much as possible to reduce the copper losses. So that's why we have to understand few power factor correction or improvement techniques. Then we will discuss about traveling waves. If I have transmission line here and suddenly a surge comes, right? Surge like lightning. If lightning comes, you know, it will dissipate on the left hand side, it will dissipate on the right hand side suddenly. It will be just like a wave. Just like a wave. If you remember in rotating magnetic fields, we are discussing about standing wave. Like the wave itself is rotating in nature, right? So here also we'll get some waves if some lightning suddenly falls on the conductors. Okay, so those are known as traveling waves. We will discuss about this as well. Surge impedance, like our transmission line will provide a different kind of impedance that is known as surge impedance when a surge arrives on the conductors. Okay, then distribution systems, basically once the power is received at a distribution station, then it reaches your homes. So from that distribution station to your home, there needs to be some kind of different systems, right? Like we have this radial ring main interconnected. So there are different types of connections which can be utilized to provide supply to the consumers. Which one is the efficient one? That depends on what kind of load we are connecting. So this also we'll discuss in the PSA 1. And then we have cables and insulators, theoretical topics, and economic load dispatch. So to minimize the generation cost, which generator should be turned on, which generator should be turned off, how much should generator G1 provide power, how much should the generator G2 provide power to get the most economic output. That is, the cost of generating the overall system, generating the power is lowest if I share my load. So basically calculate the most economic load sharing. This is also important part because this was recently added, I think 4 years back this topic was added. So one question, 1 marks question generally comes from this topic. Okay, now the second portion which we will be covering in this part, PSA2, we have single phase, 3-phase system. Single phase system you already know, and 3-phase systems also you know, okay, which have been covered in network theory. So what I will do, I will again add that video here in the lecture 1, and then I will solve few additional problems. Okay, I will discuss about that. 3-phase systems you have to study. One thing is per unit systems. So briefly I have discussed about per unit in machines prerequisites, but here we will go more deeper into it because whatever we see in power system, right, everything is in power per unit. Why is it in power per unit? We will discuss about that. Why is per unit is so important. Then symmetrical faults means faults which are balanced in nature, where the current flows is balanced. Okay, basically if let's say you have three conductors, three phase, right, all the three conductors are suddenly shorted to ground. What will happen? Here the load was connected, all of them are suddenly shorted to ground, so huge current will flow and that current will be balanced, and those kind of faults are known as symmetrical faults. If instead of three conductors only two conductors are shorted and then grounded, then what will happen? That kind of fault is known as unsymmetrical. Why is it called unsymmetrical? Because here the current won't be balanced, because in one phase current is flowing normally, in the other phases current is flowing different, right, magnitudes are different, so the system becomes imbalanced, it is not balanced anymore, so the fault is known as unsymmetrical faults. For that we have to study symmetrical components. So here what kind of analysis we'll do? Again we'll divide this into three portions: positive sequence, zero sequence, negative sequence, and then we will do the analysis. Don't worry if you don't know all this, we will discuss this in brief, in details as we move along. Okay, then we have power system stability. So whenever there is a disturbance in the system, we have discussed in synchronous machines that if there is a disturbance, suddenly the load changes, my delta angle will change, there will be hunting. Okay, so how to make my system stable, what kind of stability will be there, we'll discuss. Mainly there are three kinds of stability: steady state stability, transient stability, and dynamic stability. So all these three stability we will discuss. Then at the end we will discuss about load flow. So load flow basically will determine if I have a very big power system, right, there is so many, like, don't get scared, we will solve all this. So these many generating stations are here, there is some load connected. How can I calculate the voltage at this node? For that we have a analysis known as load flow or power flow analysis, in which we will be using matrices. To solve the voltage and currents and power at each nodes. Okay, so this was the PSA 2, and PSA 3, as I discussed, is circuit breakers and relays. So relays are the devices that will send the tripping signal to the circuit breaker when some fault has occurred. So basically it senses the current, and depending on if the current goes very high, it will send a signal to the circuit breaker, please open the circuit. Basically, please open the circuit, fault has occurred, please disconnect the generators. Okay, so relay is the sensing device, it is the sender, basically it is a messenger. Relay is a messenger, like a postmaster, right? It is a messenger, it will message to the circuit breaker, please disconnect the alternators or generators from the transmission line because a fault has been occurred. Okay, and circuit breakers, as the name suggests, it will break the circuit, its task is to break the circuit. Okay, so this will be the PSA 3 that we will be learning at the end of PSA 1. Okay, so I will start with lecture 1, that is three phase AC systems. Now the important point is, I have already covered three phase AC systems very comprehensively in the network theory, in the last video, right? If you see in the network theory last video, we have already covered it. So here what I will do, I will again insert that video here. Okay, so that video will play, I will show you the timestamp. When the video will end, you go into that timestamp, if you have already watched that video, no need to watch that video, that's just the previous video. Okay, network theory, if you have, you can skip into this timestamp, go into the timestamp. I will solve few additional questions which are relevant to power systems. There I have not solved it because that I was teaching EC and IN guys as well, so that was not important for them. But now we are studying power systems, so I have picked a few additional questions which I will solve. So if you have already watched this three phase AC systems from network theory or from electrical machines prerequisites, you can directly skip and move forward to this particular timestamp and directly watch the questions, solution questions. Okay, you can try out the questions by yourself as well. If you have not watched it, please go through the video. Okay, so I will start with the three phase systems. So let's discuss about three phase system. So mostly whatever we have been discussing till now are single phase system. Okay, so in a single phase system, what does mean this phase, right? Phase means that all the supplies will have the same phase. Okay, supplies will have same phase. So if you observe in the left hand side diagram, this diagram, that here I have a supply which is VP angle phi, and here also I have two supplies, but both of them are having same phase, right? So it is a single phase supply only because the neutral is common between these two supplies, and both of the generators have the same phase. But if I see in the right hand side diagram, I observe something different, that this voltage source has a amplitude of Vp, that is fine, but phase angle is 0 degrees, but here the phase angle is minus 90. So they have phase difference between them. So whenever there is a phase difference, that means it is a polyphase system. Poly means multi-phase system. So in this case, it is a two-phase, three-wire system because I have two phases and I have three wires. Here I have single phase, three wires. Here I have single phase, two wires. Okay. So that is how we classify our polyphase systems. Now let's come to why three phase. Okay, why we have used three phase? Everywhere you go, like whatever supplies you are getting from your home, okay, if you go around your home, right, the nearby distribution transformers, all those things, three phase supply is coming. Why three phase? So three phase system dominates the power distribution and generation for mainly three reasons. Global standards, almost all electricity worldwide is generated and distributed in three phase. So anywhere in the world, maximum 99% of the cases, the electricity that is generated and distributed are in the form of three phase. Okay, everywhere it is distributed in three phase, so it helps. It is a global standard. That is the first thing. Second thing is constant power delivery. Unlike single phase or two phase systems, three phase power does not pulsate, ensuring stable power transmission. Okay, so if you remember in the complex power chapter, we had derived the power expression. If the voltage and current are both sinusoidal, how will the power expression be? Okay, so in case of single phase, right, the power, if you remember, was pulsating. Sometimes it was negative, sometimes it was positive. Okay, but in three phase it will not be pulsating. Okay, so if in three phase it is not pulsating, that means the harmonics will be lower, and that means it will reduce the vibrations in machines. Okay, that is better and greater efficiency. For same power output, a three-phase system requires less wiring than an equivalent single-phase system, making it more economical. So if you see, this is a three-phase supply. Okay, how many wires I required for a three-phase supply? 4 wires. And here, to supply the same power, right, I will need three of this copy, right, 3 copies of this. So it will be what? How many wires I will require? 6 wires. Here I only required 4 wires, and here I required 6 wires to let's assume to transmit 10 kilowatt of power. Here I require so much lesser amount of wires, right? So of course, if I want to transfer or deliver power, right, from my generating station to your home or somewhere, I have to connect the wires. Okay, and those wires actually cost money. So of course, if we are able to save the costing in wiring, that will be better. And how, you might have a question, sir, how is it possible that with 4 wires I'm able to transmit the same power? Because all of them have a same common neutral. And if the neutral is balanced, right, then the neutral current is actually 0. If all the 3 phases are balanced, then the neutral current is actually 0. I'll discuss about that later on. Okay, and easy guys, right, easy guys, don't have to take too much stress on this particular topic. Just listen to me whatever I'm saying and just do the numericals, whatever we are doing, that's it. Okay, no need to study it again, or just study once, that's it, and once in a while revise it. Okay, no need to stress. I'm talking about EC aspirants. Okay, so yeah, we will discuss more about this. So now you might have a question, sir, why 3 phase, then why not 6 phase, why not 12 phase? So as we increase our complexity, right, sorry, as we increase our phase, the complexity also increases. Okay, of course there is a what do you say, there is a drawback to everything, right? So it's not like I can increase my phase infinity times. Okay, as more and more phase becomes as I increase my phase more and more, the complexity increases, and to generate, right, 6 phase power or 12 phase power, it will be more difficult. We are easily able to generate 3 phase power because our generators that we built, so we will study this of course in machines only, that is why we will study that we are easily able to generate 3 phase power. Okay, so it is easier for us to deliver the same 3 phase power. Okay, 6 phase generation of 6 phase will be more and more difficult. Okay, I hope you have understood this point. So yeah, this is the machine, and you can ignore this particular thing right now, that how our winding plays, all those things we will learn when we will actually study the machine, electrical machines. Okay, so yeah, so in it, just these are the I just wanted to give you overview how is 3 phase power generated. You can ignore. Okay, now here this is the important portion. So there are mainly 2 kinds of 3 phase supply. Okay, one is the star connected 3 phase source, another one is the delta connected 3 phase load. Okay, there is a bit of difference between star and delta, because you can connect 3 phases in 2 different ways. One is the star connected, another one is the delta connected. In the delta there is no neutral wire, in the star there is a neutral wire. Okay, neutral wire has its advantage. Okay, neutral wire has its advantage, so mostly we use star as well, sometimes we use delta as well, depending on the use case. Okay, and another important point is that if I have three phase, okay, let's say VA, VB, VC, so the three phase will be, the supplies of the three phase will be phase shifted by 120 degrees. If it is a balanced three phase network, then all of them will be phase shifted by 120 degrees. So if I start from 0 for VA, for VB I will start after a lag of 120 degrees, for VC I will start after a lag, another lag of 120 degrees, and like this the three phases, the three phase voltages are phase shifted by 120 degrees. Okay, but their amplitude peak values will be same, just their phase difference will be different, because that is what the definition says. If I have a three phase system, I will have three sources with three different phases. Got it? Okay, so here, right, this I actually taught in my power electronics class. I will just quickly revisit this. So already discussed that three phases I have. So either they will call it VA, VB, BC, okay, or they will call it VR, VY, VB, RYB, either RYB or ABC. Okay, I hope you are comfortable. RYB was the older notation. Like previously we used to color code our wires for three phase supply, red, yellow and blue. Okay, now we have changed, we have gone to ABC. Okay, so considering like this three phase supply, so if I have a red phase or AB, then it will have, its value will be Vm peak into sine omega t. Then the value of the Y with respect to the neutral, I'm talking about neutral, I'm not talking about delta right now, I'm not talking about delta connection, I'm talking about star connection. This is a star connection. Okay, so Vyn will actually lag by 120 degrees of Vr. So if it lags, right, so if this is my reference, Vr is here, then I will lag, my Vy will lag Vr by 120 degrees. So I will move in the clockwise direction by 120 degrees. I will move in the clockwise direction by 120 degrees. Okay, then Vb is here. Okay, Vb is here. So Vb is Vmp sine omega t plus 120. How is it plus 120? Actually, it lags by 120 of Vy. Okay, it lags Vy by 120. So it is minus 240. And I can change my minus 240 to plus 120. How? Just adding 360, because adding and subtracting 360 does not make any changes. If I add and subtract 360, it will not make any changes. Okay, so that is what my VVN is. So these are my phasor representation. Okay, because we will use this, actually we will use this. And if the load is a balanced load, I will discuss about balanced load. If the load is a balanced load and it is a lagging load, then the current IR will lag by some phi angle with respect to VR. The current IY will lag the voltage with respect to, like VY with some angle phi. Current VB will lag the B phase voltage with respect to like by some angle phi. Okay, by some angle phi. Okay, so this is how like everything will work out. This is how everything will work out. Okay, and one more important point is, like, if I have a supply like this, okay, what if, like, there are two terms, one is the phase voltage, another one is the line voltage. Okay, I will discuss about that. So if I just reduce the size, so here if you see that this particular voltage, right, VAN, is actually called as the phase voltage, because with respect to neutral I am measuring for a single phase. So this particular voltage is called the phase voltage. Phase voltage. Okay, and this voltage VAC, right, or VAB, whatever you want to call it. Like, let's say I'm measuring the potential across these 2 points. So these are called the line voltages. Why line voltage? Why line voltage is called? So I'm measuring the voltage across the two lines, right? Not across it on a single phase. This is called as a single phase. I'm not measuring across a single phase. I'm measuring across the line. So this is called the line voltage. So for a star connected network, if we do this, right, if we do this calculation, okay, VRN minus VYN, I have taught this. Okay, I will not derive here, we don't have time for to derive. It will come out. I will directly, like here also I think, I guess I have derived somewhere, right? Yeah, it will directly come out to be equals to, this value will directly come out to be equals to VRY, right? So VRY is what? VRY is VRN or VAN. VAB will be VAN minus VBN. Okay, that is what is written over here. So this directly comes out to be root 3. Like you can solve, it will come out like this value will come, right? I have to this from this value I have to subtract this value. So it will be a formula of sin A sin B. From there, if you remember the formula of sin A sin B, you can simplify, and ultimately your answer will come out to be root 3 VMP sin omega t minus 30. Okay, so it will actually lag by 30 degrees. So that is the like difference that I think I have derived here. Okay, not lag, sorry, this will be plus, right? Sorry, that is what I was thinking. Sorry, not lag, it will lead, right? So like if you just calculate the result, this lead value will come out, okay, plus 30. So where will my VRY or VEB lie? VAB will lie somewhere around here, right? It will lead by 30 degrees. Okay, you can do the calculation. I'm not doing it. Okay, this you have to unfortunately remember. Okay, this you have to remember, because for electrical guys this is very important, and this anyways you have to remember, and this will automatically be remembered by you because you will use this multiple times in different subjects. Okay, so this will be VAB or VRY, anything. VAB and RY both are same. So RYB is same as ABC. Okay, so it will lead by 30 degrees. As it is a balanced system, all other voltages will have a phase difference of 120 degrees. So now my VYB will be lying somewhere here. Okay, VBR will be lying somewhere here, not here, sorry, sorry, we will be lying somewhere here. So I have actually derived it, you can see. Okay, I have already derived it. So my VBR will be lying somewhere here, VYB will be lying somewhere here, RY will be lying somewhere here. So the angle difference between the line voltage and the phase voltage will be 30 degrees. Okay, now there can be like opposite voltages as well. What do you mean by opposite voltages? Let's say we don't want VRY, we want VYR. How will you write VYR? VYR is simply VYN minus VRN. Okay, so I had already calculated VRY. VRY is VRN minus VYN. If I multiply a negative sign, I will get this value. So simply what you do is, we already know VRY, just multiply a negative sign. So if I multiply a negative sign here, this will be minus under root 3 VMP sin omega t plus 30. So this will be root 3 VMP into sin omega t minus 150. Okay, so that is the thing here. That is the main point, main crux that you have to understand. Okay, so like just you have to remember these. What you have to remember, this one. Okay, this, either you make a short note or something, and you have to remember these values as well. Okay, RYB and ABC are interchangeable. Please don't get confused. Remember this one and this one as well. So these slides are very, very important. Okay, and another point is that I was discussing about this, and what is the current. So in case of star connected load, right, in case of star connected load, the line current and the phase current are same, because like whatever current is coming out is the same, right? So if I connect a load here, this will be the load here across the neutral and the phase, and so this is coming out of the phase, and same is going to the line as well. So line current and phase current are same, but in case of delta connected load, the line current and phase current are different. So if I see here, if I let's say this is my voltage source, right? Where is my delta connected load? Here. So here, right, my load is here. Load will be connected across the 2 points. I don't have a neutral here. So line current is, phase current is coming out of this phase, right? Let's say this is I AB. But line current is different. IA, like what will be line current equal to? Line current will be equals to the summation, this phase current will go here, like direction does not matter, it will be the KCL at this node, right? It will be IC will be equals to IAB minus ICA. Okay, so in case of delta, the currents are different. In case of star, the voltages are different. Okay, this also you have to remember. So like this slide is also very important. In case of star, the voltages will be different. Just the what will be the amplitude of the voltage? Amplitude will get multiplied by √3. In case of star, the current amplitude will get multiplied by √3. Okay, for the line current or line voltages will always be higher than the phase current or phase voltage. Okay, or always be higher or equals to. So line current or voltage, so line always have the higher power. That's how you remember that line always will be either greater than or equals to phase. Okay, when will it be equals to? It depends. So in case of star, it will be equals to line current and phase current will be equal in case of star, and in case of delta, the line voltage and phase voltage will be equal. How? So this is my line voltage and I don't have phase voltage is also this, right? So if you see, this is my line voltage and this is my phase voltage, both are same, okay, got it. So that is the important point that you have to remember here. Now this we have discussed, whatever I have discussed, like it is written over here. Another thing is that if generally there are two phase sequence possible, so this whatever phase sequence I had discussed here, it is known as the positive phase sequence. What do I mean by positive phase sequence? Positive phase sequence means that first the phase A will come. Okay, if you see the diagram, if I copy this diagram, first the phase A comes, then the B comes, then the C comes. First A comes, then B comes, then C comes. Okay, so this is the first one, A, B and C. Okay, A, B and C, that's it. Now if maybe I don't want this kind of sequence, I want first C to come. So if I want C to come, so C voltage will be here first, then B voltage will be here. So in those kind of cases, it is known as negative sequence, so ACB. So there are only two possible cases, like first A will come, B will come, C, then again A, B, C, like this. And there is another possibility that then first A will come, then C will come, then B will come, again A, C, B. So you might ask that aren't there any other possibility? No, all the possibilities have been taken care of. If you see, if you use ABC as sequence, it is same as telling me that BCA as sequence. It is same as telling me that CAB as sequence. Got it? All these represent the same thing only. Okay, so if you tell me the phase sequence is ABC, then I can tell you phase sequence is BCA. That is same, right? That is same. How is it same? So you tell me that phase sequence is ABC. So that means A will come first, then B will come first, then C will come. I tell you the phase sequence is BCA. That means B will come, then C will come, then A will come. Okay, both are same. Or we can write here CAB. That is also same. Okay, first C will come, then this is the B waveform, then this is the A waveform. So all the combinations have been taken care, all the positive combinations. So and other three combinations are there like this. So ACB is one of the phase sequence, negative phase sequence. Then I have CBA, then I have BAC. So if we say that ACB is my phase sequence, I will say CBA is also can be called as a phase sequence for the system. So first C will come, then B will come, then A, then B, or BAC is also a correct phase sequence. Okay, so in this case, if it is like this, positive like clockwise, it is known as in clockwise, so it is known as the positive sequence, then the values will be like this. Okay, if it is a ACB sequence, if it is a ACB sequence, so my VAN will not change, of course. I am talking about star load right now. Okay, everything has been discussed for star load, so star source. VAN will be VP angle of 0 and your VCN will be VP angle of minus 120 and your VBN will be VP angle of plus 120. Okay, that will be the difference. So from here I can directly say that what will be my line voltages. Okay, so my line voltages will be VAC will be equals to root 3 VP angle plus 30 degree. So how do I remember? Just remember whatever is coming second, right? Like that you derive. Now the whatever next. So this is how I remember, right? The first one I will remember. Then the next line voltages will be just phase shifted by 120 degrees. So just remember one voltage. I remember VAN, that is in 0 degree reference. So other voltages will be phase shifted by 120 degrees. That's it. That's how I remember. Okay. So V, now what will come? VAC I have taken. So now VCB will come. Just like that. If you see V, not here actually. This is wrong. Why is it? Okay, here only we have written it, right? What is it? Okay. Like okay, one more thing I forgot to say is that VBN minus 240. Okay. What is going on here? No, this will be 0, right? This should be 0. Like we can represent our phase in many ways. This should be 0 degrees. Okay. So like what, like this is my actual ABC sequence. So I can subtract 120 degrees with all the voltages and still it will follow the ABC sequence. Okay, still this is following the ABC sequence because this will be minus 120, this will be minus 240, this will be 0. Okay, so still it will follow the ABC sequence. Okay, all this will follow the ABC sequence. Got it? So yeah, so that is the thing. This occurs when the rotor spins clockwise. So now where was I was discussing this, right? So here also if you see that initially I had derived that for VRY, next it was VYB, the other phase, next it was VBR. So that's how you remember. You make a note and remember how to remember. Okay, so first you write the VRY, the first two phases. Okay, VRY, you write the first two phases, then you continue, you write the second one Y you here, and the whatever is left VYB, then you write, then you copy this one, and then whatever is left you write that, because already you have taken Y, I will write R. Okay, same thing here. So now I will copy this last one, and whatever is left I will write that. And what will be the phase of this? This phase will be very simple. This will be root 3 times VP angle. Now there will be a phase difference of 120. Very simple. Lag phase difference of 120, because here also there was a phase difference of 120. So this will be minus 90. Now again I will write here, I will copy the last one and I will write whatever is left that was not used. So this is VBA. So VBA, again the magnitude will be root 3 BP into this will be what? This will have a phase lead of plus 120, right? Because here also if you see from the first term I had a phase lead of plus 120. So this will have a phase lead of plus 120. So this will be plus 150 degrees. So I hope now you can derive for the other expressions like VCA, VC, VAB, just the negative. Just add or subtract a 180 degree angle with this particular voltages, you will get your value. Okay, so that's how you remember. Just remember these two, and then from there you can derive the other ones. Okay, so in case of ABC sequence, what will happen? I will rotate in the clockwise direction. So first A will come, then B will come, then C will come. In case of ACB sequence, if I rotate in the clockwise direction, first I will encounter C, then I will encounter B, then I will encounter like that's how I will encounter, right? If I rotate in the clockwise direction. So just hold on. So this omega is actually wrong. This should be rotating in the clockwise direction, not in the anti-clockwise direction. So this is how also you can determine the phase sequence if the phasor diagram is given. If the phasor diagram is given and if I rotate in the clockwise direction, first I will encounter A, then I will encounter here if the sequence is ABC and I rotate in the clockwise direction, first I will encounter A, then I will encounter B, then I will encounter C. So this is for the phase sequence ABC. Okay, if I encounter in the clockwise direction for phase sequence ACB, first I will encounter A, then I will encounter C, then I will encounter B. Okay, from this phasor diagram also you can determine the phase sequence. Now let's discuss like about three phase power. Okay, what is the three phase power? So the three phase power comes out to be this. Actually it is not pulsating. Three phase power comes out to be this, it is not pulsating. You can derive it. So three phase power will be what? For a single phase the voltage is VPH and current is IPH. Okay, and three phase power will be multiplied by 3, and obviously Y is I conjugate because it is a complex power. Okay, so if I write these expressions down, ultimately VPH into IPH will come out to be what? VPH into IPH will come out to be VP phase RMS, I phase RMS into cos phi. VRMS, IRMS into cos phi. That is the single phase power multiplied by 3. So this can be rewritten in terms of peak voltages. So VRMS is what? V maximum divided by root 2. IRMS will be what? I maximum divided by root 2. So it will be V maximum, I maximum, and root 2 is getting multiplied 2. So it will be 3 by 2 VMP IMP cos phi. Okay, so my three phase power expression can be written in terms of this. Also I know that my, in case of star load, this is in case of star load. Okay, star load, I know this, that, or any load, this will work for any load actually. I know in case of star or delta, either one of the relationship follows. What is the relationship? That my V line to line peak or RMS, whatever you want to discuss. So from here also I can come. So all this formula, you can remember one formula and derive all the others. So my three phase power will be what? Single phase power into 3. Okay, what is single phase power? Single phase power is V phase into I phase conjugate, or I can write V phase RMS into I phase RMS conjugate. So I phase RMS cos phi. Just hold on. Okay, and three phase power will be 3 times this. So it is 3 times this. Okay, so this is sorted. Now there are multiple variations of this formula. So sometimes you might require some, like sometimes the peak voltages will be given, so you have to use this formula. Sometimes the line voltages will be given, so you have to use this formula. So you have to be smart. You have to be very, very smart. Okay, that is what you have to take care of. So I can directly write that if I want to write this in terms of peak value, so I know that my V phase peak value will be what? Root 2 into V RMS, V phase RMS. Correct? So or my V phase RMS will be peak value VMP divided by root 2. Okay, so I can directly say that I can replace this, right? I can replace V phase RMS, I phase RMS here. So what will this expression will come? Now another thing I can say is that we have already discussed that if I have star or delta, so for a star load the voltages change. For a star load the V line to line is root 3 times the V phase. If it is peak, then this relationship will be for peak. If it is RMS, this relationship will be for RMS. It is valid. So I will do that actually. So what I will do, I will replace my V phase by V line to line by root 3. So if I replace my V phase by V line to line by root 3, what will happen? This 3 divided by root 3 will come. So this will become root 3, and I know for a star load the I line to line and the I phase are same, so it does not change. So this I phase RMS will become I line to line RMS. That's it. So this is also another formula. Cos phi, of course, will be cos phi, the power factor of the load. Okay. Now this factor you can ignore, the supply power factor. This is not important, okay? So else you will get confused. This is for the power electronics guys. So you can ignore the supply power factor for now. Now let's discuss for delta load. So this formula is valid for delta load as well, and this formula is also valid for any kind of load. So for delta load, what will happen is that here I know for delta that the line to line current is root 3 times phase current. Okay, line to line current is root 3 times phase current. So this will be what is my voltage? Voltage is same, right? Line to line voltage and phase voltage are same. So what will happen now? Instead of this I phase RMS, I will replace in terms of I line. So this will be I line divided by root 3. So again root 3 and will get cancelled. So I will have root 3. This VL will just V phase will be replaced with VL. I phase will be replaced with IL. So ultimately this comes out to be root 3 VL IL cos phi. So that's how, like, this formula is always valid no matter what. Okay, so that was the formula for this one. Now let's discuss about a 3-phase load. Okay, I have not discussed about, like, I've discussed about 3-phase power. Actually this should have come later, is after discussing about 3-phase load, but that's fine. We will move this slide to here, right? So let's discuss about 3-phase load. So there are mainly two kinds of load. As there are mainly two kinds of source, star and delta connected, there will be mainly two kinds of load. Okay, so one is the star connected load, another one will be the delta connected load. So in case of star connected load, there can be two options again. The neutral wire can be present or not present. So neutral wire is generally used for like transferring the unbalanced current. Okay, if the system is completely balanced, then the current in the neutral wire will be 0. Okay, don't worry, in the syllabus only balanced supply is there, so you don't have to worry about unbalanced system. In power systems we will learn about unbalanced supply. Okay, so that is about the neutral connection. So I have two connections, star and delta. So for a star connection, if the load impedance is ZY, for the same this what will be the per phase impedance if the supply is also star connected? So per phase impedance will be between the a line and between a neutral. So it will be same ZY only. So let's assume all of them are ZY. Okay, if it's a balanced system, so all of them are ZY for now. Let's not keep them Z1, Z2, Z3. Let's assume all of them are ZY. So if all of them are ZY, okay, what will be the equivalent delta? Okay, what if I wanted to measure the per phase impedance in delta? What if my source is delta connected? Okay, so if my source is star connected, then there is no problem. Okay, I will copy this whole thing. We'll just do one thing. Let me so here, right, if the where can I will go to the next page. So okay, it went away. Let me mark it log. Yeah, still it is log. Okay, yeah. So if I have a star connected supply and if I copy this thing, and if I connect it, so what will be the per phase impedance that we will measure? So per phase impedance, right, if I just connect these wires, together, okay, A with A, N with N, B with B, C with C, then the per phase impedance here, right, what I will measure is ZY only, that is the per phase impedance. Okay, now if I have a delta connected supply and I want to measure the equivalent impedance, right, of the same star connected network, how will I measure? Because it is not that simple, right? It is not that simple basically. So how will I measure? So what I will do is I will convert this into delta. I cannot measure, I cannot connect E, B and C, then neutral wire will be left out, right? I cannot measure the impedance. So what we will do is we will convert this into delta. So how do I convert this into delta? So delta conversion is very simple. Delta conversion is very simple. So if you remember, if I have to convert from star to delta, how do I remember? Like how do I remember the formula? There are mainly two formulas. Star to delta, I remember with the first word, okay, first letter. So I have star, so it is summation. So there are mainly two formulas, right? If you remember, there are mainly two formulas. One formula was it was z1 plus z2 plus z1 z2 divided by z3. Okay, another formula was z1 z2 divided by z1 plus z2 plus z3. Okay, these two formulas were there. So if it is star to delta, then I have S here. So S means summation. Summation means this one. So I will choose this formula. Okay, that's how I used to remember. Of course, you can have your method of remembering the formula. So here I will convert this, right? So I have to convert from star to delta. So let's assume all the impedance are ZY only. All of them are same. So it will be ZY plus ZY plus ZY into ZY divided by ZY. So it will be 3ZY. So actually, if my supply is delta, right, then the per phase impedance delta will be 3 times the per phase impedance of the star connected load. So that is what I have written over here, the comparison. That is what I have written over here. Okay, I hope now you have understood the thing. So both the star and delta connected loads, balance loads, because all of them are balanced, that means all the impedance are same, can be transformed with this relationship. Okay, either you can remember this or simply use this formula, right? Whatever I have discussed, star to delta conversion, you have studied since childhood, so you will be able to do it. Now, three phase load can have two possibilities, right? Sorry, four possibilities. If as the source is star, so the load will be also star. If the source is star, load is delta. If the source is delta, load is delta, and if the source is delta, load is star. So we will cover these three. Okay, and this one, the third one, I will give you as homework, delta delta. Okay, like not that, like this is not that difficult, this will be easy, because whatever system will come, all of them will come as balance load. We will solve few gate PYQs as well, don't worry, we will solve few gate PYQs as well. So three phase power we have already discussed. So let's like solve few basic questions. Okay, so here we have to determine the phase sequence of the set of voltages. So if I assume my so everything is in cos, so we'll assume that my 200 cos omega t to be my reference. Okay, so 200 cos omega t is my reference. So if 200 cos omega t is my reference, that means that this VAN is leading by 10 degrees. So this is my reference. Okay, and VAN is leading by 10 degrees. Okay, now my VBN is lagging by 230 degrees. So 180 degrees will be somewhere here, 230 degrees will be somewhere here. Okay, so my VBN, okay, what angle is this actually? Okay, this is 180. Okay, I can measure the angle as well, that's great, man. So 230, right? How do I measure the angle? This is 180. Okay, it is 230 will be somewhere. Okay, it is, why is it reducing? Okay, it is measuring the angle in the clockwise direction. How do I measure the angle in the anti-clockwise direction? So in the clockwise it will be 130, right? Yeah, 130. So this angle will be 130. So 130 will be somewhere here. So this is great feature. Okay, 130 will be somewhere here. Okay, this is like 130 in the anti-clockwise direction or 230 in the clockwise direction. Both are same. So this will be VBN. Okay, now VCN is lagging by 110 degrees. So if it is lagging by 110 degrees, that means it is leading by 250 degrees. Leading by 250 degrees. So to lead by 250 degrees. So I will be lying somewhere around here. Okay. So So this will be my VCN. So now, like, how do I identify the phase sequence? Very simple, right? Very simple to identify the phase sequence. Just move in the clockwise direction, rotate in the clockwise direction, and see what phases I'm getting first. So I'm getting A, then I'm getting C, and then I'm getting B, ACB. Okay. So very simple, very easy. Or you can directly mathematically do it, or you can do it in the phasor format. Whichever one is suitable by you, you do it. Whichever one is suitable by you, you do it. Okay. Very simple. Like these kind of question also can get asked. Okay. This kind of simple question can get asked in EC. Okay. So just be careful about that. So now let's discuss about balanced start to star connection. Okay, let's discuss about balanced start to start connection. That means my supply is also star, my load is also star. So here, right, bit of like many things are here. So we will dissect each and every term slowly. So in a balanced star to star, what happens is I had assumed that everything is ideal, that I have only load resistance, I don't have any source impedance and line impedance. So the wires that come to your home, right, of course they will have some impedance, right? It will be small, but it will have some impedance. Okay, and your source of course will have some source impedance. Generally what happens, like overall your star impedance, right, overall impedance, these three will get added. So Zs, like these are three are in series only because current is flowing in series. So Zs plus Zl plus Zs plus the line impedance plus the Z capital L. Okay, so this is my Zy. Now generally what happens, generally if nothing is mentioned, we will assume our Zs and my Z ZL, this will be the line impedance, actually this will not be the E line impedance. ZL will be almost equals to 0. Okay, for our easier calculation. So approximately my Zy, the overall star network impedance, becomes ZL only, the load impedance only. Okay, that is what we assume. So I hope you have understood this basic point. Now, like how the current will flow. So if you see the currents, right, for the phase A, currents will start from here and then come back through the neutral. For phase B, currents will start from here and then again come back through the neutral. And for phase C, currents will come back here and then again come back to through the neutral. Okay, so this neutral impedance also can be sometimes neglected. Okay, so that's how that will be the flow of the current basically. Now voltages we have already discussed. So like we have now, this is the balanced star to star connection with approximated impedance. So voltages we had already discussed, currents also we had discussed. Since the sum of the voltage neutral wire carries no current, phase voltage. Okay, so like the balanced network, right, IA is coming here, IB is coming, IB is coming here, IC is coming here. So what will be IN? So if I apply a KCL at this node, IN plus whatever is the incoming current, IN plus IA plus IB plus IC will be equals to 0. Okay, so my IN plus IA plus IB plus IC will be equals to 0. So ultimately my IN will be equals to minus of IA plus IB plus IC, and if the system is balanced, you will observe that all of them are phase shifted by 120 degrees. So what will happen is that this sum will come out to be 0. So like visually also I can tell you that the, let's assume that the phase like the phase current IA will be somewhere here. Okay, just let's assume this. So IB will lag IA by 120 degrees somewhere here. Okay, so 120 degrees, where will 120 degrees lie? 120 degrees, right? It's lagging, so it is 240 degrees, so it will lie somewhere 240 degrees. Okay, so 240 degrees will be somewhere here. Okay, so this will be my IB and my IC will lead IA by 120 or it will lag IB by 120. Any both way is same only. This B I am not able to write properly. Okay, so IB will lie somewhere lie 120 degrees, it will be somewhere here. Okay, so IB will be here. Just like the amplitude also is same only, even though it seems that amplitude is different, but it is same only. This will be IC. Okay, so if you add these three up, right, what will happen? If I add IC and IB, actually the component will come somewhere around here, the addition of IC and IB. So these will cancel each other out. So ultimately the summation of all the three, IA, IB and IC, will be totally 0. Okay, all the summation will be totally 0. So that is the crux basically for a balanced system. For a balanced system, the sum will be 0. So like how can I prove it as well? I can prove it as well. So if I have a system like this, right? If I have a system like this, and what will be the phase current IA? IA phase current will be what? This VAN by ZY, that will be the IA phase current, correct? The voltage across the impedance. So IA will be VAN divided by ZY, IB will be VBN divided by ZY, IC will be VCN divided by ZY. So same thing, if I add IA plus IB plus IC, so it will be VAN divided by ZY plus VBN divided by ZY plus VCN divided by ZY. So this will be equals to 1 by ZY VAN plus VBN plus VCN. Same again, if you remember the sum of the voltages as they are finite, this will also be equal to 0 only. Okay, so ultimately the summation is 0. So IN is also 0. Hence the drop in this impedance, right? Even if there is impedance here, Zn, the drop will be 0 because current is 0. Hence there is no drop. So the V small n capital N, if there is impedance here, right? If there is some impedance here, current is 0. Hence the drop is also 0. It will be IN into Zn, which will be 0 only. So it does not matter if I have neutral impedance or not, the current will be 0. There will not be any loss in the neutral. Now if let's say if it is a balanced system, what I can do, I can convert, because it's a bit hectic, right, to draw all this. I can convert this balanced three-phase system into a simplified per phase system. So in per phase system, I will just write the phase A voltage and phase A current. Okay, and all the other phase will be what? The amplitude will be same, just they will be phase shifted by 120 degrees. That's it. They will be phase shifted by 120 degrees, like phase B, phase C. Okay, so we simplify. So basically my IA will be what? IA will be VAN by ZY. This is enough. Okay, and for all the other phases, I have to just add the angles. That's it. Add the angles. So let's solve a very basic question on this. So first you have to see whether your system is balanced or not. So I am observing that my system is actually balanced, because I see this is my impedance 10 plus j8, this is also 10 plus j8, and this is also 10 plus j8. So in all the three phases the impedance is balanced. Is my source balanced? Yes. This is 110 angle 0, this is 110 angle minus 120, this is 110 angle minus 240. So all of them are phase shifted by 120. Load is balanced, source is balanced, and I have a neutral impedance. But it does not matter, because I already know that the neutral current will be 0. Okay, it is a, okay, sorry, it is not a neutral current, sorry, it is like we don't have any neutral connection here, just we have a source impedance is also balanced, and the load impedance, that's it. Okay, so what we have to calculate, we have to calculate the line currents. So what I can do is I can convert this three phase system into equivalent single phase system. Okay, and then from there I can simply write down the expressions. So this, right, this is a VAN, and okay, where is the neutral here? There is no neutral. This is like a this is the common point, right? So neutral is here, right? So even though they have not shown my neutral, so I can assume a virtual neutral. Even though they have not shown any neutral, I can assume a virtual neutral, because this is the common point of the star connected network. So this portion is a single phase only. Okay, I can write down this. So if I convert this, this will be V 110 angle 0 and 5 minus j2 10 plus J8, and so this is a like single phase conversion, whatever we have discussed, single phase conversion. So I can directly find out the IA current, and if I know the IA current, I will be able to find out IB and IC as well. Okay, this is my neutral, this is small n, this is capital N, and this is my phase A, correct? So what will be the current here? So this is my VA basically. So current IA for the single phase equivalent model, IA will be equals to VA 100 divided by the whole impedance, right? So it is 5 minus J2 plus 10 plus J8. So this will be 100 divided by 15 plus J6. So I can directly from here calculate the values basically. So if I want to calculate the values, this will be 15 whole square plus 6 whole square whole under root 16.185. This by multiply by 100. This will be 6.19 angle. What will be the angle? That is what I have to find out. So angle I have to find out, right? Okay, something am I doing wrong? Like it feels like something I'm messing up here. This is J6, this is 15. Yes, everything is correct. Okay, just let me quickly verify this. 15 whole square plus 6 whole square whole under root, okay, into 100. No, it is correct only. It is 110. Okay, sorry, it is 110. That is what I was thinking. It is 110. Sorry. So it is 110. This will be 110. This will be 110. So 210. So this will be 6.8. What about the angle? Angle is what? Angle is 6 divided by 15 tan inverse. So 21 minus 21.8 degrees. Okay, so this is the current. This is the load current. Okay, and this is the phase A current. What will be the phase B current? Phase B current will simply lag this by 120 degrees. Amplitude will not change because it is a balanced system. So it will lag by 120. So this will be 141.8 minus 141.8 degrees. And what about phase C? So phase C will lead by 120 of phase A current, right? So it will lead, the amplitude will be same, 6.81. So it will lead. So this value will be 98.2 degrees. Okay, so these are the currents. So that's how simple it is. So these kind of simple question will be asked only. Okay, you will be given a balanced three phase load like supply, and you have to convert this, analyze it as a single phase supply, and then calculate the currents and just phase shift all the other values with 120 degrees and you're done. Okay, that's how simple it is. So now let's discuss about the balanced star to delta connection. So if I have a star to delta, what we will do is, first of all, we will convert this delta to star load. Okay, we will convert this delta into star load. That will be easier for us. Okay, like two things we can do. There are two ways to go about this. Either I convert this into line, like if you don't want to convert, right, from star to delta, you can directly also solve. Okay, without converting it star to delta, you can directly also solve. How will you solve? So there are two methods to solving this. So first method is simple conversion. So you convert this load, you convert the load from star to delta. Okay, this is the first way to solve. Let's say if you don't want to convert, right? Next, what is the next way? Next way is you calculate using line voltages. Use the line voltages. So we have derived the line voltages, right? So these are my phase voltage, VAN, VBN, VCN. What is the line voltage? Line voltage is already given. This I have already derived. in the starting of this lecture. So what will be this value IAB current? IAB will be VAB divided by Z delta. So what is VAB? VAB is the line voltage. So line voltage is given here. That's how simple it is. What is IBC? IBC will be VBC divided by Z delta. So what is the line voltage? Line voltage is VBC, that is given here, divided by the Z delta. Like that also you can simply solve. Like that also you can simply solve. For line voltages, what you have to remember, that the amplitude increases by root 3 times and the phase shift is there by plus 30 degrees. Phase shift is there by plus 30 degrees and amplitude increases by root 3 times. That is the only thing that you have to take care while using the line voltages formula. Okay, same thing whatever I have discussed is written over here. What this will be my currents, right? So these are the currents across the load. These are the currents across the load. Now if you want to measure the line current, IA, IB, IC, how will you measure the line current? So you can measure the line current with respect to like this. IA will be what? It will be IAB minus ICA if I apply KCL at this node. So like that you can calculate the line currents. Same here. And for this the current expression will come out with this you don't need to remember. No need to remember this. Okay, you can simply use the phasor addition formula and from there you can calculate these many things. If you remember, right, you will get mad. So I don't want you to remember everything. Just the voltage is enough. From voltage you will be able to find out the current. And if you don't want to actually calculate this without if I don't want to calculate this, right, so this method you will use when second method you will use when I have to actually calculate the phase currents across the load, currents across loads. So if I have to calculate the currents across the load, I will use this line voltage method. So simply line voltage divided by the impedance will give me the currents across load. Now if I want to measure the currents across the line, what I will do is simply I will convert this delta connected load from delta to star. Okay, after I convert from delta to star, what will happen? Simply this will become something like this, right? Okay, I will not be able to draw it unfortunately. So plus minus here will be there, minus plus, and this load also will be converted into star load, right? So now, right, if this load is converted into star load, and we know that this will be Z delta by 3, correct? Z delta by 3, Z delta by 3. Okay, that is because it is in division. Yeah, it will be Z delta by 3. Now I can directly, because this is neutral, this also will be a neutral. I got my neutral point. So what will happen? This will be simply VAN. So what I will do is my line current IAN or IA will be equals to simply VAN divided by Z delta by 3. That's it. That's how simple it is. Okay, like this also you can find out without stressing, like without using this formula. Okay, this you will use when I have to find out the line currents, source line currents, source line currents. Okay, so yeah, that was about it. Whatever I have discussed, like simply convert this and solve using single phase method, that is also totally fine. So we will solve one question. A balanced ABC sequence is star connected source of VAN is equal to this. It's connected to a delta connected balanced load of 8 plus J4. Calculate the phase and line currents. So they are asking me to calculate the phase and line currents both. So if they, first of all, they are asking me phase currents. So phase currents means that I have a load here, I have a supply here, plus minus, then plus minus, VAN. So this is VB ABC, right? This will be VBN, this will be VCN. Okay, Z phase, so this will be 8 plus J4, and 8 plus J4. Okay, so these are my basically line currents and voltages. So now what we can do is just hold on a second. We can sorry, this is not this is not connected. My load is delta connected actually. Sorry, load is delta connected. So if load is delta connected, ignore my drawing. Okay, please ignore my drawing. So the load is delta connected. This will go here and this will go here. Okay, so first they are asking the line phase currents. So phase currents I will calculate. What I will do is I will convert this, right, line voltage into phase voltage. So what will be VAV, because this will be my phase voltage, right, VA and B. Okay, so my VAB will be root 3 times the phase voltage 100, so it will be 100 root 3. And what will the phase angle? Phase angle, it will lead the phase voltage by 30 degrees. Okay, so it will lead by 30 degrees. So this will be 10 degree plus 30, that is 40 degrees. This will lead by 40, 10 degrees plus 30, that is 40 degrees. So from here I can directly calculate the phase current. IAB will be VAB divided by Z delta. So this will be VAB divided by Z delta. So Z delta will come out to be like VAB is root 3 times this 100 root 3 angle 40 divided by Z delta. Z delta is 8 plus J4. Okay, so this value will be 173. This value is 173.2 angle 40 degree divided by 8 square plus 4 square under root 8.944, 4 divided by 8 tan inverse angle 26.56 degrees. Okay, so plus 40, 13, so this angle will be 13.44435 degrees, and this will be 173.2 divided by 8.944, so 19.365. Okay, so this will be the current, phase current. So what about the other phase currents? So other phase currents will be very simple, right? So BC, just copy the B over here and write the other term. BC will be equals to V BC divided by Z delta, which will be like the amplitude will be same, the phase will be shifted by 120 degrees, it will lag, so minus 120. So it will be, if I subtract minus 120 here with this value 13.435 minus 120, this will come out to be 100 and minus 106, right? Okay, this will be negative, this is positive. Just I am checking if I am doing this correctly. Yes, minus 106, minus 106.565 degrees. What about I? Again I will write I CA, so C will come here. Okay, and other one will be copied, so ICA will be again V CA divided by Z delta, which will be equals to 19. Amplitude will not change, 19.365 angle. Now it will lead the initial current by 120 degrees. So this will be 13.435 plus 120, 133.435 degrees. Okay, so this will be the value basically. This will be the value. Okay, now what about the phase currents? So either you can use this formula, okay, but I have told you, don't remember this formula. So what you will do is you will convert this star into delta and then calculate the phase currents, then calculate the line currents. So if I convert this star into delta, so my load now will become, sorry, if I convert this delta into star, so my load will now become this load will be here it will come, this will be one of the load, this will be the other load, and this will be the third load. Okay, so this will connect here. So here, right, if I'm converting from delta to star, so that means it is division. So the formula that I will use is Z1 Z2 divided by division, right, Z1 plus Z2 plus Z3. So ultimately what will happen is it will be Z delta divided by 3. Okay, so this will come out to be 8, what was the impedance, 8 plus J4 divided by 3. So 8 plus J4 divided by 3, here also 8 plus J4 divided by 3 divided by 3. Okay, so now I can directly basically calculate the currents, right? So neutral, it is a balanced load, so neutral can be connected. Again, I can write the equivalent single phase equivalent, right? So it will be simply a single phase equivalent will be, this will be VAN, this will be the load, and this will be my IA current, right, the line current now. Okay, so this is my IA current, that is what I'm interested in. So all this hassle I'm doing just so that you don't have to remember that formula, right? I don't want you to remember everything. Okay, so this will be the impedance 8 plus J4 divided by 3. Okay, so IA will be equals to VAN divided by 8 plus J4 divided by 3. So 8 plus J4, right, is okay, I have not written, I have written it. So 8 plus J4 will not change, obviously, just a multiplication by 3 will come here with respect to the 10 100, right, 110, I guess it was 110, or what was it, 100 only. Okay, so this will be divided by 3 is also there, so 3 into 100, what is the angle, angle will be whatever is the VAN angle, VAN angle is 10 degrees, so this will be 10 degrees. Okay, so from here, just hold on, from here my current, right, line current, this will be, I will just quickly calculate this, 100 divided by 8.944 into 3, so it will be 33 point something. Okay, 33.54. What will be the angle, angle will be 10 minus 26.56, so this will be minus 16.56. Okay, this will be the phase A current. What about the other phase currents? Okay, the other phase currents will be just IB will, again what, IB will lag phase A by 120 degrees, so it will be like amplitude will be same, but it will lag by 120 degrees, so I have to subtract another 120, so this will be minus 136.56 degrees. IC will lead by 120 with respect to IA, so it will be 103.44 degrees. Okay, so what is the shortcut? Shortcut is basically another shortcut is like, if you know my phase currents, what you will do is the line current will lag the phase current by 30 degrees, and the amplitude will increase by root 3 times. So that is what is written over here. Okay, so if you don't want to, if you want to remember this, you can directly apply the formula. If you don't want to, you can use this simple conversion. Okay, So that was the solution of this particular question. Now let's discuss about another type of load, that is balanced delta load. Again, same thing, right? I will not discuss again. I will not discuss the same thing again. Like if I have delta connected load VAB, like what will be the, how do I, sorry, this is not balanced delta, sorry, it is balanced delta to star. Okay, if it is balanced delta to star, that means the easiest method would be, if I want to calculate the line currents, what will I do? I will convert this star to delta and I will calculate the line currents. So for line currents, if I have to calculate the line currents, what I will do? I will convert my star to delta impedance. Okay, load I will convert from star to delta. So I will be easily able to find out the line currents. What will be the line current? It will be simply VAB divided by whatever the delta impedance, equivalent delta impedance. In our case, it will be what? It will be 3 into star impedance, right? 3ZY. If I have to calculate the phase currents, now things will be a bit different. So if I have to calculate the phase currents, how will I calculate the phase currents? So phase currents, if I have to calculate, so there are two ways to go about this phase currents, right? So either what you can do is, either you can convert this delta into its equivalent phase source. So how do I convert? So I remember that if I have a delta source here, if I have a star source here, okay, and I have a neutral here, and I have another source here, right? Another source here. So whenever I calculated the VAB, what was happening? The equivalent VAB, right? This VAB was coming out that it is root 3 times the initial voltage, this V angle 0, root 3 times V and plus 30 degrees, correct? Now let's say if I change this, now my VAB, let's say, is V angle of 0 degrees. Now if I want to go back to my star, equivalent star, so how will I do? So if I have to go from star to delta, what I did, I added angle of 30 degrees and multiplied by root 3. So if I have to go from delta to star, what will I do? I will subtract angle 30 and I will divide by root 3. Subtract angle 180 and I will divide by root 3. That is the only thing that will do. Okay, so that's it. So same thing, let's say if I have to find out the phase currents. So phase currents, how will I find out the phase currents? So as I am comfortable more in star, if I have to find out the phase currents, what I will do, I will convert my source from delta to star. Basically my VAN will be VAB divided by root 3 angle of minus 30 degrees. Okay, that's the only thing that we have to take care of. Everything else is sorted. So these are the conversions. Basically I don't want to go, I will just solve with using this method, right? This equivalent method, that is the easier method, because in question you will be asked a balance, like you will be asked a balanced load only, you will not be asked any like unbalanced load. Okay, you will not be asked any unbalanced load. So this is the last question of the textbook. Next we will solve the gate PYQs. So like I want you to try out. So please pause the video and try out this question. This is the first question. This is a gate question. This is an unbalanced load, but trust me, this will be easier question. Okay, if gate has asked unbalanced, it will be very easy question. And this also came in gate recently only, and this also is a gate question. And this is the last question. So try it out by yourself, and then I will solve all the questions. So let's solve this question. A balanced star connected load with a phase impedance of this is supplied by a balanced positive sequence delta connected load with its line voltage as 210 volts. Calculate the phase currents. So I have a balanced delta connected load here with the line voltage. So this line voltage is 210 volts. Okay, and I have a star connected load, and they are asking me the phase currents. Okay, so if they are asking me the phase currents, it is difficult, right? Calculating the phase currents is difficult. What I'll do, I'll convert this delta load into delta source into star source. So this will be here 210 divided by root 3, and angle will be phase shift because they have not given me any angle. So initially I will assume this as reference. So this will be actually they haven't even asked us angle, but still we will calculate the angle. This will be minus 30, and I will have B phase over here. This will be 210 divided by root 3 angle. This will be minus 150 210 divided by root 3 angle. This will be plus 90 degrees. Okay, so this will be my star connected load basically, and star connected source basically, and my star connected load is already here, right? Already my load is star connected, that is 40 plus j 25. So this is my, just ignore my drawing, okay? My drawing is really bad. So this is my star connected load. I can not this will not connect it, this will connect here only. So this is my zy. So my zy equals to 40 plus j25 ohms. So this will be so right, I can directly convert this single phase, right? Single phase I can connect the neutrals. So basically my phase current I phase will be what? This 210 divided by root 3 angle minus 30 degrees divided by the zy is 40 plus j25. So the values will be, this value will be 40 whole square. Okay, I can take common 5. So if I take common 5, right, this will be 42 divided by root 3 angle minus 30. This will be 8 plus 5 j5. This will be equals to, so now if I calculate 8 square plus 5 square whole under root, this will be if I multiply into 42 divided by root 3, so this will be 2.57. And what about the angle? So angle I have to calculate. Angle will be, this is 5 divided by 8 tan inverse, and minus is there already, so minus 30, so minus 62. Okay, this angle roughly comes out to be minus 62 degrees. And the other, what will be the other phase current? So this will be the current of the phase A. What about the other phase currents? So this was A, this was B, right? This was B and this was C. So the other phase currents will, the amplitude will be same, just the phases will be different. So this will be IB will be equals to 2.57. It will lag by 120, so minus 120 if I do, so it's almost equals to minus 182. Okay, either I can subtract 120, yeah, this will be minus 182 yeah, 182 degrees. And what about the other phase current? Other phase current will be IC will be, it will lead by 120, so I will add 240, that will be 58 degrees. Okay, so IC will be 58 degrees, IB will be this. So these are the phase currents that they have asked. So these kind of questions can get asked. Now let's solve the gate feedback question. Okay, so although it seems like it is a delta connected, like it is a unbalanced load, but still you will be able to easily solve it. Okay, so let's solve this question. So like very basic question. So unbalanced load is given, balanced supply is given, but unbalanced load is given. You don't have to worry about this. Okay, you will be able to solve using the balance concept. So in gate, if some three-phase question will come, question will be on the easier side only. It will not be on the difficult side, not be on the calculative side. So here they are telling me that a three-phase balance voltage is applied to the load. Load is like unbalanced, and phase sequence is R by B. So this is my R phase, this is my Y phase, this is my B phase. Okay, the ratio of magnitude of IR over magnitude of I, ratio of magnitude of IB over magnitude of IR. That is what we have to find out. We have to find out the magnitude of IB over magnitude of IR. So what is IB? If I notice IB, right, IB is actually equals to the summation, like if I apply KCL at this node, if I apply KCL at this node, it will be IB plus IR plus IY equals to 0. So my IB is actually equals to minus IR plus IY. Okay, so IB is minus IR plus IY. What is IR and IY? So my IR is equals to what? IR is this phase voltage divided by the phase impedance. So phase voltage, this is neutral, right? This is neutral. So it will be VRN divided by the impedance, that is minus J10. IY will be what? IY will be V. This will be Y actually. Sorry, this will be Y and this will be B. Don't get confused. Okay, don't get confused. It follows RYB sequence. So this will be Y and this will be B. So it will be V yn divided by plus J10. Okay, now what is VRN and VYN? They have told me that it is a balanced three-phase supply. So my assumption is I will assume an initial reference. So I will assume VR to be reference. So it will be V angle 0. So my V, then after this, what phase sequence I will follow? I will follow VYN. VYN will be V angle minus 120 degrees, and VBN will be angle V plus 120 degrees. Okay, so VRN, YN, VBN is all these values. So simply just put the values. And you will get your result. So your IR will be what? IR will be equals to VRN, that is V angle of 0 divided by J10 or minus J10. So this will actually be V by 10 into angle of plus 90 degrees. Okay, or I can directly write this as plus J V by 10. Now what is my IY? IY will be V angle of minus 120, divided by plus J10. V angle of minus 120 divided by plus J10. Okay, so this will be equals to basically V by 10 angle and another minus 90 will get added. So this will be minus 210 degrees. This will be my IY. And what will be my IB? My IB will be the negative of these two, right? So J V by 10 and plus V by 10 angle minus 210 degrees. Okay, so this will be minus sign will be outside, V by 10 angle 1 angle 0, 1 angle 90 degrees plus 1 angle minus 210 degrees. Okay, from here you can simply calculate these values. I can calculate these values, right? So this value will be what? This will be like, this will be J only, this will be J, this will be minus V by 10, and this value, right, cos of 210 is minus 0.0 that is root 3 by 2, and sine of 210, right? Sine of 210, it will be plus 1 by 2, j 1 by 2. So this will be minus v by 10 minus root 3 by 2 and plus j 3 by 2. Okay, so I can take common here, root 3 by 2 minus root 3 by 2 I can take common. Okay, so this will be v by 10 into root 3 divided by 2. This will be 1 minus j root 3. Okay, this is my IB. This is my IB. Now what do I have to calculate? I have to calculate the magnitude of IB over magnitude of IR. So magnitude of IB over magnitude of IR. Magnitude of IB over magnitude of IR. So magnitude of IB will be what? So from here I can directly write that my magnitude of IB will be equals to V by 10 into root 3 into 4, right? That is the magnitude of, not 4, sorry, into 2. So, and what is the magnitude of IR? Magnitude of IR, if you see, it is simply V by 10 only. It is V by 10 only. Okay, so this will be V by 10 into root 3 divided by V by 10. So this will be root 3, that is 1.732. So 1.732 will be your answer for the question. So like, although the question seems difficult because it is unbalanced load, but if you solve with basics, right, whatever I have discussed in this lecture, you will easily be able to crack all the gate exam problems. So let's now move on to the next question. So this also came in gate exam only. So this is the next question. So here what we have to find out is, in the circuit shown below, a three-phase star connected load is connected to a balanced three-phase supply with phase sequence ABC. The star connected load has impedance ZA as 10 ohm, ZB is 20, and this is ZC is in ohms. I don't know what is the value of ZC, and it is an unbalanced load. So they are asking unbalanced load, but don't worry, you will be able to solve it. For which the voltage difference across the node N dash will be 0. So they are telling me that the voltage difference across these two nodes will be 0. For which value of ZC? What will be the value of ZC such that the voltage difference across these two nodes are 0? Okay, so if the voltage difference across these two nodes are 0, that means my N and N dash, right? N and N dash are at same potential. N and N dash are in same potential. That means if, let's say, I assume I connect a impedance here, it does not matter. It does not matter if even if I connect an impedance, even if I connect these two wires, because they are in same potential, I can connect these two wires, right? Because they are in same potential, I can connect these two wires. So the current, right here, let me assume a current IN. Let me assume this current as IA. Let me assume this current as IC. Let me assume this current as IB. So the current IN will be equals to IA plus IB plus IC. Okay, that is what I know. Now if N and N dash are in same potential, that means even if there is a some impedance, let's assume there is some impedance. So there is some impedance, the voltage drop is 0, V N dash is 0. So if voltage is 0, that means the current is also 0, right? If there is some impedance, if the voltage is 0, that means the current is also 0. So my neutral current will also be 0. My neutral current will also be 0, because if I assume an impedance here and the voltage across this, like both of these points are in same potential, so there is no potential difference across this impedance. So if there is no potential difference across this impedance, that means the current is also 0. That means the current is also 0. So I can simply apply this rule. So I can write my IA, although the load is unbalanced, it will behave like a balanced system. IB plus IC will be equals to 0. Okay, so from here I can directly write what is my IA. IA will be the phase voltage VAN divided by ZA. IB will be VBN divided by ZB, and this will be VCN divided by ZC. Okay, so this will be equal to 0. So like it follows, it is a balanced three phase supply, and the like connection is 100 root 3. So whenever this voltage is given, right, this voltage is actually line to line voltage. So phase voltage will be what? Phase voltage will be divided by root 3. So 100 angle 0 VBN. It follows the phase sequence of ABC. So this will be 100 angle minus 120, and this will be 100 angle plus 120. Okay, that is what it will follow. So now if I just simply calculate these values, so this will be 100 angle 0 divided by ZA. What is ZA? ZA is 10 ohms. VBN is 100 angle minus 120 degrees divided by ZB. ZB is 20 angle 60. 20 angle 60 plus 100 angle 120 degrees divided by ZC. That is what I have to find out, equal to 0. So will be a bit difficult. So this is 10 angle 0 degrees, right? This is 10 only. Yes. So this will be 10 only. 10 plus 100. This is 5 angle of minus 180. So this is actually getting simplified. This will be 100 angle plus 120. I can take it on the other side actually. Divided by ZC. So this I can calculate. This will be 100 angle 120. ZC will be equals to minus 5. This will be minus 5. So ZC will be this will be minus 180. So 100 angle minus 60 divided by 5. ZC will be 20 angle minus 60. Okay, so these kinds of phasor calculation will come actually. So whatever we have been doing, right, it is actually required. So if they are giving some unbalanced load, it will be easier only. It will not be very difficult thing. Okay, so 20 angle 60 will be the correct answer for this particular question. So let's solve this next question. So in this question, what they're telling us, that two balanced three phase loads are shown, okay, in the figure, are connected to a 100 root 3 supply. Okay, this is the line voltage, and given that Z1 is this and Z2 is this, and like it is a balance, so these are all same, these are all same. The ammeter reading will be what? So they are asking me the ammeter reading. So it is a like delta connected load, okay, and they're asking me the ammeter reading. So what I can do is I can convert this star into delta, because I have to find out the line voltage. So I'll convert this star into delta, right? I'll convert I have to find out the line currents. Okay, sorry, I have to find out the line currents. So in case of line currents, right, which are same. In case of line currents for star are same. Line and phase currents for star and star are same. Okay, if you remember that this is my source, so line currents for the star connected load is same. Correct. This is my load, and here whatever is the phase current, this is the phase current, and this is the line current. Both of them are same. So I will actually convert this whole load into star connection. So this is already in star. I have to convert Z1 into star. So I have to go from delta to star. So what formula I have to use? I have to use division. D, right? Division. Division means this is the division. Z1 Z2 divided by Z1 plus Z2 plus Z3. So all of them are same only, that it is Z1 only. So it will be Z1 divided by 3. It's very simple. So Z1 is 18 plus J 24. So this will be 6 plus J 8. Six plus J 8. Okay. So this is what my like equivalent star connected load is. Now now what we can do, we can actually find out the equivalent impedance, right? So basically this Z1 I have converted into star, so this is also in parallel with Z2. So equivalent single phase load, right, will be this Z1 divided by 3 parallel with Z2. Okay, so Z1 divided by C is 6 plus 8J, and Z2 is also, I guess, 6 plus 8J only. So if both same impedance are in parallel, basically I divide by 2. So this will be 3 plus J4. So what they are asking me to find out the equivalent ammeter reading. So it is ammeter reading is the line current. So current, right, IA. So IR or IA, whatever the current they are asking, this will be the phase voltage divided by the phase current actually. So sorry, phase voltage divided by the phase impedance, right? So it will be V phase divided by Z equivalent, because my loads are like this, right? This is my Z equivalent, and this is my star connected load, right? Here I have star connected load. Okay, so basically I have to find out this line current, right? I can convert this single phase. So line current will be this voltage, phase voltage divided by the phase impedance. So this is my Z equivalent. Okay, so this will be what is V phase? So V phase will be like this is the line voltage, right? They have given me the line voltage 100 root 3. So this is the line voltage, but I have to find out the phase voltage. Phase voltage will be divided by root 3, 100. So actually they are just asking the like current magnitude. Ammeter can only measure current magnitude, so I don't care about the phase. Okay, so this will be magnitude of 3 plus J4. So magnitude of 3 plus J4 is 5, so this will be 20 amperes. Okay, this is 5 actually magnitude, so 20 amperes will be the reading of the ammeter. Okay, so let's solve this next question. So in this question, like we haven't given a balanced delta connected load, RC series RC circuit. It is a balanced delta connected load, and we have like a balanced supply. Okay, and it has a line inductance. Considering the change in the supply terminal voltage with loading to be negligible, calculate the magnitude of the voltage across VEB. Okay, so if I draw the circuit for now, if I draw the load, so it is like a delta connected load, right? Because the phase A and phase C is like phase A is here, and in between these two points, so in between these 2 points, phase B is here, right? In between AB I have a RC circuit, between BC I have a RC circuit, between CA I have a RC circuit. Okay, AB RC, BC RC, CA RC. Okay, now now what we have to do, it is a balanced delta connected load, so I will draw the load for now. I will draw the load. So I have a delta connected load here, so this will be RC, ignore my drawing. Okay, RC and RC. So I have R XC here, minus JXC, and R minus JXC. Okay, so now what I can do is, I have a like this line inductance I have, right? This line inductance I have, here as well I have line inductance, here as well I have line inductance, and my supply is here. Okay, it is a, let's assume this is a star connected supply, so it will obviously be a star connected supply only. Most cases it will be star connected supply. Okay, so this will connect here, or this will connect here, and this will connect here. So now what we need to do is, they are asking me what is the voltage at this is my A point, this is my B point. So what is the voltage in between this A and B point? So actually, right, it will be very difficult for me to solve this, right? It will be very difficult for me to solve this. So there is a way out. What is the way out? Way out is everything is balanced. So let me convert this into star. Then let me calculate the per phase voltage across that equivalent model. And then if I multiply it by root 3, I will get my line voltage AB magnitude. Okay. So what do I mean? So if I convert this, right, into equivalent star, right, this will be ZY, this will be ZY, 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 and ZY. Okay. So I have a ZY, ZY, ZY here. So this will be here, the inductance will be here, okay, and this inductance will be here, and this inductance will be here. So ultimately, right, these AB points will not shift. What has happened is that only I have converted this from delta to star, and this AB voltage will be still same. So if I am able to somehow find out AN voltage, VAN, right, so my VAB will be what? VAB, magnitude of VAB will be root 3 times VAN. Okay, magnitude of VAB will be root 3 times VAN. That's it. That's simply it. So I can directly write here, right? So this is my equivalent star connected load. So what ultimately what we have to do? So this, it is a balanced load, right? As it is a balance, like this is also XL, this is also XL, this is also XL. As it is a balanced load, so this neutral are connected. So I can convert this into single phase, because multi-phase calculating all this will be very difficult for me. So I'll convert this into single phase model. So single phase model will be something like this. This will be plus JXL. Okay. So single phase model, if I write, this will be my VAN. VAN. This will be the XL inductance, JXL. Okay, and this will be my basically R and XC as well, because like what is the equivalent? So I'm converting from delta to star. So I'm going from delta to star. So I'm doing division again, right? So this is delta to star. So I will do division. Division means Z1, Z2 divided by Z1 plus Z2 plus Z3. Okay. So basically everything is equal. So it will be the initial delta by 3, Z delta by 3. Z delta is R minus JXC. So this will be R by 3 and minus J XC by 3. So this is my neutral point, right? So what are they asking? If I just somehow, like, this is my initial voltage, this is my supply voltage, this is my point A, this is my point A, okay, this is my point A, this is my point A here, right? So I can say that my what will be my voltage basically? What will be the voltage? So they have given me 415 volts. So with respect to what? 415 volt, whenever they give this voltage, right, it is always line to line voltage. Whenever they give any voltage, this is always line to line voltage, but this is a phase voltage, right? So it will be divided by root 3. So this will be 415 divided by root 3. So whenever they mention the voltage, unless and until specified, by default you will assume line voltage. So I will write here one point, key point, that by default, if nothing is mentioned about the Nothing is mentioned about the supply voltage. Assume line voltage. Okay, that is the assumption that you will take. So now it's very simple, right? I have to find out VAN. It will be what? Voltage division. So it will be basically 415. So this is angle 0 basically, the phase A. So 415 divided by root 3 into simple voltage division, right? So this will be R minus JXC divided by 3 into R plus JXL minus XC. Voltage division. Simple voltage division. That is what I am doing. So what is R, what is XC, all this we have to calculate. So I can directly see from here, my R is 15 ohms. So R will be 15 ohms. Okay, my XC is 1 by j omega c, 1 by omega c. So it will be 1 by omega is 2 pi into 50 into C. C is 212.21 microfarad. So into 10 raised to power minus 6. So this will be XC will be equals to, this roughly comes around I think 15 ohms. So 100 212.21 into pi inverse into 10,000. This will come out to be 15 ohms. 15 ohms. What about XL? So XL, right, will be omega into L. So it will be 2 pi into 100 into 2 pi into 50 into, like, frequency is 50 Hz, 31.83 millihenry, right? So this will be 10 raised to power minus 3. So this will be basically 31.83 into pi. So this will come out to be, XL will be equals to roughly 10 ohms. Okay, so I can replace all this here, right? So my value will be 415 divided by root 3 into, this will be 15, R is 15, XC is 15, divided by 3 is there, and R is again 15 plus XC, XL minus XC. XL is 10, XC is 15. So this value, right, this value will come out to be, all these I am calculating phase, right, my phase voltage. So my phase voltage will be 415 divided by root 3. I can take here 15 common, right? If I take 15 common, this will be 15 divided by 3, 1 minus j, and in bottom, right, I can take 5 common here, right? I can take 5 common. If I take 5 common, this will be 3 minus 3 minus j, yes, 3 minus j, yes, 3 minus j. So what will be this value basically? So this is 115 root 3 into 5 into, this will be under root 2, right? I guess this will be under root 2. Okay, yes, this will be under root 2, and this will be, just calculating the phase voltage, plus minus 10 j5. Okay, just hold on. Anything wherever I have done something wrong, this is okay, sorry, I messed up, right? This will not be just this, right? Sorry, I messed up. This will be R by 3 and XC by 3. I messed up here, sorry. So this will be actually 5 and this will be 5. So this will be 5 plus j5. I can take 5 common. Okay, so I can take actually 5 common. So this will be 1 plus j. So now what we have to do is we have to simply calculate the magnitude, right? Okay. Oh, sorry, 1 3 was already here, right? Sorry, 1 3 was already here, right? This 3 was already here. Okay. Okay, this 3 was already here, and I have taken 5 common. So what happens is that this becomes like I have to ultimately calculate the magnitude. Magnitude will be, this will be 1, and this is 1 minus j, 1 plus j. So magnitude will be root 2, root 2. So this will ultimately become 1. So your value will come out to be 415 divided by root 3. Okay, this is my phase voltage, but they have asked line voltage. So what will be the line voltage? I've already discussed that the line voltage will be root 3 times this. It is a balanced system. Line voltage, I have to find out VAB. So VAB, right? VAB will be magnitude, will be root 3 times the phase voltage. So this will be root 3 into 415 divided by root 3. So 415 volts will be your answer actually. So it seems like, how is it the 415 volt answer? But 415 volts luckily is answer. Okay, so answer will be 415 volts. So this question was actually very good. So sometimes they do ask a bit like tricky question as well from this, right? What you have to do, you have to simply convert this into star, then you have to write down the equivalent. So good questions do come from gate exam from 3 phase, right? So recently also, these questions came recently as well. Okay, so I hope you have understood 3 phase systems. So now we will solve few additional problems, which, like, already we have solved few problems. We will solve these additional problems which are more relevant for power systems. Okay, so this is the first question. It's a gate PYQ. In the 3 phase balance system, 50 hertz, the value of the inductance L is 10 millihenry. Okay, the value of the capacitance for which all the line currents are 0 in millifarads will be. They are asking me what will be the value of the capacitance if I want to make the line current 0, that is the current here should be 0 ampere, that is coming, but a 3 phase balance supply has been applied. So this, let's assume that this is VAB, right? So this will be some V angle 0 degree, then the other phase will be V angle 120, other phase will be V angle minus 120. Okay, but I want to have infinite, like I want to have 0 current. How can the current will be 0? First of all, let me convert this star into delta. Okay, so here I have my inductance that will provide what kind of reactance? That will provide A plus J XL reactance, right? And then I will convert the delta into star. Okay, now will this be XC here? No, right? I'm converting star to delta, so it's summation, right? If you remember, I had already discussed how to convert from star to delta. So if I'm converting from star to delta, basically the formula is summation. Like, how do you remember? I remember like this, summation. So what does summation mean? Means summation basically means it is x1 plus x2 plus x1 into x2 divided by x3. So here x1, x2, x3 all are same, so it becomes 3x, right? So this will be 3xc. This will be 3xc. Okay, if you don't understand this, ignore. I hope you know how to convert from star to delta. Okay, so this will be 3xc. Now the aim is, I'm drawing the per phase equivalent. The point is the current here should be 0. How can the current here be 0 if I'm applying a finite voltage? If the impedance is infinity as seen from these 2 points, if the impedance is infinite as seen from these 2 points, then the current will be 0. So here this will be voltage V upon this impedance. Now what is this Z equivalent? Z equivalent, I am observing it is J into XL into minus J3 into XC divided by JXL minus 3 JXE. Okay, so I need this to be infinity. So obviously numerator cannot I cannot make numerator infinity. What I can do, I can make this equal to 0. If I make this equal to 0, then this will go to infinity. This will blow up, right? So basically the ultimate point is my XL minus 3XC should be equals to 0. That means my XC should be equals to XL divided by 3, or I can say that my, what is XC? XC is 1 by omega C should be equals to omega L divided by 3, or I can directly say that my C will be equals to 3 by omega square L. Okay, so this will be omega square is 2 into pi into 50 whole square. L, what is L is 10 millihenry, right? 10 millihenry is like, this will be 3 by 98. Okay, 10 millihenry means, yeah, 98 point, sorry, 986.96. okay, so into 0.01 into 3 into 10 raised to power 6, because they have asked in they have asked in millifarads. So in millifarads, what will be the value in millifarads? If I calculate, like, this will come out to be 3.39 into 10 raised to power minus 3 farads. Millifarads they have asked, so this will be 3 millifarads. Okay, question is actually pretty simple, elegant question, but like, first you have to understand the units. Unit conversions is very important. If you are smooth with unit conversion, then you will not mess up this question, and understand this conceptually. Why this has to be equal, right? Many students, they don't understand why this has to be equal, because the impedance has to be infinite, because the current they have told has to be 0. So this is the per phase equivalent circuit. Because it's a balanced circuit, I can draw the per phase equivalent, right? Per phase equivalent already we have discussed in the 3 phase. Okay, so this was the answer for this particular question. Okay, now for this question, a 3-phase load is connected to a 3-phase balance supply as shown in the figure. Okay, so 3-phase load is connected, okay, this is the 3-phase load. It is connected to a 3-phase balance supply. Voltages are given positive clockwise direction. The value of the R such that the current in the neutral wire is 0. Basically current here should be 0. What is the current IN? So if I write KCL at this node, it will be this current, IA current plus IC current plus IB current equals to IN current, right? So it's, I'm just writing the KCL. So IN will be equals to IA plus IB plus IC. Now the important fact to note here is that what is my IA current? It will be VAN, the voltage across this resistor, divided by the resistance, right? So very simple calculation. So it is just a 3-phase calculation. So this will be VAN, that is 100 angle 0 divided by R. What is IB? IB is VBN divided by the J10 impedance. What is VBN? 100 angle minus 120. So it will be 100 angle minus 120 divided by J10 plus 100 angle minus 120, 100 angle minus 120 divided by J10, and VCN is 100 angle minus 240 by minus J10. Okay, so I can directly write that they have told me in the question, given in the question, that they want the neutral current to be 0. They want the current in the neutral to be 0. So they want this to be 0. So if they want this to be 0, then I can directly find what is my R. R will be, first of all, let me calculate this value. 100 by R will be equals to, this will be 10. Okay, let me this minus j will go, this will go on that side, so plus 90. So this will be minus 30 plus, then this will be plus j, this will go there, so this will be minus j, so minus 90. Minus 90 is 10 angle minus 90, it will be minus 330. Can I write this plus 30? Is it possible? I can add or subtract 30 degrees, right? So basically I'm adding, it's like two phasors. Okay, one, if let's say this is the reference 0 degree, one is lagging by 30 10, another one is leading by 30 10, right? Magnitude is same. So whenever magnitude is same, either you do that vector addition formula, a square plus b square into 2ab into cos of angle between a and b, you'll under root, you'll get the value, or this is a shortcut that will be used multiple times, I will use it. So what happens if I have two vectors, right, that are equidistant from each other 30 degrees, okay, so they will directly, like the resultant will directly lie in the middle, it will be bisector, magnitude will be root 3. So this value will come out to be 10 root 3, magnitude will be root 3 times the magnitude of the other two vectors. So 10 root 3 angle 0, and here I have 100 by R. So from here I can directly write what is my R. R will be 10 divided by root 3. So 5.77. 10 divided by root 3. Sorry. 10 divided by root 3. 5.77. ohms. Okay. So that is what your R is equals to. I hope it is clear. So that's how you will solve. So here the answer will be 5.77. 5.77 ohms. Let's now solve the third question. So here we have to find out IR, IY and IB. Now remember here, right, this you cannot very easily solve. Okay, why you cannot very easily solve? The point here is, first of all, neutrals are not connected, and even if the neutrals, let's say this is ground, right, if let's say this is ground, so for a balanced system what would have happened, this also would have been ground. For a balanced system, this also would have been ground. These 2 points would have been ground if it was balanced. Let's say the load was balanced, that is 4 ohm, 4 ohm, 4 ohm. I will discuss about balance and imbalance systems later on, okay, when discussing about faults. But if all of them were 4 ohm, 4 ohm, 4 ohm, I will draw the circuit basically. I will show you, okay. So if let's say if the circuit diagram would have been something like this, the load was balanced, that is all of them were 4 ohms, 4 ohms, 4 ohms, then I could have simply grounded this, right? Then the analysis would have been very simple. I would have just have to do the per phase analysis. So I would have converted this circuit into per phase. So single phase only. This will be 10 angle 0. Here I have the resistor. Here I have the IR, and I will get the value of IR. No problems. I will get the value of IR. Okay. That's simple. But here the problem is load is not balanced anymore, right? So I cannot do this, right? Because the load is not balanced. So how will I solve? So you have to do the rigorous analysis only. You have to do the rigorous analysis. So what kind of rigorous analysis? So I can assume a potential here, that is Vn. Now neutral won't be 0 anymore because this is connected to ground, but this point will not be ground anymore. Neutral is not 0 anymore. Okay, so I have to assume a potential here, and then I will solve. I will apply the KCL at this node. So it will be Vn minus 10 angle 0. This is a vector, divided by 4 ohms plus Vn minus 10 angle, this point potential is minus 120 degree divided by 6 ohm plus Vn minus this 10 angle 120 divided by 8 ohms equal to 0. Okay, because there are only 3 nodes, right? And this node is open here. Remember, your neutral is not connected anymore. It is open. So here current is 0 actually. Current is 0. That's the trick. Current is 0 here. Okay. So now I will get the value of Vn. If I know the value of Vn, I will be able to find out IR, IY and IB. Okay. So your Vn, how do I calculate? So Vn will be equals to this, right? 2.5 plus 10 by 6. So 5 by 3 minus 120, then it is 5 by 4. So plus 1.25 120 degree. Okay. Now this I have to add. So adding this will be okay. I can add this. This is 0 degree only, right? This is angle 2.5 angle 0. So this will come out to be 2.5 will be here. So this will be 5 divided by 3 okay, cos of 120, right? Cos of minus 120 into 5 divided by 3, so it comes out to be minus 0.833, and this divided by 5 into 3 into 1.25, so this comes out to be minus 0.625. then I have my J as well, right? So 120 minus sine into 5 divided by 3, so it is minus J 1.4434 into 3 divided by 5 into 1.25, so it comes out to be plus J 1.082. okay. So my Vn equals to so this will be minus 1.4434, so this comes out to be minus J 0.36. So this minus 625 minus 0.833 2.5. okay, so this is my Vn. So if I want to convert this in basic polar format, this will be 1.1 angle will be 0.36 divided by 1.042 tan inverse, yeah, minus 19 0.06 degrees. Okay, this is the VN. Now I can simply find out IR, my IR, my IY, my IB. It's very simple, right? So IR will be what? IR will be simple this voltage minus this voltage divided by the impedance. So it's this value only, this value only, in the opposite sense, in the opposite sense. Okay, so 10 angle 0 minus 1.1 19.06 divided by 4. So already I have this value written, so I will directly convert this here, directly write this here. So this calculation will be lengthy. Okay, so this will be 10 angle 0. Like these exact question will not come in GATE, but a small concept from here, like voltage here will not be 0, current here is 0, right? So these small concepts will be asked. So that's why I'm stressing in this particular concepts, because in anywhere else no one will teach you these questions, right? In the phase no one will teach you these additional questions, but I am teaching you because I know in the next few years they can ask questions from this topic, from this area. So this will be okay, so 10 minus 1.042, so this comes out to be 8.958 minus, this is 0.36, okay, minus j, this will be plus j 0.36, this will become plus j 0.36. So this whole square plus 8.958 whole square whole under root, that is like almost 8.96 only. That imaginary portion does not make any difference. 95 angle will be what? Angle also will be very low, almost be equals to 2 degrees, right? Very low, 2.3 degrees divided by R. So 8.965 2.3 amps. Okay, so this is the IR. Similarly you can find out IY and IB. I want you to try, so please find out the answer of IY and IB and put it in the comments. Okay, put in the comments so that I can understand that you are actually watching this video and doing something by yourself. Okay, so put it in the comments what will be the value of IY and IB. So let's now come on to the fourth question. So here we have two identical resistors. Okay, so these questions are also kind of good. So we have two identical resistors are connected in series across line B and C. So I have two identical resistors. So let's say I have three lines here. Line A. Okay, let me do different colors. Line B and line C. I have three identical resistors. Sorry, three lines, and I have two identical resistors that are connected in series across line B and C. So across line B and C, I have two identical resistors that are connected in series. Okay, so this is R, this is R. It is a 400 volt system. Whenever they say three phase 400 volt, they are actually talking about the line. So the line voltage is 400 volts. Okay, what is the magnitude of the voltage between line A and the midpoint of the junction of the two resistors? So they are asking me what will be the voltage between this point and this point. So what is the voltage between this point and this point? How will I calculate the voltage between this point and this point? How will I calculate it? Okay, so what is the magnitude of the voltage connecting between midpoint of the two resistors? If I say this point is, let's say, X, right? I know the potential between A and B. I know the potential between A and B, that is VAB. And if I am able to find out this VBX, then I will be able to find out the potential VAX, correct? So I have to find out the potential VAX. If I have to find out the potential VAX, I know the potential VAB, this much potential, and if I add this additional potential plus VBX, I will get my overall potential VX. That is what they are asking, right? And they are asking the magnitude only. They are asking the magnitude only. So here I know what is VAB. VAB is 400 volt. Okay, and as it is like the phase sequence they have not mentioned. Actually, I should have mentioned the phase sequence. Phase sequence is ABC. Although I don't think it will matter, right? I don't think if you choose other phase sequence, it will come out to be same only. If phase sequence is ABC, then your VAB, line voltage VAB, if I assume it to be reference, it is 400 volt 0 degree. It is 400 volt 0 degree. Okay, that is what my VAB is equals to. That is what my VAB is equals to. Now, how do I find out this VBX? Now, I know what is the voltage at the line. Okay, I know what is VBC, right? I know what is VBC. What is VBC? VBC is the potential across these two. So, if I redraw this circuit, right, this much. Here I am applying VBC, and here this is R, this is R. So what will be the potential here and here? It will be simply VBC by 2 and VBC by 2, right? Simple potential divider, that's it. Simple potential divider. These are in series. So it's simple potential divider. So this VBX actually is equals to VBC by 2. So it is VAB plus VBC by 2. It's that simple. It's that simple. Okay. So it's VBC by 2. So what is VBC? VBC is 400 volt and it should be minus 120. Right? 400 volt minus 120. That is my VBC. So because the phase sequence is ABC, so first AB will be 0 degree, then VBC will be minus 120, then CA will be plus 120. Okay. So VCA will be plus 120. So all these have been explained in the 3-phase lecture. So I hope I am not explaining it over here again. So VCA is this. So if I rewrite this equation, my VAX is equals to VAB, that is 400 angle 0 plus VBC by 2. So it is 200 angle minus 120. Yeah, even if I change the phase sequence, it won't matter. Okay. So I have already told you just in the previous one. Okay. If I am adding one more important point, one more very important point you have to understand is that, let's say if I am adding 1 angle 0, 1 angle minus 120 plus 1 angle plus 120. It is a balanced 3-phase system, right? It will come out to be 0. So from here I can get a very important, or I can write here B. It does not matter what is the magnitude. I can get a very important relation that V angle 0 plus V angle minus 120 will come out to be minus V angle plus 120. So I will do the same thing here. Okay. So I can break this 400 into 2 parts. One of the parts will be 200 angle 0 and the other part will be 200 angle 0 plus this minus 120. So this is 200 angle 0 plus 200 angle minus 120, which is equals to minus of 200 plus 120. So it will be minus of 200 plus 120. And if there is a negative sign, I know negative sign basically means it is phase shifted by plus 180 or minus 180. So I can subtract or add 180 with the angle. So if I subtract or add 180 with the angle, what will I get? It will be 200 angle 0 plus 200. I am just inserting this negative sign inside, right? So it will be minus 60 degrees. Now, is this something familiar to you? Is this something familiar to you? This is something very, very familiar to us, right? So if you see, already have discussed, if I have two phasors, one is at, let's say here reference 200 angle 0, another one the phase difference is 60 degrees, so it's here 200 angle minus 60, so it's lagging actually, minus 60 is here. So if there is a phase difference between them of 60 degrees and magnitudes are same, so the resultant will be the angle bisector, that is 30 degrees downwards, and the magnitude will become root 3 times the previous one. So 200 root 3 angle minus 30 degrees. Okay, so that's actually very neat. Without even touching, doing any complex calculation, I'm directly able to tell what will be the voltage. It will be 200 root 3 angle minus 30. So the magnitude will be what? Magnitude, they have asked me the magnitude, it will be 200 angle root 3. This will be the answer. If you have enjoyed this concept, right, please drop a like. Please drop a like in the video, and trust me, more concepts like this will come. So without even doing any calculations, I'm directly able to write the answer. Okay, so that's the trick basically. Of course, you can solve this, right? You can solve this, you can do the calculation, you'll get back the same result. But in exam, this sometimes helps you to save time, because you don't have to go to the calculator. With hand calculations, you are able to solve this question. So that's why knowing all this is also very, very important. Okay, so I hope this question is clear, and I'm expecting, like, this question have not been asked yet, but I'm expecting a similar kind of question to be asked in 3 phase, and trust me, you guys will be the first one to be able to solve that question. So let's now solve the last question of today's lecture. So this is again a gate P by Q, which was asked in 2007, gate EE 2007. Okay, so a source is supplying a load through a two-phase balanced three-phase supply. So whenever there is a two-phase balanced three-phase supply, first thing what you should know is the phase difference between two voltages VA and VB, right? VA will be V angle 0 for a two-phase. I'm talking about two-phase balance system, and VB will be only for two-phase balance system. It will be V angle 90. Otherwise, in all other phases, the angle phase difference will be 360 divided by M, where M is the number of phase. Okay, so here M has to be greater than or equals to 3, and it is number of phases. Okay, it is number of phases. So I hope that is clear now. Okay, so they are asking me, like, these are the voltages, these are the currents basically. They are asking me the total instantaneous power flowing from the source to load. What is the total instantaneous power that the source is supplying? So what is the instantaneous power formula? Instantaneous power formula is V of t into I of t, right? That is the formula for instantaneous power. Now here I have two phases, phase A and phase B. So it will be equals to VA of t into IA of t plus VB of t into IB of t. So VA of t already I know this value, VAN they have given me, IA also they have given me. I will multiply these two, so it will come out to be 220 sine 100 pi t and 10 sine 100 pi t. Then we have VBN into IB. So VBN, so VBN is 220 into cos 100 by t. and this is 10 cos 100 pi t. The current is 10 cos 100 pi t. So 10 cos 100 pi t. Okay, so this will be basically, what is this? 2200 sine square 100 pi t. So 2200 sine square 100 pi t, and this is actually 2200 cos square 100 pi t. So 2200 cos square 100 pi t, and actually conveniently, very conveniently, it comes out that I can take common 2200 sine square omega t plus cos square omega t is 1. So actually our instantaneous power is constant. Instantaneous power comes out to be a constant value, that is 2200 watts. So this will be your answer. Okay, it comes out to be a constant value 2200 watts. So this is also a very good question. Few students might be scared, might get scared by seeing a two-phase system, by hearing the word power. So that's why I took this question to clear the confusion and doubt. So with this, three-phase is completely over. Now we will come to the next topic, that is also very most important topic for power systems, that is per unit systems. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. So today we will be discussing about the lecture 2 of power system analysis. So today we will be learning single line diagram. What is a single line diagram? Why is single line diagram used? And also we will be discussing about the symbolic representation of different devices like transformers, generators, motors. Okay, what is the symbolic and per phase equivalent of different devices? And at the end, the most important part, we will be doing the per unit analysis, and why is per unit analysis required. So let's start with this diagram. Is this diagram intimidating to you? If it is yes, that means we need a alternative way to represent our circuit, because a power system is a very complex circuit. Complex circuit means there are so many things. First of all, it is three phase. Then there are transformers before the transmission line, which will step up the voltage. Why I need to step up the voltage? To reduce the copper loss, because I know the transformer does not change the power. Power is constant on the primary and the secondary. What it does, it changes the voltage level and the current level. So I know the copper loss is related to I square R, right? Is related to current. So I know power is constant, so VI is constant. So if I somehow increase the voltage very high, current will reduce. If the current reduces, then this power loss reduces. So that is the requirement that we need. That's why transformers are connected just after the generators and just before the load, because then again we have to step down the voltage, because load does not take very high voltage. Load takes 230 volts, right? And we transmit around, let's say, 11 kilovolt. So generator also generates at around 440 volts, something like that. But we step it up to 11 kV so that the current reduces. So I reduces largely. So if I reduces, then there will be huge copper losses here. If there are huge copper losses here, if I reduces, then the copper losses will be lowered, and ultimately my load also does not take very high voltage, right? It takes 230 volts. So your phone, all those things, when you charge the devices, it operates at low voltage. It cannot operate at 11 kilovolt or even 132 kilovolt. So then I step it down. So it's actually not 11, it can be 132 kilovolt as well. Right? Generally we transmit at very high voltage, 132 kilovolt. Then I step it down here to around 230 volts, and then I feed it to the load. So that's why I need three-phase transformers before the transmission line and after the transmission line, and everything is in three phase. So it is very congested, very congested, right? So we have to simplify our circuit diagram, because every time I will not draw the circuit diagram. When I will try to solve what is the current here, I will not draw the circuit diagram every time. So what we do, draw a notation that is single line diagram. So this whole generator, right, three-phase generator, gets converted here. Very simple. We know power system, we operate in three phase. That is already understood. So we know this generator is in three phase. This symbol tells me that it is star connected, because here the symbol is of star, and the neutral is grounded. I will discuss about grounding. So neutral is grounded. So this side neutral, if you see, it is grounded. Yes, correct. Right, then I have a transformer which is again star to star. So here I also have star, this is also a star. So it is star to star. It can be delta as well. It can be delta as well. So I will connect the transformers in delta, but here I have connected the transformers in star. So I am writing star to star, and the neutrals are counted, as you can see. So I hope you remember three-phase transformer chapter, how to connect in delta. All those things have been covered over there. So it represents a transformer. Let's say I'm generating at 11 kilovolt, and then I'm stepping it up to 132 kilovolt. And this is a three-phase transformer, star to star, where neutral is grounded. Okay. Then I have three-phase transformer here. Again, it is star to star. Again, neutral is grounded here. Neutral is grounded, right? Neutral is grounded. Now, this is 132 kV, 11 kilovolt, and it is supplying a motor. If you see here, I have not drawn the load here. It can supply a motor. So this is a motor. It is not a generator again. They will tell you whether it is a generator or motor. It is a motor. Motor loads are defined like this because motor has back EMF, right? Motor has back EMF EB. So that's why they are defined like as if it's a voltage source. So it as if it's a voltage source. Okay, but it's a load. It is taking power, not delivering power. It is absorbing power. And I have a load. It can be a static load. So this kind of loads are called rotating load, or dynamic loads, and this kind of loads are called static loads. Okay, like RLC, those kind of loads. Okay, so things is so simpler. It is so simple to draw, right? Than this. It will take, like, it took me around 10 to 10 minutes to draw this. Okay, and it will take me around 1 minute to draw this. And I will in rough, I will not even draw all this, right? I will draw in rough. So that's why single line diagram is very, very important. Why is it called single line diagram? Because here a single line represents everything. So doing the analysis is very simple. So this is the SLD. In short, this is called as SLD. Single line diagram. Okay, it is called SLD. So this is my single line diagram, basically simplified representation of three-phase systems using a single line. Shows electrical connections of generators, transformers, loads, circuit breakers. It reduces the complexity, highlights the power flow, like how the power helps in power flow analysis. So we will be easily able to analyze which path it is following. So we will see that when we will do the fault analysis. Okay, so all this, it helps, right? So the key point here is all phases must be identical. If they're not identical, then I will not be able to simply convert this here. Then I have to draw the three-phase circuit only. I will not be able to draw the per phase equivalent. We used to draw the per phase equivalent because we knew our circuit was balanced. But if the circuit goes imbalanced, then it is difficult. Then I cannot simply draw the per phase equivalent. So we will understand this when we will discuss about unsymmetrical faults. Voltage, current, magnitudes will come same. Magnitude will be same, right? If it's a balanced system, just the phase will be shifted by 120 degrees. Phase will be shifted by 120 degrees. Bus bar. Okay, so another kind of thing there is, this is called as the bus bar. These are called as bus bar. It's just like an infinite bus. We discussed, right? It's infinite bus. So bus bars are those points where electrically other equipments will be connected to take out the voltage. That's it. Bus bar is just a straight line in the single line diagram where we take the voltage. So here voltage will be constant. It's just like infinite voltage. Okay, so yeah, bus bar is the conducting bar with bolted connection. So here I can take out, like, in reality the diagram of bus bar is somewhat like this. I will show you where is the, if I have the diagram, a diagram of bus bar is here. So this is the bus bar basically where we take out the wires, and here we have bolts here where we connect the wires. Okay, so simply we just take out the wires and this voltage will be constant potential, constant voltage. Okay, this voltage will be constant voltage. So yeah, I hope you have understood that point. Now yeah, so we will discuss about few grounding systems. So first one is solid grounding. So if it is said that the device is solidly grounded, basically it means that neutral is shorted to ground. The neutral is shorted to ground. That is what solid grounding means. Sometimes it is also told as it is bolted to ground. Bolted to ground. That also basically means simply it is shorted. Circuit analysis point of view, it basically means it is simply shorted. Okay, that is what it means. Then we have resistance grounding. So resistance grounding means basically we have a resistor, right, which will connect to the neutral. So now the neutral will directly not be connected to ground. There will be resistance in the path. It is another kind of grounding is called reactance grounding, where the neutral will be. So this is my neutral basically. These are my neutral, where the neutral will be connected to ground via a reactor. Okay, we will understand the advantages and disadvantages of connecting reactance and resistance. So we will see this when we will do the fault analysis. So bus bar I have already explained. Bus bar is just a electrical node that serves as a common junction point in the power system. So we take out incoming lines will come here and the outgoing lines will go out. We will take out wires and connect the wires that are incoming. That's it. That is what bus bar is. It's just like acts as a feeder to the outgoing lines and it acts as a sink to the incoming lines. That's it. Okay. So typically in single line diagram they are shown horizontally. If you see, it is just a horizontal straight line. That is what my single line diagram is. Okay. So let me. This is not required here. Yeah. So that is bus bar. So I'm just discussing about the terminologies here. Now let's discuss about the symbolic representation. Okay, what are the different symbolic representation of different devices? So first one is synchronous generator. So synchronous generator is already we have discussed this in our synchronous machine chapter, that we will have a voltage source here, EG. A voltage will be developed. We will have the synchronous reactance and the armature resistance. Generally, most cases, armature resistance is neglected. So we only have synchronous reactance, and don't worry, the synchronous reactance also has a very good story which we will discuss. Okay, very important. If you like, we will understand this in the symmetrical fault analysis. Very important. So simply a per phase equivalent of a synchronous generator will be this EG angle delta. Here I will have terminal voltage and I will have the synchronous reactance. And the single line diagram will be somewhat like this. We have used this actually in machines, but there I have not told you that this actually is called a single line diagram. Okay, but now you know that it is called a single line diagram. So nothing to explain over here. It's just the symbolic representation. Now why is the resistance neglected? That you might have a question. Why, sir, is the resistance neglected? So resistance is neglected because first of all, calculations will be very complex, right? Because if it is purely imaginary, calculation becomes very easy. If there is some real part, again calculations will be complex. So to simplify the calculations, we neglect the resistance. Okay, so simplify, actually it should be to simplify the short circuit characteristics. So how is it possible? Simplify. So let's say if your generator, this circuit is short circuited, right? It was suddenly delivering to a load. Okay, it was delivering to a load and suddenly it is short circuited. Okay, what will be the short circuit current here? Short circuit current will be EG angle delta divided by RA plus JXS. Now if you see, the calculation is very difficult. If I neglect the resistance, and then I do the short circuit, okay, so this will be short circuit current here. ISC will be equals to EG angle delta divided by JXS. So this will be EG delta minus 90. Okay, very simple, and divide by XS. So calculation becomes very simple here, right, in the second case. That is why. And also during transient stability we'll consider it. We'll consider because If only excess is there, there will not be any transient, right? So during transient stability we will consider it, but sometimes we want to only do the steady state analysis. So for steady state analysis we can neglect the armature resistance. Okay, so practically excess generally practically will be very very large, and that's why you can simply neglect the armature resistance. It will not make much difference in the calculation. Okay, so that was about the why resistance is neglected. Now let's discuss the symbolic notation for transformers. So transformers, we know already a single phase transformer we have. The symbolic notation is this. Single line diagram will be simply this. This will be the single line diagram, that's it. And for a transformer, the magnetizing branch is neglected because, again, for simplifying the calculation. Simplifying calculation. Why? During fault and in normal operation as well, the magnetizing current is flowing in the shunt branch, and I have a current that is going in the load or the short circuit current. So IL will be much larger than IM, much larger than IM. So simply IM we can neglect. Okay, IM we can neglect. I hope you have understood this point. So I hope that is clear now. That is over. Now, yeah. So how do I model my transformer? So transformer will have its like winding resistance and leakage reactance Z1 on the primary side and Z2. So generally what we do is we actually define our overall leakage reactance and the winding resistance on one side. Okay, either it will be on the primary or it will be on the secondary. Why? We will understand this in the uh, per unit analysis of transformers. Okay, just in the coming slides. Now I hope you remember the referring. What was the formula for referring? So if I am referring my Z2 to the primary side, it will be what? The side which I am referring to, that voltage level or the turns ratio divided by the side from which I am referring to, that is V2 whole square into Z2, right? This will be my Z2 dash, and Z1 dash. Z1 dash will be what? Side to which I am referring to, that is V2, side from which I am referring V1 whole square into Z1. So I'm just revising all these concepts. This has been taught in transformers already. So I'm just revising all this. Okay. So that's how you model the transformers. Now let's discuss about transmission line. So transmission line in single line diagram will be shown like this. It might have, like, we will assume like they will give you some either impedance of transmission line here, and we will connect this impedance of transmission line will be just like here, just a series impedance. Okay, but actually we model with nominal pi and nominal t, that we will learn while PSA 1. While studying the PSA 1, there we learn how we model our transmission lines. But in case of fault analysis, simply either you will draw a straight line, assume that there is no transmission line, we neglect the shunt branches. Again, we will ignore the shunt branches because the current here will be much higher than the shunt branches. And or either you neglect the whole transmission line impedance, or they will give you some transmission line impedance, and you will represent it as a series circuit here. That's it. That's it. Okay, you will neglect the shunt branches. So here if I neglect the shunt branches, why I neglect the shunt branches? Again the same reason, right? Same reason, because current here will be much, like this series current will be much larger than the shunt current, so it won't make much of a difference in the calculations. So I series much larger than the shunt current. Okay, so yeah, I hope you have understood this point. Now now let's come to synchronous and induction motor. So these are loads, but these are called as rotating loads or dynamic loads. Why are they called dynamic loads? Because their parts are rotating. If I have a fan, it's a rotating part, right? So that's why it is called a rotating load. For a synchronous motor, it's very easy, right? Because we have to model it with a voltage source, because we excite the DC field. So that's why we model with a voltage source for a synchronous motor. Okay. For an induction motor, there is no source. There is no voltage source. Why there is no voltage source? Because it works on the principle of induction. So it's just like a transformer. The equivalent circuit of an induction motor is just like a transformer, already has been discussed, with its secondary being shorted, with its rotor being shorted. So this is the rotor side. I hope all this you remember, rotor side, and this was the stator side, right? So in single line diagram, how will I represent? In single line diagram, the synchronous motor will be represented like this. Where did it go? Yeah. So I have two kinds of load. One is motor load, okay. Another one is static load. So synchronous motor will be, in a single line diagram, will be basically drawn like this, okay. And in case of a induction motor, it will be just drawn like a static load. It will not be drawn like a voltage source, because this represents a voltage source that is present in the synchronous motor, but induction does not have a voltage source. So simply a single line diagram for an induction motor and a normal static load, that is Rx, right, will be same. This will be same. So you will not be able to differentiate whether it is a rotating load or static load. Okay, I hope that point is clear. Okay, yeah. So now we will discuss about the per unit analysis and why it is very, very important. So let me bring the previous single line diagram. If I bring the previous single line diagram, this was the previous single line diagram, right? So here, if I say, can you tell me the current throughout here, right? If I say current here, let's say is I1, will the current be here be same? No, because there is a discontinuity. There is a discontinuity because the voltage levels have changed, so the current levels also will change, right? Because current will be higher here, current will be lower here. So if I am calculating current here, then again I need to recalculate the current here. Of course, it will be dependent on the turns ratio, but again I need to recalculate. Again, this is a step down transformer. Current here will be higher, current here will be lower. Again, I need to do the recalculation. So there is discontinuity in the circuit. Okay, and each time I have to find out, I have to do complex calculation. If I convert everything into a single base and then I compare with respect to that base, then the circuit will be much simplified. So per unit system is nothing but normalization. It is same as normalization. If you don't know what is normalization, just look it up. Okay, normalization. It is similar to normalization, right? So what is the formula? The formula for per unit is very simple. It is the actual upon the base value. Whatever base you decide, actual. So let's say, if you say that if I have a voltage that is 5 volts and your base for the voltage is 10 volts, then what will be this VPU in per unit? It will be actual upon base, that is 5 upon 10, that is 0.5. Now per unit value can be higher than 1 or lower than 1. There is a misconception that it has to be always lower than 1. No, because your voltage can be 15 volts. Your base, you have assumed it to be 10 volts, that's fine. So what will be your per unit VPU here? It will be 1.5 PU. and it is greater than 1, there is no problem. No problem at all. There is no problem at all with that. Okay, there is no problem at all with that. So I hope you have understood this point. Now, one more thing is per unit quantity is unitless. Unitless. It is unitless. So you will divide the base for that particular quantity. So if I am having a voltage, I will divide by the voltage base. If I am having a current, I will not divide by voltage, right? If I am having a current of 5 amperes and the base for it will be given to you, we will choose the base. We will understand which ones to choose the base. So I base will be 10 ampere. Then your IPU will be equals to 0.5. Then it is correct. You cannot just divide by any base, right? You have to divide by the base of its own quantity. So 5 upon 10 will be 0.5. Again, it is unitless. So this is the basic thing about per unit. Why we are using per unit? You will see that here, right? It is much simpler, and the impedance also is much simpler, because in case of transformers we have to refer to left or right, but if I use per unit, the refer will be gone. This transformer will, this discontinuity will be totally gone. How this will be gone, we'll understand that while the derivation. Okay, so it helps removing the discontinuities. Okay, so these are the like advantages of per unit. Let's do a very simple like question, just a basic introduction to per unit. And like these are the differences between absolute means actual value, absolute unit scale, and per unit. You can go through the difference. You can read. Basically the number of equations will be much higher. So if I rewrite this is the single line diagram, right? If I show you the actual three phase diagram, here the equations are much bigger, but in per unit equations will become much simpler. Okay, you only need one equation using the single line diagram. You don't have to think about the transformer up voltage, transformer step down voltage, all those things you can ignore, because the transformer gets converted to a isolation transformer, that is 1:1 transformer in per unit system. How, why, we will see that. Okay, so the computational complexity reduces. It is applicable in power system modeling, and whenever we are doing network theory based analysis, then we will use our actual analysis. Okay, so the discontinuities are removed. How it is removed, we will understand that. So let's first solve a question, very basic question, and through this we will understand it does not matter whatever base I choose, the answer will come out to be same. So per unit is like a universal method. Okay, so let's start off. Basically, let's assume that I'm choosing any random base. Let's say first I'm choose, you have to choose two base at least, and the other quantities can be derived. How? So let me choose a voltage base, V base, to be 5 volts. Generally it is the rating of the machine, 5 volts, and let me choose the MVA base, that is 10 volt ampere. Okay, or let me choose this a bit higher, 50 volt ampere. Anyways, you can choose any base, it does not matter. So they're asking what is the current and power dissipated in the resistor in per unit method. Using the per unit method, I have to find out. So this is the case one where my base is this. Okay, this is my V base and this is my S base, V base and S base. Okay, so now I have to find out the current in per unit. Can you tell me what will be the current in per unit? So what will be I base? So I know one formula, right? I know S equals to V into I. So these actually relation will be valid in both the actual quantity and in the per unit. In per unit also this will be valid. So I can write SPU will be equals to VPU into IPU, as well as S base will be equals to V base into I base. So both these equations are totally valid. Okay, so I will use this one to calculate my I base. What is my I base? So I base I base will be equals to this S base upon V base. So it is 10 ampere. Now what is the uh, like if I want to write what is the actual current? The actual current I will be what? Voltage upon resistance, that is 5 by 2, which is equals to 2.5 ampere. So what is IPU? IPU is actually equals to 2.5 actual upon the base quantity, that is 10. So it is 0.25 pu. This is what my IPU is. Okay, it is clear. Now one more relation I can write. What is the power relation? It is VI cos phi, or VI is what? S. So it is S times cos phi. It is S times cos phi. So it is S cos phi. Now can I write this in per unit? So cos phi is what? It is always 1, right? Because it is a resistive load. It is a purely resistive load. So I can write power is equal to S for a purely resistive load if my power factor is 1. So I can directly say I know what is my VPU. So voltage across the resistor. What is VPU? VPU will be V actual. Actual voltage is 5 and the base voltage I have assumed to be 5 volts only. So it is 1 only. So 5 upon 5, it is 1 pu. I know what is IPU. I have just calculated the value. IPU is equals to 0.25. So what will be my power? Power will be simply voltage into current, right? So it will be 0.25 into 1, that is 0.25. It is same as S in pu. Now what is the actual power consumed? What is the actual power consumed? So actual power consumed will be what? Actual power consumed will be this multiplied by its base. So I know power is equals to apparent power, active power is equals to apparent power. So the base also is same only, value of the base, that is 50 VA, 50 only. So I can directly multiply the P actual value, that will be per unit quantity, into the base, that is 50. So it will come out to be 2.5 into 5, that is 12.5 watts. Now I know you already, like you have already solved this question and you know it is 12.5 watts. It's just like a, I think class 10 or class 9 question. Okay, that is not the factor here. So we are getting 12.5 watts. Are we expecting that? Yes, it is V square by R. So 25 by 2, it is 12.5 ampere, 12.5 watts. Now let's choose a different base. Let me choose a different base. If I choose a different base, any random base, okay. So let me choose R base, that is 10 ohms, and let me choose a current base, I base, that is 10 amperes. Okay, now let me solve it again. So I have to derive the other base quantities. So I know voltage is equals to I into R. So my V base will be equals to I base into R base, which is 10 times 10, which is 100 volts. So V base comes out to be 100 volts. Okay. What about the S base? S base is very simple. It is V base into I base. So V base will be 100 volt into I base. I base will be 10 amperes. So it is almost 1000 volt amperes. Okay, 1000 volt amperes. So S base I have got V base. So can I write the power again in per unit? So again, what will be VPU now? So I know what is the current, actual value of the current. Actual value of the current will be the voltage upon the resistance, that is 2.5. So I know what is IPU. IPU will be actual upon the base. So it is 0.25 pu. But what about the VPU now. So what is the voltage across the resistor VPU? VPU will be the actual voltage, that is 5 volts, upon the base voltage. What is the base voltage here? Base voltage here is 100 volts. So here lies a confusion. So I get per unit to be 0.05 pu. But sir, you just said that per unit values will be same. But here, sir, I am getting it is 1 pu. Here, sir, I am getting it is, where did it go? Just hold on a second. 0.05 pu. How they are same then, sir? They are different, right? Remember, if you are changing the base, the per unit values will change, but the actual quantities will remain same. Okay, very important point. This I know you already know, but I know many students have this confusion, so wanted to clear the confusion right now itself. Okay, so those who already know, they can skip this portion. So actual quantity, actual value remains same, but per unit values might change if base is changed. So like then sir, what is same here? Actual value. So let me find out the power. Power will be what? VPU into IPU. So VPU is 0.05 into IPU. IPU is 0.25. 0.25. So this is my PPU. Now actual value of power. What will be the actual value of power? It is per unit into the base. Base, S base and P base will be same because it is a resistive load. So apparent power and active power are same. So it is V base into I base, that is 10 raised to power 3. So basically this will be 0.05 into 0.25 into 10 cube. So this will be 5 into 2.5, so it is 12.5. So I hope you are observing that actual value is not changing. Still I am getting 12.5 watts here, still I am getting 12.5 watts. I just taken a very simple example to show you, but in a bigger circuit this will be complex. But what should be in your mind? In your mind it should be there that actual value will remain same no matter what base you choose, does not matter. Per unit values will change because the base has changed, right? Actual values will be constant. It is just a circuit analysis, so that will remain constant. Now the thing is, I took this question to clear this confusion that we can choose any base as we like. So we can choose any base for two quantities. Then what we'll do? Then derive the base, derive the other, derive the base for other quantities. Okay. Generally the trend is we choose voltage and the rating, MVA rating, volt ampere rating as the base. Okay, and derive the other quantities because they will be same. So here these are the quantities, right? All these are the quantities. So what we'll do, we'll choose two base, that is voltage and S base, voltage and the MVA rating, base apparent power, and we can derive all this, right? I base will be what? For a three phase system, I discussed for a single phase system. For a three phase system, we know your MVA rating is equals to root 3 into VL into IL. So I base will be S base divided by root 3 base. So V base is the line voltage for 3-phase system and your I base is the line current. Remember this. Okay, then only this relation will be followed. Otherwise you have to divide by 3, because I know 3 V base into I base is equals to S base, or root 3 into VLIL is equals to S base. Anything will work. But remember, whether root 3 will come a 3 depends on the type of the voltage and current that you are writing down in the actual expression. Okay. So yeah, we will choose voltage and our apparent power as the base rating, and then we will derive all these quantities. So you can use the same simple formulas, simple whatever formula we know, and we can derive any quantities that we like. Okay, so let's take the example of a simple series R L circuit or any impedance, right? If I have a circuit like this, series R circuit, R plus Jx, right? This circuit is there. How will I write this in base quantities? So for this, right, we know this is my impedance, Z equals to R plus Jx. So I will divide this by the Z base. So if I divide both sides by Z base, I will get my per unit values. So this will be ZPU will be equals to R by Z base. R by Z base so what is this? This is RPU and this is XPU. Okay, this is RPU and this is XPU. Okay, so that's how we derive. So how do I find out Z base? What will be my Z base? How do I derive my Z base? So Z base is very simple, right? So I know what will be my I base. I base will be root 3, sorry, S base upon root 3 into V base, and I know voltage upon current, that is V base upon I base, will be my Z base, because voltage upon current is impedance. So from there I can easily find out the base impedance. Or what we do, we can directly derive this value as well. This is my I base, right? So if I put here I base, what will I get? If I put here my I base, what will I get? So my Z base becomes V base upon S base upon root 3 into V base. So this will be equals to here V base whole square divided by S root 3 into V base whole square divided by S base. So this is the formula for Z base. If I replace here Z base, right, I will get my RPU and ZPU formula. So this is one of the formula for Z base. So do you need to remember it? No, you don't need to remember it. Just understanding the things is enough. Just understanding what formulas are there. Now, one more important fact to note here is that this, right, this value are line voltages and line currents. Line voltage and this was line current. So remember all this, let's assume like it's a star connected system. So one mistake I have made. So if it's a star connected system, right, this is my impedance here. This is my impedance. So your impedance actually Z equals to V phase divided by the current of the phase, right? But in star, I know the line current is same as the phase current, but the voltage, right, is divided by root 3. So actually this is the formula for Z. I have made a mistake. This is the formula for Z. Okay. So here this will be B upon IB here, but remember these are line, these are phase quantities, right, phase quantities. But here I have to write in but this okay, sorry, this VB was actually line value, right? This VB, whatever we had discussed, is the line voltage. VB, we have assumed that VB is the base line voltage, right? I have already told you here. If I see, yeah, this is a line voltage. So V base is the line voltage. So it is exactly not equals to ZB. That's my bad. So VB divide by root 3, because it is the it has to be phase quantity. That's why I will divide by root 3. Divide by root 3 into IB will be my Z base. So now it is correct. So another extra additional root 3 will come, and here root 3 will get cancelled, because I know you have mugged up the formula about the Z base. This is the formula for Z base, right? I know you have mugged this up, but an extra root 3 was coming. How it is coming? Okay. So everything is, I hope, clear now. It does not matter. You are choosing the system to be star here. If you choose delta, it will not matter. Then the line current will be 1 by root 3, sorry, phase current will be 1 by root 3 times the line current. Then all this I base also will change. So all these things will change. Automatically your Z base will be constant. It will always be V base whole square divided by S base, no matter what. It will always be the case. Okay, don't worry. So that is what my Z base is. So we derive with voltage and the S base, we can derive any base. Impedance we have derived. Okay. Power is simply, power base is S base only. So for all this, the base is S base. Okay. For these three quantities, the base is Z base. For this, it is V base. For this, I can derive it. It will be simply, if it's a three-phase system, it will be S base upon root 3 into V base. Okay. Now for this, it is the inverse. So it will be 1 by Z base, because conductance is the inverse, susceptance is the inverse, and your admittance is the inverse. That's why the base also is the inverse. Okay. I hope it is clear how to find out the bases for any quantities, and then simply you can write the per unit values. Now what about the power factor angle or theta z? Does your power factor is already in per unit or it is not in per unit? Okay, we can discuss about that. So already I discussed that your power, reactive power, all those things can be derived with S base, right? How? So I know S is equals to active power plus the reactive power. Okay, if I divide by S base, I will get my per unit power. This will be SPU. This will be equals to P divided by S base plus Q divided by S base. So here this is PPU, this is QPU. Okay, so I hope now it is clear. The base for reactive power is also same, the base for active power is also same, that is S base only. Okay, now what about the power factor? So I know one thing, if I draw the power triangle, right, if I draw the power triangle, this is my active power, this is my reactive power JQ. I'm assuming it to be lagging, it can be leading as well, and this is my apparent power S, and this is my theta. Okay, so if I write the relation in actual quantity, tan theta will be Q upon P. If I want to write the same relation in per unit, tan theta per unit, it will be simply Q per unit by P per unit. Now can I convert this equation to this one? Yes. How? Just divide both sides, numerator and the denominator, by S base. So this will be Q divided by S base, this will be P divided by S base. So this one gets converted into QPU, this one gets converted into PPU. So automatically I get back this value. That means basically your tan theta is equals to tan theta pu. So basically already your angle is already in the base format because it is already unitless, right? This is unitless. So your power factor is also already in per unit format. Your power factor is already per unit. You don't need to convert it. You don't need to convert the power factor to per unit, right? Because it is already in per unit format because it is already unitless. There is no that. What is the unit of power factor? It is unitless, right? So your power factor and other quantities are already represented in per unit representation. You don't have to modify. So power factor is already represented in per unit format. No need to modify. Okay, so that is the thing over here. I hope you have understood this point. Very important point regarding power factor. It is already a dimensionless quantity. Okay, what about admittance? So admittance I can quickly discuss. So if I have like a parallel component here, its conductance is G, its susceptance is B, right? So I can write the overall admittance will be what, G plus JB, right? Okay, and then I can simply divide by the base. That is what is the base? The base is simply 1 by Z base, right? So this will be G upon 1 by ZB plus J upon B 1 by ZB. I'm just showing you how can I convert each quantities into their per unit equivalent. Okay, I hope it is clear now. So the base for admittance is simply 1 by Z base. The base for admittance is simply 1 by Z base. Okay. So now let's basically discuss about star and delta. What will happen in star and delta to per unit values? Okay. So if I have a star connection, how will I derive? Right. That is the important portion here. So always, ultimately, our aim will be to have a V base and I base. So our V base generally we choose the V base to be the line voltage, the rated line voltage. Okay. So if V base is the rated line voltage, okay, if V base is the rated line voltage, then can you tell me what is the per unit phase voltage? What is the per unit phase voltage? Will it be, so here this will be what is the per unit line voltage? So per unit line voltage, right, VL per unit will be this VL actual value upon the base value. Okay, so let me take few numbers. So let me assume that my line voltage here is 10 line voltage is 10 volts. So I can easily find out what is my phase voltage, and the base voltage, right, assumed to be 20 volts. That is in the line. Okay. So what will be the VLPU? So VLPU comes out to be actual, that is 10, upon the base, that is 10 upon 20, that is 0.5 pu. Now what will be the phase voltage per unit? So what is V phase per unit? Now here very interesting thing will come. Please listen to me very carefully. What will be V phase per unit? V phase per unit is equals to the actual phase voltage divided by the base voltage, but this should be the phase base voltage, right? Because I have to divide by the base of that particular quantity, divide by the base of that particular quantity. So base for this particular quantity was the line voltage here, but base for this particular quantity will be different. Base will change depending on the quantity. So this is the phase voltage, so I have to divide by the phase base voltage. So I know the line base voltage. What will be the phase base voltage for a star system? It will be 20 by root 3. So here 20 by root 3 will come. And what will be the phase voltage for this system? Line voltage is 10 volts. What is the phase? It will be 10 divided by root 3. So this also will be 10 divided by root 3. So what is happening here? Root 3 is getting cancelled. I am getting back the same result, 1 by 2, that is 0.5 pu. So what is the important conclusion? The conclusion is that it does not matter whether your system will be in star or delta. I will show you for delta as well. That it will be same. For delta as well it will be same. There will not be any difference. Okay. So I can show you that. So yeah, let me show you for delta. So if I have a delta here, don't worry, I will derive the expression for the resistance, per unit resistance in delta as well. Don't worry about that. So again the same thing, that this is my, let's say this is my V line and this is my V phase, but this time the current has changed. Like here the current is same, line current and phase current is same, so I am not deriving the current. But here current has changed, so this is the line current and this is the phase current. Okay, so let's assume a thing. Let's assume that the line current will be 10 amperes, and what will be the phase current then? If it is a balanced system, actual phase current will be 10 by root 3. Okay, and let me assume again the same thing, that the base of the line current, I can choose any base, will be 20 amperes. So I will do the same thing, right? I will write down the per unit value for the line current, IL per unit. So this will be equals to actual upon the base of that particular quantity. So this is I base measured on the line, okay, not on the phase. So 10 upon 20, so it is 0.5 pu. Okay, 0.5 per unit. What about the I phase per unit? I phase per unit, I phase is 10 by root 3 actual value. What is the base? Base also will be divided by root 3 only. So this will not be 20, this will be 20 divided by root 3. So it becomes same only, 0.5 pu. So that is the advantage. That is why I have told you that it is unified. So it does not matter whether it is star connected or delta connected. It does not matter. In per unit, they come out to be same. So per unit values do not depend on type of connection. So I previously told you that per unit values can change if the base has been changed, right? That was for a system. This whole thing, whatever we discussed, this was for a whole system. For a single system, if I am changing the base, then of course the per unit value will change. Actual value will be same. This is for a whole system, right? But here what I am doing, I am not changing the base. The system is constant. I am not changing the base, but I am changing the connection. So it does not matter whether it is star connected or delta connected. The per unit value will be same no matter what. So that is what the advantage. That is the advantage. If you want to connect this in star, you can. If you know the per unit, you can convert it into equivalent star. I will show you. Don't worry, I will show you that, and delta as well. So per unit values do not change depending on the connection type, right? What is the advantage? The single line diagram, if I just write down the per unit expression, is done. I don't have to worry whether it is star connected or delta connected. So connection type, I don't have to worry. So per unit removes this dependency on the type of connection. Okay, but if the per unit value is given, you will not directly able to say whether it is star or delta connected. You are blind, right? So I hope these points are clear by you. These points are clear. Now, few more relations I wanted to say here. Few more relations, like if you have been given the single phase power, so then what will be the three phase power? So three phase power will be 3 into single phase power. Okay, so your base of the three phase power will be 3 into S base of the single phase power. So yeah, this is one of the formula, and from there you can easily find out what is P and I, all those things. So whatever relation we have in normal equation, normal electrical equation, everything will be followed in per unit. So this also will be followed. Okay, in per unit, the concept of three phase and single phase is also gone. In per unit, the concept of three phase and single phase is also gone. Why? Because let's say if I have a single phase load, it consumes a power of S, right? S actual, right? Single phase. So what will be the per unit value? So SPU will be S actual single phase divided by S single phase base. Okay, then three phase load. Let us assume it's a balanced three phase load which consumes single phase. In a single phase, it consumes S actual single phase, same as, right? So what will be the three phase actual? Three phase actual power will be what? Will be 3 times this, as it is a balanced load. So here, what is the per unit value? It is 3 times S actual times single phase divided by, now what is the base? Base also has also changed. It is a three phase load, so base also will be changed. So it will be 3 times S single phase base. So one thing you are observing, that this is same. So it does not matter if it is single phase or if it's three phase or if it's five phase, our per unit value remains same, just like star delta. So there is no concept of connection type in per unit. There is no concept of three phase or single phase. Like they will tell you that it's a three phase system. If you want to convert back your system into three phase, you have to just multiply this SPU with the three phase power. If it's a single phase system, then you will multiply your SPU with the single phase base. Okay, base value has changed, that's why the per unit remains same, as the base value has changed. So here also base value automatically change. Okay, base value are automatically change. So yeah, I hope it is clear to you. So again, you're like this, right? One more important point, this you will learn later in PSA 1. We will discuss about this in PSA 1. Okay, there is a one parameter named as, like, this is a pi network, and this pi network has a parameter named A, transmission line parameter, ABCD parameter named A, where A is equals to 1 plus Z into Y. Okay, this is derived in the ABCD parameters in the PSA 1. Now, one thing we know, this will be actually same as this one. Okay, so okay, let me not write this in per unit, let me write this in actual values. So okay, let me show you this. Let me draw the two equivalent circuits. So let's say one is the actual one, this is the actual z actual, z, y, all these are actual values, pi network, and this is the per unit values, respective per unit values. So this a, right, I can derive it in terms of pu as well. How? This will be used in PSA 1. If you are not understanding, you can ignore this discussion. Okay, so I know what is my z. So this is the actual value, this is the actual value. So I know the actual value, so can I write this? So what will be zpu? Zpu will be z actual divided by z base. And what will be ypu? Ypu will be y actual upon y base, that is 1 by z base, right? So if I multiply, so basically this is zy actual product. So what is my z actual? So my z actual, just hold on, my z actual is equals to zpu into z base, and my y actual is equals to ypu into 1 by z base. Okay, so yeah, zpu into ypu. So z, like your if I multiply these two values here, what will I get? This z base and 1 by z base will get cancelled. It will be zpu into ypu. So ultimately your a, right, actually is equals to 1 plus zy in per unit. So both of these are same. So your a, I can directly write in terms of per unit values instead of actual. That will be useful in transmission line when we will study in power system analysis 1. Okay, I hope that is clear. Now let's come back to the star and delta format. So if I want to represent my impedance in star and delta in per unit, what will be the value? In per unit, what will be the value? So how can I define my impedance, right? So here, what will be the zpu? If you have been given the V base and S base, remember all, like this is line voltage and this is a three-phase power. Okay, I hope it is clear. So what will be your I base? I base I can derive will be equals to S base divided by root 3 into V base. Okay, so this is my I base, right? Remember it is a line current, it is a line current. So if I want to write this Z in terms of per unit, what will I write? So what will be my Z base? Z base will be your, remember it is phase voltage upon phase current. Now for delta I will write for star later on. For delta the Z base will be something different. Okay, so here in delta phase voltage and line voltage are same, so it will be VL upon phase current, and line current are not same. So line current is IL, phase current will be IL by root 3. So this will be IL divided by root 3. So this will become root 3 VL divided by IL. Okay. Now I can simply like write the base values, because VL is nothing but V base, IL is nothing but I base. So this will be root 3 into V base divided by IL is S base divided by root 3 into V base. So it comes out 3 V base whole square divided by S base. So what will be your ZPU? What will be your ZPU? Your ZPU will be simply Z actual, that is Z delta, upon the base, that is 3 VB whole square divided by SB. Okay, clear? So it is basically equals to this Z delta divided by 3 into, just give me 1 second, Z delta divided by 3, it will be SB divided by VB whole square. Okay. So this is the value. Why is this important? This is important particularly if I derive the same for star. Okay. So this is my ZPU here. If I derive the same thing for star, what will I get? What will be the again? These all are same, but this time the line current and phase current will be same, but the line voltage and phase voltage will be different. Okay. So this is my phase voltage, this is my line voltage, and this is my phase voltage. So what will be your Z base? Z base will be V phase upon I phase. So which is equals to, what is V phase now? V phase is VL divided by root 3 into I phase. I phase is IL. Okay, VL by L divided by root 3. So this will be equals to this will be equals to my Z base. This will be equals to my Z base. Okay. So this will be now what is my VL is this V base, IL is root 3 S base divided by root 3 V base. So root 3 will get cancelled. This will be V base whole square divided by S base. Okay, so your base value changes here. The factor of 3 is not here. So what is your ZPU? ZPU is equals to actual value Z star divided by the base, that is VB whole square divided by S base. I want to come to a very important conclusion. Okay, I will show you the conclusion here. Basically, it will be Z star into S base upon VV whole square. So the important conclusion here is, while deriving here, a factor of 3 comes, right? Z delta by 3, but here no factor of 3 comes. Why? If I change this delta into its equivalent star, what will be the value? From delta to star, so I am dividing. So from delta to star, the formula is what? If you remember the formula, it is Z1 Z2 divided by Z1 plus Z2 plus Z3. It is simply division, right? So it is Z delta by 3. So the equivalent star impedance will be Z delta by 3. So basically this, right, means it is already considering the fact it is star. What do I mean? So it does not matter whether I write in delta or star, the per unit value will come out to be same. Okay, this is same as this. Why? Because this is already in star and this was in delta. Now I know there is a confusion. To clear that confusion, here is the example. So I have drawn the star and I have drawn the delta. So this is just the delta equivalent of the star, right? If I convert from star to delta, it will be simply multiplied by 3. All the impedances will be simply multiplied by 3, right? If you find out the per unit value here, you find out the per unit value here, already the base are given. Base will be same, right? Base will not change. Both bases are same. You will see you are getting the exact same per unit. Pause the video and please try it by yourself. Let's find out the per unit value for the first one. Okay. So these are my base, basically V base and I base, right? V base. So V base is 11 kV and S base is 100 MVA. Now we have already derived the formula. Like you will always derive whenever you are solving. You will always derive the formula for Z base if you are forgetting. But as I have already derived it, I will use it. As I have already derived it, I will use it. Okay. So this is the formula. It is Z star actual value into the S base upon V base whole square. Now very important fact to note here is my kilo whole square is basically some mega, right? Why? It is 10 cube whole square, that is equals to 10 raised to power 6. Okay, that is what 10 cube whole square is. So it is equals to 10 raised to power 6 here, right? So 10 raised to power 6 is same as 10 raised to power 6. So basically kilos whole square is m. So if I just write here V base whole square and divide by S base, that is in MVA, so mega and mega will get cancelled. So I can directly write my ZPU in the first case will be actual value 5 into V base whole square, that is 11 whole square. Kilo whole square is there, that becomes mega, that gets cancelled with the mega in the bottom. So it is 11 square by 100 simply, right? Mega gets cancelled. So this will be 121 divided by 100, that is 5 into 1.21. 5 into 1.21. So it comes out to be 6.05. PU. Okay, let's now solve it for the second circuit. For the second circuit, remember the base has changed, so is the value of the resistance, right? So for the second circuit, the ZPU is equals to 15 into V base whole square. Remember there was a divide by 3. If you see here, there was a why did it go? Divide by 3 here for delta, right? So it will be divide by 3 into 11 whole square divide by 100, which is same as 6.05. So like what is the purpose? The purpose is to explain to you that it does not matter whether it is in delta or it is in star, the per unit value will be same. The per unit value will be same. If you want to write in star, then this formula will be used. Okay, now what if you want to convert back? So let's say you have been given a ZPU impedance, per phase equivalent is given to you. ZPU is equals to 0.6. Now how will you convert it back to star or delta? So if you want to convert it back into star, you will use this formula. So your ZY will be ZPU into the Z base. What is the Z base? Z base is S divided by S base divided by V base whole square. And if I want to convert it into delta, it will be ZPU into 3 S base divided by B base whole square. Am I correct here? It is same like this, right? So here ZPU is this value. So if I take it on the left hand side, your ZY, the actual value will be ZPU into V base whole square divided by S base. Here also the same thing. This 3 V base whole square will go at the top and this S base will be at the bottom only. So your Z delta will be ZPU into 3 V base whole square divided by S base. Okay. So yeah, that is what your Z delta is. Okay, that is what your Z delta is. So yeah, I hope now it is clear. So if you want to write that impedance in star, you will use this formula. If you want to write this impedance in delta, you will use this formula. Okay. Yeah. So I hope you have understood. So the important point is in per unit it is same. In per unit the value is same whether it is delta or star. Just the base value changes. So that's why per unit is very simple and unified. Everything is same in per unit. It does not matter whether you are in three phase or per phase or in star or in delta or what is the power, like the voltage levels are different. It unifies everything. So we will derive the same for a transformer as well. But before that, let us understand about per unit at different sites. Okay, what will be the per unit value referred to both the HV and LV side? So HV side is this one, right? Wherever the number of turns is higher, that will be HV side, and LV side will be this one. Okay, so uh, so the thing is, let me derive the per unit values both with respect to HV side and LV side, and let me check whether both side the per unit value is same or not. Let me check it. Okay, because I know one thing, actual value will change. So if I want to derive, like refer this impedance on the LV side, the actual value will change. Correct? That I know. So first of all, let me write the values over here. That let me first of all do it on the HV side. HV side means this, right? Higher number of turns. So your Z PU HV side. What will be the value Z PU HV? It will be the same formula, right? So if it is on the HV side, I will choose the voltage of the HV side and the current of the HV side. Okay. So have they given us any base? Okay, they have not given us any base. Yeah, few things are missing actually here. I should have given here. Like this is for actually I forgot to mention. This is a forgot to mention the rating of the transformer. This is a 40 kV 10 kV transformer with 100 MVA base. So 3 phase power is 100 MVA. Okay, 40 kVA 40 kV 10 kV and 3 phase power is 100 MVA. Okay, I hope it is clear now. So now if I want to solve, so this will be 40 kV on the HV side, it is 40 kV, LV side it is 10 kV, and S base is 100 MVA. The rating of the transformer, it is just a what? It is a star delta transformer. It is a star delta transformer. It is a 3 phase transformer star delta. If my impedance I have in the primary side, HV side, what will be the per unit value of that impedance? So if it is on the HV side, I will choose the base as the high voltage side base, right? V base will be 40 kilovolt. Okay, so this will be equals to your actual value upon the base. What will be your base? Now remember, it is on the star side, right? It is on the star side. If it is on the star side, then automatically this will be 5. Now I can derive the formula. You can always derive the formula. Okay, I will derive the formula because you will have the doubts. So remember, it is on the star side. So if it's on the star side, what is my I base? I base will be line current base. It will be S base upon root 3 into V base. Remember, your V base is the line voltage. Okay, so your your sorry, I was stuck in some other world. So now what is your Z base? Z base will be V phase upon I phase, right? V phase upon I phase. So V phase is VL by root 3 because it is star connected, and I phase is same as the line current because it is star connected. So it will be S base upon V base. So this will simply be V base whole square divided by root 3 into S base, right? Okay, so this is what I get. So what will be my ZPU on the HV side? ZPU on the HV side will be V actual upon the Z base, that is V base whole square. Now V base is 40 whole square on the HV side, divide by root 3 into S base, that is 100. So this will be equals to 5 into 100 into root 3. Sorry, one mistake I made. This is also okay, no, this is correct only. This is line, okay, line current is correct only. This is, yeah, this is correct only. No, everything is, oh sorry, here also this has to be, okay, sorry, okay, I made a mistake here, right? Sorry. So that's why you should not hurry. That's why you should not hurry. So your Z base is this, that is V base upon root 3, and your I base is already this S base by root 3, right? Into S base divided by V base. So, and divided by root 3 is also there. So root 3 will get cancelled. So it will be simply V base whole square divided by S base. Sorry for that mistake. Root 3 will not be there. So this will come out to be 100 into 100 divided by 40 whole square. 16 into 100. So your per unit comes out to be 5 by 16 per unit. Okay, so this is what your per unit value comes out to be, 5 by 16 per unit. What about your LV side? LV side, what will be the per unit value? So LV side, first of all I have to refer this to the LV side, right? I cannot directly write this, I have to refer this to the LV side. So how will I refer? Because this is in series with the windings. Here also if I am referring, it should be in series with the windings. Okay, so thing is, okay, I have to refer to the LV side. So I have already got the per unit value on the HV side. If I want to refer it to the LV side, what will be the value? So this resistances should be in series with the windings here. No, now one more interesting fact is what we have already discussed, how referring works in three-phase transformer, right? I will use that actually here. So these are the referred values. So what will be the referred value actually? What will be the referred impedance on the secondary side? Remember here what was given to me, that this was 40 kV is to 10 kV. Okay, 40 kV is to 10 kV. Now the thing is, yeah, now the thing is, what will be the value? So remember this is line voltage, right? So what is the phase? Then I can talk about the turns ratio. This I have talked in my three-phase transformer. So actually the turns ratio is the phase turns ratio, right? Always remember, it is the turns ratio between the coils. So it is actually basically V phase of the HV side upon V phase on the LV side. So you have to compare the turns. Okay, so these are the line voltages. So here in the second LV side, the line and phase voltage are same, but in HV side the line voltage is 40 kV, but the phase voltage will be 40 kV divided by root 3. So this will be 40 divided by root 3 and this will be 10 kV. So it comes out to be 4 divided by root 3. This is the turns ratio. Okay, so your impedance referred to the LV side will be Z dash will be equals to the actual value into the turns ratio in which I am referring to. So it should be N2 by N1 or NLV by NHV, that is root 3 by 4 whole square, because this is what? This is NHV by NLV, right? High voltage side by low voltage side, but I have to write low voltage by high voltage whole square. So it will be root 3 divided by 4 whole square. So it comes out to be 15 divided by 16 ohm. Okay, 15 divided by 16 ohm. Now let me solve the per unit. What will be the per unit in the LV side? What will be the per unit value in the LV side? It will be Z LV actual upon the Z base. Okay, so it is equals to, what is ZLV? What is ZLV? So ZLV is equals to, I already know, that is 15 by 16, right? What is Z base? So Z base in case of delta, you can derive it. It will come out to be Z actual by 3. So not Z actual, sorry. Z base will come out to be, okay, we can derive it. So it will be V phase upon I phase. Now remember, your I phase has changed. Your line current, your I phase is, this is VL by IL by root 3, right? IL by root 3. So this comes out to be IL by root 3. Now I know already that IL or I base, right, like the base line current is equals to S base upon root 3 into VB, right? So I will replace here this value. I'm doing in this like multiple times so that you are comfortable. I'm not directly writing the formula, so that you are comfortable. Okay, so your Z base will be this V base upon S base upon root 3 VB. So VB will go on the top, so this will be V base whole square divided by okay, this is by root, so yeah, 3 V base whole square divided by S base. Am I correct here? Yeah, it is correct. So now my ZLV per unit, like this, we will get a very important conclusion here. This will be ZLV is actually is 15 by 16, 15 by 16 into this divided by Z base. So Z base is 3 V base whole square. So V base we already know what is the V base on the secondary. What is the line voltage? 10 kilovolt. So 10 square into S base, right? So what is S base? S base is 100 MVA. It will not change. 100 MVA will not change, right? Whether I am in the secondary or primary, your 100 MVA will not change. It will be same only. So this will be 100 MVA. So from here, if I write the values, 100 will get cancelled. It will be 5 by 16 PU. Is this something similar? Is this something similar? Yes, it is. So what is the important conclusion? So the conclusion is ZHVPU is equals to ZLVPU. Both are same. ZHVPU and ZLVPU both are same. Okay. If both are same, that means what? That means no need of referring concept. So all this calculation, whatever I did, right, all this is eliminated totally. So you just see in the timer how much time got wasted to calculate all this. If I want to refer this impedance here, but if it is in per unit, if I know the per unit value on one side, I can directly write the per unit value on the other side. It will be same, it will not change. Why it does not change? Why it does not change? Because the base value itself changes. Base value on the primary was with respect to the HV voltage. Base value on the LV side is with respect to the LV voltage. So the base value changes. If the base value changes, that means it will help us keep the per unit value constant. So these many complications are removed with per unit. So or in other ways, what you can say, your transformer gets converted into a 1:1 transformer. So your transformer becomes a 1:1 transformer. In 1:1 transformer, it does not matter which side you refer to, it is same. Why? Because your N1 by N2 is 1. Your N1 by N2 is 1. So it does not matter whether you refer to left hand side or to the right hand side, it will be same. It will not change. It will not change. It will be same only. So why? Because your Z2 dash will be what? It will be N2 divided by N1 or N1 divided by N2 whole square into Z2, which is 1. So it is Z2 only. So your referred value is same. So your in per unit, your transformer gets converted into a isolation transformer or 1:1 transformer, where I don't need to do the referring. The value will remain same whether seen from the HV side or seen from the LV side. So that's a very important conclusion. So let's now solve similar kind of question, but this time with a single line diagram. If a single line diagram is given, like here circuit diagram was given, right? But let's say a single line diagram is given and they are telling you to draw the per phase equivalent circuit in per unit domain, refer to both HV and LV side. Okay. So if it is referred to both HV and LV side, let me assume that this is 66 kV only. This side is 66 kV. Okay, and it is star connected. This is also star connected. Okay, it can be anything, delta or star connected, does not matter. So what will be the per phase equivalent? So the first of all, I will draw the three phase equivalent, then I will discuss about the per phase equivalent. Okay, so three phase equivalent will be something like this, right? Here I will have a star transformer. On the left hand side, I'm not drawing the source. There will be a source, right? Star connected source here. Okay, my drawing is very bad. So the star connected source will be there. Okay, star connected source will be there, and the turns ratio is given, like the voltage ratio is given 66 into 3 point, so this will be 3.8, sorry, this will be 3.8, and here I have the resistance, actual value of the resistance, that is 6 ohms. Okay, now I know in per unit it does not matter whether I am in the secondary or in the primary. Already we have proved to you that it is same. So the per phase equivalent of this, instead of doing all this calculation, referring it back to the primary and then doing the calculation, I can directly draw the per phase equivalent, everything on the primary. So here I will have a single phase voltage, that will be 1∠0 pu, because here the voltage itself is 66 kV. Okay, let me write this properly. 66∠0 kV. Okay, and then I will have like a single phase transformer which is a 1:1 transformer. So it does not matter. I can even not keep it. It is just like a wire, because here the potential is V, here also potential is V, right? It is a 1:1 transformer. So I can totally ignore the transformer, and here I can directly write my RPU. That's how simple it is, right? That's how simple it is. So what will be my RPU? It will be R actual upon Z base. Remember, it is in star connection here. So I have to choose the base values accordingly. Remember, 70 MVA here. So this S base will be same throughout. But voltage will keep on changing. So if the voltage was here, it was 66 kV. The voltage here is 3.8 kilovolt line voltage. Okay. So what will be again the same thing, right? I also used to forget the formula for the Z base. So it will be base I base will be equals to S base upon root 3 V base, right? And again it is star connected, so here there will be no factor of 3, right? No factor of 3. Automatically your Z base will be, ZB will be simply V base whole square divided by SB. That's it. So your ZPU or RPU will be simply R actual 6 into S base is 75 MVA divided by line base voltage, that on the LV side it is 3.8 kilovolt, on the resistance side, right? 3.8 kV whole square. So this will be the RPU is coming out to be something more than 1, and that is totally fine. So 6 into 75 divided by 3.8 whole square, it comes out to be 31.16 pu. Okay, so your per phase equivalent will be this 31.16 pu. So in per unit domain, the question was trick question. They have asked in per unit domain, if I refer it to the primary or the secondary, what will be the per phase equivalent? The per phase equivalent will remain same. So I will write here in per unit domain, in per unit domain, per phase equivalent circuit remains same be it on the HV or LV side. Why? Because transformers are converted into 1:1 transformers. Okay, transformers are converted into 1:1 transformer. That's why, that is the reason why it does not matter in per unit domain, either refer to the primary or the secondary, it remains same, it will not change at all, it will not change at all. Okay, so that is the advantage basically of per unit domain. So if I have this multiple transformers, right, then if I just find out the per unit value on this position, and if I just, let's say this is my Z3 pu, this is my Z2 pu, and this is my Z1 pu. Okay, where automatically the voltage levels are changing, right? Voltage levels are changing, and the per unit values are calculated with respect to their own voltage levels. Then this simple circuit can be simply converted into a series circuit, because everything gets converted into a 1:1 transformer. So this complex circuit, I don't have to do any referring, nothing, will be simply converted into a simple series circuit. So here the V base will be this 11 kV VB1, here the VB2 will be this, here the VB3 will be this. Okay, this will be Z1 pu, Z2 pu, and this will be Z3 pu. Okay, so that's why per unit analysis is so important. So the aim purpose of today's class, we spent I think around 2 hours explaining this, that why is per unit so important. And trust me, no one will explain you like this, each and every single thing in detail. I'm going into the exact details of each and everything. So that's why per unit is so important, that this complex circuit can be just simply converted into a series circuit, right? In per unit domain, because a transformer gets converted into a transformer gets converted into a 1:1 transformer. Now very important, another very important factor to note is that what is the transformer impedance. So let's say if the transformer has winding impedances Z1 and Z2 respectively on the N1 side and N2 side. So let's say I have Z1 impedance here, that is the winding impedance of the primary side, one side, and I have Z2 impedance here. That is the winding impedance on the secondary side. So what will be the equivalent circuit in per unit domain? Because I have already told you that this one gets converted into a 1:1 transformer, because we divide by the voltage base and automatically it becomes a 1:1 transformer. So what we will do is we will calculate the Z1 PU with respect to its own base. How to calculate Z1 PU I have already discussed, right, on the primary side. We will calculate the Z2 PU, and then what we will do, we told you, right, this one simply gets converted into a single line. It's just a 1:1 transformer, so it becomes a isolation transformer. So on the left hand side I will have Z1 PU, on the right hand side I will have Z2 PU, and this will be Z1 PU plus Z2 PU. Okay, so ultimately you can convert your equivalent transformer, the winding resistance of Z1 and Z2, into a single impedance. So you will see this, right? What we do in a single line diagram, if transformer is given, they will give you this impedance ZT PU. So actually it is a combination of Z1 and Z2. So you will not be able to say what is my primary side winding impedance and what is my secondary side winding impedance. Winding impedance is consist of the winding resistance plus the leakage reactance, right? So in like everywhere, and I know there this is the confusion, how can I convert a simple transformer where the left hand side winding impedance is something else, right hand side winding impedance is something else? How can I convert it into a single impedance? How is it possible? Because your like I for those students who have already solved the per unit analysis, or who have already studied power system, they will know there is a confusion, right? This ZT is actually combination of Z1 plus Z2, but I cannot directly say in the question they will always give you this. This will be given in the question. This will be given actually, and you don't need this. You don't need this. So ultimately, while doing the fault analysis or analysis of the circuit, you will just replace the ZT with simple series impedance. That's it. This is not important, okay? Because we are just doing the circuit analysis. So that's why this, right, is very easy, because the winding impedance on the primary might be different, the winding impedance on the secondary might be different, but in per unit both of them come in series. There is no concept of referring because the turns ratio becomes 1:1. So we just simply convert our transformer into a single impedance ZT, and of course we neglect the shunt branches. So magnetizing branches are neglected. So a transformer, that's why we can replace a transformer with a ZT. That's the conclusion of today's lecture. I can replace a simple transformer with the value ZTPU, okay, and we neglect the shunt branch, that is the magnetizing branch, because the current in the series windings will be much higher than the shunt, okay. So what can I say is that your ZT will be given, and it is a combination. It is a series combination It is a series combination of the primary and secondary winding impedance. Okay, so that is the conclusion. We can simply replace our transformer with a ZT, single impedance. Okay, so in actual domain, this will be the values. Here I will have the winding impedance in the primary side, and no one explains this clearly, right? These things no one explains this. So yeah, this will copy. In actual domain, the transformer will be shown like this. Okay, but in per unit, simply we can convert this into a single impedance ZT, that is a combination of both the primary and the secondary. So things become very simple, very simple. Okay, so yeah, that's the conclusion basically in per unit what happens to the transformer windings. So I wanted to give a homework. This question I will solve in the next lecture, but you guys can pause the video, try it out by yourself, and in the starting of the next lecture we will start with the solution of this question and we will discuss more about per unit. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 3 of our power system, right? Today we will continue our discussion with per unit. Also we will do the assignment 1 solutions. There will be many questions here which we will be solving. So this was the first question that I gave you homework in the previous lecture. So this is a P by Q, gate P by Q. So the power system is shown, single line diagram is shown, generator G1, all the values and their respective reactance percentage is shown. So whenever percentage is shown, it basically means per unit, right? So percentage basically means, I know what is my PU. PU is actual upon base, right? So PU percentage will be what? PU percentage will be simply PU into 100%. That's it. That's as simple as it is. So if I want to write the per unit, what will be the per unit of the generator? XGPU. XGPU will be 0.09. Now it is 0.09. If I see in the single line diagram, because they have told you in the single line diagram, convert this into per phase equivalent. The basically choose the 25 kilovolt as the base. The impedance diagram will be, basically they are telling me what is the per phase equivalent diagram of this single line diagram. I am not observing 0.09 anywhere else. What went wrong? In the question they have told me to use a common base voltage of 25 kilovolt and the rating of 200 MVA as the base, and the base 25 kilovolt is base voltage where? At the generator G1 side. So generator G1 side, the base voltage is 25 kilovolt. Can you tell me what is the base voltage for T2 on the LV side? The base voltage for T2 on the LV side will be 25 kilovolt. The base voltage for T2 on the HV side will be 220 kilovolt. Why? Because base voltage itself will change. Base voltage on the generator is 25 kilovolt. If I am observing on the HV side of the T1, here if you see the voltage was 25, it is 25 is to 220. So base voltage also changes. So on the LV side of T1, base voltage will be 25 kilovolt. On the HV side of T1, base voltage will be 220 kilovolt. Because base voltage will change. Why? Because base voltage follows the equation of normal equation. So basically I know my V2, VLV, VHB upon VLV is, for the transformer T1 it is 220 upon 225. 220 upon 25. Okay, it is 220 upon 25. Now if I have told you base values follow the same equation as actual values. So this will be equals to V base of the HV side upon V base of the LV side. So automatically you are observing that the V base of the LV side will be 25 kilovolt, V base of the HV side will be 220. So automatically it will get changed. So base voltage gets changed. That's why per unit values remain same, right? You might have the doubt, sir, How is per unit value remaining same? Because the base is automatically getting adjusted to keep the per unit value same. Base automatically gets adjusted to keep the per unit value same. Okay. So if the base voltage is given at the generator G1 side 25 kilovolt, then automatically all the other base voltages are also fixed. And MVA base is generally, it's a global base, so it's same. MVA base will be same throughout. You don't have to worry about referring, because you cannot refer MVA, right? You refer voltage. There is voltage transformation, but there is no MVA transformation. Correct? Okay, I hope it is clear now. So let me draw the equivalent impedance diagram first, then I will slowly find out the per unit values of each of the component. So I will have here generator, then I will have the generator per unit reactance. Remember, this reactance was derived with respect to its own base, but now if you see, now the S base has changed, because here the base was 100 MVA, but the base they have told me to choose as 200 MVA. So what will change now? We will discuss about that. Exactly that we will discuss. Okay. So this will be Xg. Then I will have, they have given me this generator G2. So G2 is here actually. G2 is here, but T1 is here, right? So T1 again will be only a single reactance is given. That means it is the overall winding reactance. So previously I derived for the impedance. So if you neglect the resistance, you will get only reactance. So this represents the overall winding reactance of both HV and LV side. So I will have this XT, and then I have this transmission line. For the transmission line, they have given me that it is 150 ohms in actual value. They have not given me the per unit value. So this will be X transmission line per unit value. Then I am encountering the transformer T2. So I will have XT2. Why is this called reactance diagram? Because there is no resistance, only reactance is there. That's why it is called reactance diagram. If there was resistance, it would have been called impedance diagram. Then ultimately I am encountering generator. So this will be generator G2. So here I have EG, and remember this will be simply, what is the voltage? Because it is 25 kilovolt and base is also 25 kilovolt, it will be 1 pu, right? 25 by 25, actual upon base will be 1, 25 upon 25, so it will be 1 angle 0. Here also it will be 1 angle 0. Okay, here they have not written the voltage because angle I don't know, because there has to be some angle difference. That's why they have just written here G1 and G2. That's it. They just want the reactance values, and this is my reactance diagram. So let's one by one calculate our values. So what will be Xg? Remember, Xg here is 0.009, but it is not same because this was calculated with base MVA as 100 MVA, but here the base MVA is 200 MVA. So what will change? So the thing is, that I know okay. So how do I calculate the PU? I know PU is equals to, for impedance, I'm talking about impedance, it is basically my per unit impedance XPU is, actual value will be constant, actual value will always be constant, right? It is X actual upon, like it is proportional to the S base upon voltage square, right? S base upon voltage square. This we have derived in the previous lecture. This formula we have derived in the previous lecture. So what I can say is my per unit value is like my actual value will never change. Whatever is the actual impedance value, that will never change. Just like the transmission line reactance is 150 ohms, it will never change. Okay. But I can see that the per unit value actually depends on the base MVA that I select. It is directly proportional and it is inversely proportional to the V base. This will always remain constant. X actual will always remain constant. So I can say my XPU is proportional to S base and my XPU is inversely proportional to V base whole square. In this whole diagram, I can see that the V base will not change. Like this will have 25 kilovolt. This T1 base voltage is same only 25 to 20. Here also the transmission line voltage. Okay, with this we have to calculate. Okay, what is the base voltage? 220 kilovolt, because this is the high voltage side, right? Then here also the base voltage will not change. MVA base will change. MVA base will change. Here also the base voltage is again 25 kV, that is shown here. So base voltage is not changing. What is changing throughout the line? Throughout the line, the MVA is changing. S base is changing. Here the S base is what? 100 MVA. Here I have to choose 200. So it is changed. Here it is 100 MVA. Here it is 90 MVA, right? For this T1, it is also 90 MVA. Here it is not shown. It has not shown me what is the MVA here. Okay, I have to individually calculate it. So S base is changing. So basically my PU, right? If I write XPU new upon XPU old, if only S base is changing, right, it will be what? It is directly proportional to the new base. If everything else is constant, my V base is constant, actual value will never change. Okay, so it will be S base new base upon old base. Okay, so the thing is this is the formula actually. If you are struggling to understand, I can directly use this one. So my XPU is what? XPU is equals to my X actual upon into S base upon V base whole square. Now you might have a question, sir, what if like there was a factor of 3 here, right? So factor of 3 will automatically get cancelled. Factor of 3 will get cancelled. So I am not writing it. So note factor, you derive it, you will see it is automatically getting cancelled. Factor of 3 will automatically get cancelled. So I know my actual value will never change. Let's say this per unit value was XPU1 on the base chosen as SB1 and VB1. Let me write the other per unit value XPU2, that is equals to actual value will never change. Actual value will always be constant into S base 2 divided by V base 2 whole square. Okay, so I can equate this one and this one. Actual value will never change. So from here I can write what is my actual value. If I divide these two equations, right, simply dividing these two equations, so what will I be left with? So I can write XPU1 by XPU2 equals to this will be S base 1 divided by S base 2 into V base 1 divided by V base 2 whole square. So in our case the base voltage does not change, right? It is same only, just the MVA base changes, hence the per unit value will change. It is directly proportional to the S base. So this is the actual formula that if someone has already studied power system analysis, he or she will know this very well. I had derived this in the machine's prerequisites as well. Okay, there I had derived this in the machine's prerequisites as well, right? So there I explained with different perspective. Here again I am explaining it with different perspective. So if you are changing the base, the per unit value will actually change. If you are changing the base, the per unit value will actually change. So here the base has, like in this generator case, the new base is double of the previous one. It is 200. So your xg1, right, your xg1 will be what? It will be your old pu, because here, right, your x1 will be x2 pu, the old pu, into the new base upon the old base into the voltage ratio whole square, right? So sorry, this will be, sorry, I made a mistake here. Yeah, this will be 2 actually here. Here we'll have 2, here we'll have 1. Okay. This will be 2, this will be 1. Okay. So in our case, the voltage base is not changing, just the S base is changing, right? So the new PU value will be the old PU value. So I can write here, I can convert this XPU new will be equals to XPU old if the PU2 is the old one into the S base new divided by S base old. Also voltage ratio is there, right? Into V base old divided by V base new. Whole square. Okay. So yeah, we got these values basically XPU new, XPU old, S base new, all these things. So here I can use this direct formula. So base voltage will not change, but the S base will change. So it is XPU old, that is 0.09 into new base. New base is 200 MVA, old base is 100. The voltage ratio are same, voltage base ratio are same. So it actually becomes 0.18. So here this will be XG1 will be basically 0.18. Same will happen over here, XT, same will happen because the voltage ratio, voltage base has not changed, but the MVA is 90 MVA. So this has been calculated with respect to its own MVA. So your XT new will be what? It will be the old XT 0.12 into the new base, that is 200 divided by 90. So this one, right, will be 200 divided by 90, 2.22 into 0.12. So 0.267, 0. Your xt1 will be 0.267. Your xt2 will be what? %. So same formula will be used. This also will be 0.267. What is your transmission line? So here actual value is given, actual value. So I have to use the like this formula. I have to use this formula. So what will be my XTL PU? It will be actual, that is 150 ohms, X transmission line one actual, that is 150 ohms, into the S base actual. What is the S base actual? S base actual is they have given me, it is 200 MVA, and whenever nothing is mentioned you will assume it to be star connected. That's why this your voltage, right, this formula will come out to be 150. There will not be any factor of 3. In star connection there was not any factor of 3. So by default, always by default if nothing is mentioned, consider star connection. And anyways, we have already proved in the previous lecture that if you consider delta or star, the value, per unit value will come out to be same. So star connection. So it does not matter, but still to clear the confusion, you assume it to be star connection. Okay, but again we have proved in the previous lecture, it does not matter whether it is delta or star connected, the per unit value will come out to be same. So this will be 150 into S base is 200 MVA, 200 divided by the V voltage whole square. V base is what is the voltage in this line? Here it is the high voltage side of the transformer, right, which is 220. So it will be 220 kilovolt whole square, 220 whole square. So this value comes out to be 150 into 200 divided by 220 whole square. So 0.612. So this is the reactance that we get. Okay, so 0.6, sorry, not 0.612, 0.619, which is almost equal to 0.62. So this will be 0.62. So what is the reactance here? Xg2. Xg2 is just same, right? Again double the S base, so this will also will be 0.18. Okay, so here 0.18, 0.18, 0.18, 0.18, 0.267, 0.267, 0.62. So 0.18, 0.18, 0.267, 0.267, 0.62. Yeah, this is correct. So option B will be the correct answer for this question. Okay, so this is the gate P by Q, and I have not, like, I've explained you like how the change of base works. So we actually understood a concept without teaching you the concept by solving the question. So the concept is change of base. So this concept is basically change of base. If I am changing the base, then what happens? Change of base. Okay, that is the concept. I hope you have understood this point. So that's how change of base actually works, and I have already derived you the formula of change of base. Okay, so now try this question again by yourself. Again, this is a very big circuit, and all these values are derived with respect to their own base. So we will try to use the change of base formula here. Okay, I will try to draw the per phase equivalent. So first of all, I will write the per unit values with respect to a common base. Per unit values with respect to what they have given me in the question, that choose the base as 100 kilovolt and 100 MVA. So sorry, not 100, 11 kilovolt. So my bad. One thing I've this actually one more thing I should mention here, that 100 kV on the generator side, because whenever voltage is mentioned, because voltage keeps on changing, so I have to mention exactly at what point you are referring to with respect to base. So 11 kV on the generator side. Okay, so yeah, now I hope it is clear. So your V base is here, right? So with respect to 11 kV, and S base is MVA. Okay, so this remember on the generator side. Okay, so sorry, not 200, it will be 100 MB, right? Because they have mentioned I have to choose 100 MB. So now let me draw the like equivalent reactance diagram, or not reactance, actually impedance diagram, because we have impedance here as well, right? So if I draw the equivalent diagram, first of all I have a generator. So per phase equivalent I'm drawing, I will have a generator which will have its own reactance, right? This is generator G. Then I will have the transformer which will have its own reactance, right? Then I will draw the transmission line. So transmission line, they have not given me any resistance, so I will assume it to be, there is no resistance, 0, so it is short circuit, right? Then I have another transformer, step down transformer, that is here, and then ultimately I have two loads connected, so they are in parallel. So they are in parallel to this point, two loads connected. So one is the motor which will have its own reactance and motor will be there, and another one is a static load, that is a impedance load, right? That is given, ZL is 1 plus j pu. So it is basically RPU plus XPU. RPU plus XPU, right? So now let me derive the per unit value. So Xg is 1 pu, with V base is very simple, it is 11 kilovolt, but S base has changed, it is 200 MVA, but they are telling me to choose a base of 100. So what will be the new xg new? So xg new, let me do one thing, let me change the, okay, let me make it more interesting. Let me change the base value as well, so that the question is more interesting, right? Because someday this can come. So let me choose the base v base to be 22 kV. If I choose the v base to be 22 kV, then things will change. If the v base is 22 kilovolt on the generator side, right? Although this is not advised, because this will only make the calculations more complex, but I am preparing you for the worst case. So in the worst case, this can get asked, right? So if the base on the generator side is 22 kilovolt, can you tell me what will be the base on the LV side of the transformer? It will be 22 kilovolt, because here also it was 11 kilovolt. For 11 kilovolt, the base was 22 kilovolt. Here also the base will be 22 kilovolt. So here the base will be 22 kilovolt. So let me copy this diagram. I don't want to change stuff here. So here on this side the base will be 22 kilovolt. Now can you tell me what will be the base here? Base is just the double, right? If you observe, it will just follow the turns ratio. So here I multiplied by 12, right? I multiplied this by 12. So this also, if I multiply by 12, it will be double. It will just be the double. So this will be, on this side it will be 264 kV. Okay, on the HV side it will be 264 kV, on the LV side it will be 22 kV. Okay, here again the base voltage will be 264 kV, here the base voltage will be 22 kV, and here also the base voltage will be 22 kV only. Okay, so if these things are changed, now the XPU will not be just proportional to the MBA, it will be dependent on the V base as well. So this will be xg new will be equals to xg old. Now this formula, if you remember, it is actually very good, useful, so you have to remember this, right? So xg old into SB new upon SB old into VB old whole square into VB new whole square. So now what will be, like, what is my xg old? Xg old is given to me, it is 1 pu. So 1 pu into S base new. S base new is 100 MVA, 100 upon S base old. S base old is 200. So this will be 200 into VB old. VB old is actually, old base was what? Old base was with respect to the generator, that is 11 kilovolt of the generator, right? So it is 11 kV, 11 kV, which will automatically get cancelled. kV will get cancelled upon 22. The new base is 22 on the generator side, right? So whole square. So this will become 1 by 2 whole square. So this will be 1 by 4, 1 by 8. So which is 0.125 pu. So your pu has changed, right? So this will be 0.125 pu, J 0.125 pu. Here also I forgot to write, like all these are reactants. So here J will be there, right? Okay. So yeah, now it is, I guess it is fine. So I got one value. So I have to find the other values. So for the other values, I can again take out a page. I can take out a page here, right? The transformer T1 and T2. So xt1 new will be xt1 old, that is 2, into base new is 200, sorry, not 200, so it is 100, right? Sorry, 100 MVA divided by the old base you see is 300, right, with respect to its own base. So 300 into VB old, okay, VB old, uh, VB old, that is 130. So what is the base? So I can choose, okay, okay. So if I am choosing VB old, right, you have to choose either the primary or secondary. So if I am choosing the primary, right, then I have to choose the old base of the primary, that is 11 kV, and the new base at the primary. So choose in both the common side. If you are choosing the primary, then choose the primary. If you are choosing the secondary, then choose the secondary, because per unit value won't change, right, either in the primary or secondary, but you have to choose one point. But you cannot do that I'm choosing the old base from the primary or from the LV side and the new base from the HV side. That you cannot do. So here I will write a note. So this will be old base, that is 11 kV, upon the new base, that is 22 kV. So in note that for transformer you must choose the base. Choose the base either both on LV or HV side. You cannot choose one from the LV and one from the HV. So one from LV and one from HV, you cannot do it. Then this formula will not work. Okay, not allowed. So this will be whole squared. So this will be actually 2 into 1 by 4. So this is 1 by 2, 1 by 6, right? This is 1 by 6. So 1 by 6 is 0.167, right? 1 by 3, 1 by, yeah, 1 by 6 is 0.167 pu. Okay, so this will come out to be 0.167, and this will this be same? No, here the rating of the transformer MVA base is same, but the per unit value has changed. So the new per unit also will change. So xt2 new will be the old value of xt2, that is 0.5 into new base, that is 100, upon the old base, that is 300. Now what is the voltage? You choose either both on the HV side or on the secondary LV side. So let me choose HV side. So if I am choosing the old base of the HV side, that is 132 kV. So this will be 132. If I am choosing the new base on the HV side, I have to choose from the same side. It is 264 kV. So this will be whole square. So 1 by, so this is 1 by 2 whole square, 1 by 4, 1 by 4 into 2, that is 1 by 8 into 1 by 3, right? It is even lower. So this will be actually 4 times lower than the previous one. So previously it was 0.167, it is 4 times lower than that, that is 0.04167. So this will be J 0.04167. Okay, here in case of motor, what will be the reactance in case of motor? It will be equals to reactance for a motor, right? X motor new, it will be equals to, what is the old value? Old value is, they have given me, it is 1 pu, and remember what is the S base? S base is 20 MVA, so it is 1 old value into the new base, that is 100, upon the old base, that is 20, into the voltage. Now what is the voltage level here? Voltage level here is fixed. For a transformer there was doubt, but voltage level here is simply, according to the old base it is 11 kV, but according to the new base it is 22 kV. So this will be old upon new, so 11 upon 22 whole square. So this will be 5 into 1 by 4, so this will be 1.25 pu. So this will be J 1.25 pu. What about here? What will happen here? So for R base as well, it will be same only. Here the S base is 10 MVA. Sorry, so for the load, right? For the load, it will be old load. What is the old value of the impedance? Old value is 1 plus J pu, right? 1 plus J pu, 1 plus J into the S base new. S base new is 100. S base old, what is the base? Base is given to me 10 MVA, right? It is given to me 10 MVA. So 10 into the V base old, that it is again fixed, that is 11 kV, and V base new is 22 kV. So 11 upon 22 kV whole square. So this will be 1 plus J into 10 into 1 by 4. So this will be 2.5, right? So 2.5 plus 2.5 J pu. So here this will be 2.5 pu and J 2.5 pu. So that's it. That's the equivalent diagram with respect to a common base. So I know it's difficult because the voltage V base was changing. If V base was not changing, then this would have been so simple, right? Like just like the previous example. I did not want to copy the same example again, like do the same question again, because that will be just waste of time. So I want you to try this question by yourself. So we are solving the assignment question only. Try these questions by yourself and I will come back with the solution. So let's read this question. We have a single phase transformer that is rated at 1000 volt ampere. So the rating of the transformer S base is 1000 volt ampere. It's a single phase transformer, right? Single phase. It's not a three phase. So which is 200 volt to 100 volt primary to secondary. So I have a single phase transformer which is 200 volt in the primary and 100 volt in the secondary. Okay, 200 volt in the primary and 100 volt in the secondary. The transformer has leakage reactance of 25%. So if I want to draw the equivalent circuit diagram of the transformer, then the leakage reactance XPU is 25%, that is 0.25 pu. Okay. Yeah. Now they are asking me calculate the referred leakage reactance of the transformer on the HV side. Okay, in ohms. So they are asking me the exact leakage reactance. So this is what? This is XPU that contains both the X1 pu plus X2 pu. Right? This we have already derived in the previous lecture. Now what is the actual value? So if I convert this into actual value, right? X1 actual will be X1 that is already in the primary side plus X2 dash, that is X2 referred in the primary side, right? Or if I want to write X2 actual, it will be like basically this is the sum of both the reactances, right? This will be equals to x2 already in the secondary side plus the x1 dash, that is x1 referred to the secondary side. They are asking me what is the referred leakage reactance of the transformer on the high voltage side. So everything is referred on the high voltage side. So I know what is XPU. How do I find out X1 actual? It is very simple. You just have to, you know what is my XPU, and if you multiply this with Z base, you will get your X actual. Now this Z base should be, depends whether you are calculating at the primary or secondary. Now they are telling me what is the equivalent primary. So I will write the Z base of the primary. What is Z base? Z base will be very simple. It's a single phase. So for single phase it is very simple, right? So I know what is my S base. It is VI, V base into I base. And my Z base, it is single phase, right? Single phase means it is V base upon I base. So I can replace here I base with S base by V base. So this will be V base whole square by S base. Right? Yeah. So Z base will be V base whole square. It is a single phase. Single phase, we don't have any confusion, division by 3 or multiplication by 3. S base. Okay. So I hope now it is clear. Now you replace this over here. So my X actual, X1 actual in the primary side will be equals to XPU. XPU is XPU is 0.25 into Z base. Z base is V base whole square. V base whole square is in the primary side, what is the base? 200 volts, right? So it will be 200 volts whole square. 200 volt whole square divided by the S base. What is the S base? S base is 100 or sorry 1000 volt ampere, right? So it will be 1000. So this will be 1 by 4 into 4, so this will go away, basically 10 raised to the power 4 divided by 3, so this will be 10. So on the primary side it is 10 ohms. Okay, on the primary side it is 10 ohms. X1 actual. Now remember this is, sorry, actually my notations are actually wrong. This should be X, it should not be X1 because you will get confused that it is only just this leakage impedance, leakage reactance of the primary side. No, it is the leakage reactance referred to the primary. So primary, let me write XP. Okay, let me write this as XP, and this is, let me write XS. Leakage reactance, actual value of the leakage reactance referred to the secondary. Okay, so here this, let me write it XP, otherwise you will get confused with X1, right? So it becomes 10 ohms. Now next what they are asking, this is the first answer. This is the first answer. Now the second answer, calculate the referred leakage reactance on the low voltage side. Okay, low voltage side basically means the secondary side. So again the same formula, XS actual will be equals to XPU, will be same, it will not change, but this time the V base will change. V base will be 100 volts instead of 200 volts, divide volt ampere rating will not change. So this will be basically reduced by 4 times, that is 2.5 ohms. So on the low voltage side the equivalent leakage reactance is 2.5 ohms. Now let's solve the third question. If 3 identical transformers are connected in star to star. So basically I am converting my single phase transformer into 3 phase transformer and I am connecting them in star star. Can you tell me what will be the volt ampere rating? What will be the S base? So S base, right, will become 3 times the S base of the single phase because I have 3 transformers connected. So it will be 3 times S single phase, 3 times 1000. So it will be 3000 volt ampere. Okay, so it will be 3000 volt ampere. So I hope that is clear now. 3000 volt ampere. What is the, sorry, now what are the working, what is the rated line voltage on the secondary side? Secondary side meaning on the this low voltage side. what will be the rated line voltage? Now remember, we are connecting the transformers in star star. If I am connecting the transformer in star star, then the phase voltage is still on the secondary side is 100 volts, right? But what is the line voltage? Line to line voltage will be, as it is star, it will be 100 into root 3. Very simple. Or you can simply connect the 3 transformers. Okay. So if I am connecting 3 single phase transformers in star to star, how will they look? This we have already discussed in 3 phase transformers, right? That's why I'm not here giving enough emphasis to this concept, because already we have discussed this in 3 phase transformers. So I have 3 transformers. It's just like a transformer bank which is connected star to star. So star to star. Here. So this is the phase voltage, but they are asking me what is the line voltage between these 2 points. I know this point has the voltage of 100 volt, right? Phase voltage is 100, like this is 200, this is 100, right? Phase voltage. But they are asking me what is the line voltage. So line voltage will be 100 times root 3 because it is connected in star. Very simple, right? So it will be 100 root 3. So it will be 173.2 volts. Okay. So that is the line voltage. Next, what they are asking? They are asking what is the total 3 phase power rating. So it is very simple. 3 phase power rating will be 3000 volt ampere. Okay. I don't feel I have to explain much. 3 phase will be 3000 volt ampere. This is the other answer, and this one is the other answer. That's it. That's how simple this question was. So let's now move on to the next question. Now this actually is a concept, but I am trying to explain this with a question. Okay. The question is that if we have, now one more thing before coming into this question, I want to explain one more thing, that if you notice, observe one thing here, what will happen to the S base? S base becomes 3 times S single phase, right? S base becomes 3 times S single phase. So will your ZPU change? What was ZPU? ZPU in case of a single phase, right? ZPU for a single phase, it was simply Z actual upon Z base. Z base was actually equals to S base upon V base whole square. Now will the ZPU change in 3 phase? Will it change? If your answer was yes, then you are wrong, because we told you, right, ZPU does not depend on the phase connections. It is Z actual into S base. Now what is the base? S base is 3 times S single phase, right? So now the base has changed to 3 times S single phase divided by V base. Okay, V base, remember your line voltage has not changed. It is root 3 times the previous one, right? So it will be root 3 times whichever side you are in times V base whole square. Previously it was 100, V base was previously 100, now it has become 100 root 3 because it is the line voltage. So this is squared. Sorry, this is not whole square. Sorry, this will be squared, right? Whole square. So I'm observing, if you see, it is same, right? This 3 and 3 will get cancelled. It is a single phase upon V base, that is the previous one only. So basically ZPU 3 phase will be same as ZPU single phase. So basically that is the beauty of per unit impedance. So it does not matter whether it is single phase, it is 3 phase, it is delta, star, it does not matter. Your per unit impedance will not change for a transformer. For a transformer, your per unit impedance will not change. So your per unit impedance for a transformer is independent of connection type. Okay, it is independent of the type of the connection. It does not matter, it will not change. Okay, so now let's come to this concept. Basically, if it's a 3-winding transformer, then what will happen? So if it's a 3-winding transformer, just like 2-winding transformer, you will assume that, let me bring it here. What you will assume? You will assume that, let me write the per unit impedance of this one. Okay, like this, let's assume that these are all winding impedances, right? Leakage reactance and the winding resistance for all the 3 windings, correct? So you will assume that I will get some Z1 PU here, I will get some Z2 PU here, I will get a Z3 PU here. Then what will do? I will simply connect this in series, right? And again you will get equivalent ZT of the transformer, that will be equal to Z1 plus Z2 plus Z3, and then your life will be so easy. But unfortunately your life is not that easy, you have to struggle. So it is not that simple, right? You will just simply convert them into per unit and then simply add up. For 2-winding transformer it will work, but for 3-winding or multi-winding transformer this will not work. You have to follow the old approach. What was the old approach? If you remember, we used to connect the dots at a single point and the non-dots at the other point. So actually the circuit diagram will be like this. Actually what will happen is, I will have a ZPU in the primary side, so Z1 PU. So this is my Z1 PU, right? And let's assume that this point is the dot point. Okay, so this dot point will be again connected here as well. So I will refer this on the primary side, and I will not refer this directly. First of all, I will find the Z2 PU, and you know this thing, that if I know Z2 PU, if I refer this on the primary, I don't need to change anything. The value will be same, because referring in per unit, the value does not change. So I will refer this into the primary and I will connect this with a dot. So here I will have Z2 PU. So all these concepts have been taught in machines, like referring and then connecting the dots. That's why I am not stressing. I am expecting that you have learned machines from me. I have taught this very well in machines, all this. So Z2 PU will be connected in the dot, and in the same dot, my Z3 PU will be connected also. But if you see that here Z3 PU is connected with a non-dot, so the dot is just short circuit. So dot will be short circuit for the third one. Okay, so this is the connection. Now what about the non-dot? What about the other connection? So this is the non-dot. So this point will be the other point of the secondary side, this point will be the other point of the primary, and this point will be the other point of the tertiary. So this is the third winding, right? So third winding, if you see, non-dot is connected with this impedance. So I will find the equivalent Z3 PU and I will connect it over here. So non-dots are, all of these are non-dots, they are connected together, and all of the dots are connected together. So that's how you will solve. So this is the per phase equivalent. Okay, this is the per phase equivalent. Like for now you are observing it's just a single phase transformer. In 3-phase as well, this will be the per phase equivalent diagram. It is just like it is called as a T diagram because the shape is like T, or star diagram. So this is what happens when you have more than one windings. That's how you will solve. So same thing will be followed for a 3-winding transformer, 3-phase 3-winding. So I have 3 windings. So this is my primary, this is my secondary, and this is my tertiary. So tertiary is delta connected, and why we use tertiary? To remove the circulating currents, right? This already have been discussed in the harmonics chapter of machines. And so if I have 3 windings, the equivalent diagram will be ZP, ZS, ZT. What is ZP? ZP is the primary leakage impedance in per unit. ZS is the secondary leakage impedance in per unit. ZT is the tertiary leakage impedance in per unit. So all the dots are connected together and non-dots are connected here. Okay. So I hope it is clear. So non-nodes are connected with neutral because this point is neutral basically. Okay. So I hope it is clear now. I hope it is clear. How can I draw the per phase equivalent? But now how will you actually find out ZP, ZS and ZT? Okay. How do you find out? So what we do, we use a method known as measuring. So we have three variables, ZPS, ZPT, ZST. So let me see the definitions of each of them. So ZPS is per unit leakage impedance measured from primary with tertiary open circuited. So I will just show you the single phase transformer, that will be easier for me to explain. Okay, I just need a explanation. So here the first one is telling per unit leakage impedance measured from primary with tertiary open. So this is open, and okay, one more thing I missed, with primary open, with tertiary open circuited and secondary short circuited. I missed this point, short circuited. So if I am short circuiting the secondary and if I am open circuiting this, so here no current is there, 0 ampere. And if I am applying some voltage here, right, I am measuring the impedance from here, Zin, what will I see? I will observe that this impedance, and if I refer this to the primary, so I will have Z1 PU plus Z2 PU, because only this winding impedance is there, right? It is shorted, otherwise it is shorted. So only winding impedance. So this is Z1 and this is Z2. So whatever I am measuring is Z1 PU plus Z2, right? So basically I am measuring ZS PU. So your ZPS is equals to ZS PU or ZP PU plus ZS P. Okay. So your ZPS is equals to ZP PU plus ZS PU, right? Same thing. You do the same thing. Apply the same thing for the ZPT. So ZPT will be the per unit leakage impedance measured from primary with secondary open circuited and tertiary short circuited. Tertiary will be short circuited. And the last one, so here what will be this value? So this value will be equals to actually, so actually what happens, we actually measure it, we actually measure the impedance and then we divide by the Z base to get the per unit. I hope that point is clear. So we'll measure, we'll get the actual value, okay, ZP plus ZS dash, because it is referred to the primary. Then I will divide by the Z base of the primary, right? So I will get my ZPS in per unit, that will be ZP PU plus ZS PU, because if it is referred, I am dividing by the base of that particular site. Okay, so ZP PU plus ZS PU. I hope it is clear. Okay, so yeah, so this value will be ZP PU plus ZS PU, and this value will be ZP PU plus ZT PU, and this value here, what we are doing, we are measuring at the secondary, measured from the secondary with primary open circuited and tertiary short circuited. Okay, so this will be actually equals to ZS PU plus Z TPU. So basically why we are doing this, to get the value of ZP, ZS and ZT, right? We have got three unknowns and we have three equations and three unknowns, I can easily find out what is my ZP. What will be my ZP? So my ZP will be equals to, why can I find ZP? So ZP, so how do I find ZP? So what I can do, ZP is common between these two, right? ZP is common between these two. If I subtract ZS minus ZP, no. Okay, if I add all these three, what will I get? ZP plus ZS plus Z, no, that will not help. If I add these two values and okay, if I add these two equations, so I have three equations, right? Three equations I have. Let me show you the three equations. One is ZPS. ZPS is ZP plus ZS. Everything is in per unit. I'm not writing it. Then I have ZPT, that is ZP plus ZT. Then I have ZST, that is ZS plus ZT. So if I add these two equations and then subtract this one, what will I get? So it will be basically 1, 2, 3. So first of all, I will do 1 plus 2 minus 3. So this will be, on the left hand side, it will be ZPS plus ZPT minus ZST equals to these two additions. So ZPS Z2 ZP plus ZS plus ZT and minus ZS plus ZT is there. So automatically this will get cancelled. So my answer will be, I can directly find out from here ZP. I can find out the value of ZP. So what will be the value of ZP? So ZP will be half into ZPS plus ZPT minus ZST. Similarly, you can find out ZS. What will be ZS? It will be half of ZST plus ZPS minus ZPT. You can solve, you will get this value, and your ZT will be what? Or everything is in per unit. Okay, ZT will be half of ZST plus ZPT minus ZPS. Okay, so I will write here again to emphasize this point. Note, everything is in per unit, then only I can simply add this. If it is not in per unit, things will be different. I will show you. So everything is in per unit. Okay, everything is in per unit. So these are the formulas. You don't have to remember it, but understanding this is enough. Okay, so let's solve a quotient to clear whatever we have learned even better. Okay, so here we have a 3-phase 3-winding transformer that has the following specification. So it's a 3-phase 3-winding transformer where the primary is connected with star. So primary I have star, and secondary is again star. Secondary is star, right? And the tertiary is delta connected. Tertiary is delta. Okay, so this is the primary, tertiary, and secondary. Okay, so primary is star, which is 66 kV. The rating I'm writing 66 kV, 15 MVA, and your secondary is 13.2 kV and 10 MVA. Now you might have a doubt, so transformer cannot change power. How is it possible? Because whatever we learned, that if it's a single phase transformer, right, and for a 3-phase transformer as well, if I know the power rating of the primary, right, that is 15 MVA, it is 15 MVA only. Secondary also it will be 15 MVA. But why, sir, how is it changed here? It has not changed. Here windings are different. So here it was only 2-winding transformer. If it's a 3-winding transformer, right, and here also I have a winding. So if you are transmitting from, if you are providing input power as 15 MVA, some of it will be distributed to here, some of it will be distributed here, right? Because I cannot provide here 15 MVA power. If I provide here 15 MVA power, whatever input I am providing, it is going to the secondary winding, nothing is going to the tertiary. So the tertiary winding rating has to be 0 MVA, because obviously transformer cannot generate power by itself. Previously power was same because it was 2 winding transformer. Now it is 3 winding transformer. So the power rating also will be changed. So the secondary has a power rating of 10 MVA and the tertiary will have the remaining power rating, that is 15 MVA. So you can check the calculation as well, that input is 15 MVA plus tertiary plus secondary, that is 15 MVA. So input equals to output. Okay, that is still intact, that is still same. What is the voltage level? Voltage level is 2.3 kilovolts. kilovolt. Okay, so the voltage level is 2.3 kilovolt. Now what they're telling me, the following leakage reactance have been measured. So we have only measured the leakage reactance, we have not even measured the the resistance is negligible. So 0.07 pu on a 15 MVA 66 base with secondary short circuit and tertiary open. Basically what it is telling, it is telling that we have measured ZPS pu. So ZPS pu is 0.007 per unit. Is it correct? Yes, because on the primary side I see that the voltage rating is 66 kV and the S base is 15 MVA. So this will not change. This is absolutely correct. Okay, this will remain 0.07 per unit, given in percentage or 0.07, whatever you want to say. 0.09 pu on the same base with tertiary short circuit and secondary open. So basically it is telling that I have measured the Z same base tertiary short circuit. So it will be ZPT. ZPT pu is given as 0.09 per unit. Okay, 0.09 per unit. Okay, I hope it is clear now. Now let's do the last one. 0.08 pu on a 10 MVA base and 13.2 kV base with secondary short circuit and tertiary open circuited. Okay, so we have measured 0.08 per unit on a 10 MVA base, 13.2 kV base, 10 MVA 13.2 kV base with secondary short circuit and tertiary open. Secondary short circuit, tertiary open. So it is basically ZP. Sorry, this is incorrect actually. This is incorrect. It should not be secondary short circuit. It should be ZST actually. So it should be primary open, tertiary short circuit. Sorry, mistake. Tertiary and primary open. Okay. Okay. This is ZST pu equals to 0.08, right? And of course, if we are keeping the tertiary short circuit and we are keeping the primary open, that basically means we are measuring at the secondary. So this has been measured in the secondary. Now the problem is here, right? We have measured in the secondary and the base used also have been used in the secondary. Base has been used, the base that has been used is the of the secondary. So one very interesting fact that we want to understand is, let me take a single winding transformer. Okay, so if I have a single winding transformer, what is the Z base in the primary? Z base in the primary will be, it is S base, like S is same for single, like not single, two winding transformer, the kVA MVA rating is same. Okay, so S is same, so yeah, and the voltage here will be V1 and V2. Okay, voltage here is V1 and V2. So what will be the Z base on the primary side? It will be S upon V1 whole square. And what will be the Z base on the secondary side? It will be S upon V2 whole square. Now let's take a case. Let's assume that I have a Z2 impedance here, right, on the secondary, Z2 impedance. And if I refer it to the primary, right, what will be the value? It will be Z2 dash. So what is the per unit value here? The per unit value here will be Z2 PU will be equals to Z2 upon simply Z base on the secondary side, that is equals to my Z2 upon ZB2 will be equals to Z2 is the actual Z2 value, and this will be S into V2 whole square. Okay, that is sorted. This is my Z2 PU. Now here on the primary side, if I refer it, right, if I want to write in the primary side what will be the PU, so what is my Z2 dash in the primary side? Z2 dash will be what? It will be V1 upon V2 whole square into Z2, correct? What will be Z2 dash PU? It will be Z2 dash upon ZB1 because it is on the primary side. So this will be V1 upon V2 whole square. Okay, V1 upon V2 whole square into Z2 dash, right? So what is into Z2 basically, because Z2 dash is V1 upon V2 whole square into Z2 divided by the Z base 1, that is S into V1 whole square. Am I correct here? Sorry, yeah, am I correct here? Sorry, I wrote the base, that's why you don't remember the formula. I wrote the base opposite. Sorry. This will be opposite, right? Sorry. So this PU will be, S base will be here, V2 will be here. Yeah, sorry about that. So here okay, so here V2 just give me 1 second. So if I am dividing, so this will be V1 whole square into S. So basically this V1 whole square gets cancelled. So ultimately your value comes out to be Z2 into S divided by V2 whole square, which was the previous value, right? Z2 divided by V2 whole square into S, that is basically equals to Z2 PU. Okay, Z2 PU. So now yeah, now what we can discuss is, here I can say safely that Z2 dash PU is same as Z2 PU, but things will change now. If let's say it's a 3-winding transformer, then things will change. So if it's a 3-winding transformer and then the kVA VA rating is different, then things will change. So if I have a 3-winding transformer, right, if I have a 3 winding transformer, and let's say like I'm talking about the secondary side. So here again the same case, I have a Z2 impedance here, okay, and this is V1, this is V2, this is V3, and this will be S1, because now the ratings will be different. Why? Because this is the primary, I'm delivering let's say 15 MVA, 10 MVA will go here, 5 MVA will go here, right? So I will write here S2, this will be S3, S3. So now the base are different actually, because the S has changed. So here what will be the base? Now for multi-winding transformer actually the referred impedance always will not be equal. So here there comes a contradiction, and this, trust me, no one will teach in the whole industry. No one, like they will not even take this, they will not even take multi-winding transformer, okay? They will just use some, they will give you the small formulas, easy formulas, and that's it. No one will teach you this concept. You go and check anywhere else, you will not find this concept. So Z2 is here, okay. What is the base here? Base of the second like secondary winding, number 2 winding, it will be V2 whole square upon S2. Here ZB1, sorry, ZB3 will be V3 whole square upon S3, and your ZB1 will be equals to V1 whole square divided by S1, okay. Now the important fact is, what is the Z2PU? Z2PU will not change, right? Z2PU will be Z2 actual upon the ZB2 upon ZB2. So it is equals to Z2 into S2 divided by V2 whole square. It's very simple and easy. Now what about the Z2 dash PU referred on the primary? If I am referring on the primary, what will be Z2 dash? If I am referring on the primary, it will be V1 upon V2 whole square into Z2. So this will become V1 upon V2, right? So V1 upon V2 will be equals to V1 upon V2 okay, so this will be Z2 dash upon ZB2, okay, sorry, ZB1, right, because it is referred to the primary side. So this will be equals to Z2 dash is V1 upon V2 whole square into Z2 divided by ZB1 is V1 whole square divided by S1, okay. So here V1 whole square gets cancelled, so I get the value as Z2 into S1 divided by V2 whole square. Now is this same? Is this, are not this, are these two the same? I am observing here I have S2, here I have S1, so they are not the same actually. So their per unit values also are not same. Their per unit values also are not same, okay. So very key point, very important point, I will explain this, don't worry, because the S base has been changed, that's why. If the base here, if this was also 15 MVA, this was also 15 MVA, then the per unit values would have remained same. But this is 10 MVA, this is 15 MVA, that's the problem. There is the mismatch, that's the problem, right? For a 2 winding transformer, the base rating was same, so there was no problem. So here if I take the ratio of Z2PU dash upon Z2PU, what is it equals to? So basically everything will get cancelled, because actual value of Z2 is same, V2 whole square is same, but S1 and S2 are different, so it will be S1 upon S2. Very important point, no one will explain you this. Go and find anywhere else, like I'm telling you, any famous coaching, anywhere else you go, they will not go in depth, they will not explain you, like they will not even teach this. They will not even discuss, they will not even take the word of 3 winding transformer. Okay, so here now what is a key point, very important point. For a 2 winding transformer, for a 2 winding transformer, the per unit impedance will be same on all windings. Okay, but for more than 2 windings, okay, if number of windings is greater than 2, then per unit impedance will change as the S base has changed. So it's like it follows the same relation basically. Previously also we have discussed, right, that if I am changing the base, then my new per unit, new PU will be directly proportional to the base, right, new base. So basically it's same formula, it's similar formula to this one. If you remember, Z2 PU new is equals to your Z2 PU old into S new upon S old. Same formula, right? We have used this. So same thing we will do here. So explaining this was actually pretty important. So here also same thing is happening. So this, right, all these are fine because all these are measured in the primary. So in the primary the base is 15 MVA only. Okay, but here the base is 10 MVA. But I have to, because I have to draw the, what they are asking, determine the per unit impedance of the star equivalent circuit of the transformer referred to the primary side with base 15 MVA. So I have to refer it to the primary side. So if I am referring it to the primary side, here is my here is my XP, here will be my XT, here will be my XS, right? All dots are together. So if I am referring it to the primary side, then I have to use that referred formula because the per unit value will change. So this ZS TPU, because it is measured in the secondary, I have to refer it to the primary. That will become your ZST PU dash will become the old value 0.08 into the new base, that is 15 MVA upon the old base. Old base is what? It is measured in the secondary. Secondary has base of 10 MVA. So this will be 3 by 2. So 3 by 2 is 0.12. Okay, 0.12 pu. Okay, so it's very important. This point is very important, and I have explained this. I have spent 10 minutes to explain why this will be there. Even if someone teaches this, right, they will not explain this much. Okay, they will not explain all this. I have done every single thing, every single analysis, every single doubt that can come to your mind. I have tried to clear that. Okay, so yeah, I have got my values. Now it's very simple. What is XP? What is XS? What is XT? Is very simple, right? XP will be what? So okay, let me take a new page and let me draw the circuit again. Let me take these values and let me take these values as well. Now I can easily find out what is my Z, because it is leakage reactance only, it is not actually X, it is not actually Z, it is X, right? Sorry about that, it is not Z, it is X, because it is the leakage reactance. So okay, okay, so now I can easily find out what is my XP. It's very simple, right? Finding out XP will be simply half into XPS plus XPT, right? XPT minus XST dash. Okay, so this will be half into 0.07 plus 0.09 minus 0.12. So this will be equals to 0.16 minus, so 0.04 divided by 2, 0.02. P. Okay, this is what your XP is equals to. Okay, this is what my XP is equals to. Now we can easily find out what is my XS, right? What is my XS? So XS will be half into, how to remember, it's very simple, just write down whatever is here, right? Write that down 2 times. So X PS is there, plus what is the another term? XST, that is dash. Okay, so these two must be there, S must be there twice with addition sign, and the other must be with negative, because we have to eliminate T and P. So minus XPT, very simple, right? That's how you remember the formula. Anyways, you can derive it, it will hardly take you 30 seconds, 40 seconds. So half into XPS is 0.07 plus XST dash is 0.12 minus XPT. XPT is 0.09. Okay, so this value will be equals to okay, let me calculate this value. 0.19 minus 0.09, 0.1, 0.05 pu XS. Okay, what about XT? XT will be half XPT plus XST dash minus XPS. So XPT is 0.09, I guess. Yeah, half into 0.09 plus XST. XST is 0.12. Uh, 0.12 minus XPS, that is 0.07. Okay, so this will be equals to yeah, so 0.21 minus 0.07, so it is 0.06. Oh, no, it is 0.06. No, it is 0.04, right? So 0.14. Yeah, 0.14. 0.14 divided by 2, that is 0.07 pu. Okay, so your XT comes out to be 0.07 pu. So like this will be 0.07, this will be 0.05, this will be 0.04. Okay, so I hope it is clear, and trust me, no one will even dare to take this question and explain this question. Okay, so yeah, let's now move. This is actually a book question, this is question from book. Okay, famous book, I think it is a question from Stevenson. Okay, if I don't remember it correctly, this question is from a book named Stevenson, right? That the book that I am following basically. Okay, so let's now move on to the next part, next question. So we have a 3 winding. Okay, this is the same question only. Okay. Sorry. I copied the same question twice. That's my bad. Oh, no. Okay, this is the second part of the question. Sorry. So, okay. It's the same question only, but this is the second part. Okay, second part. So, all this we have already discussed. An infinite bus with constant voltage source supplies a system of a purely resistive load at 5 megawatt, 2.3 kilovolt. Okay, and this load as well. It is supplying two loads. So, I have basically this thing I have. It's the same common data question. It is the part 2 of the question. Okay. So now they are asking me that an infinite bus with constant voltage source supplies a system of purely resistive load at 5 megawatt, 2.3 kilovolt. So this 5 megawatt load is connected to the 2.3, that is to the tertiary winding. So here the load is connected 5 megawatt load. Okay, it's a static load. Okay, it's a static load. Now another load is connected to 13.2 kilovolt side, that is 7.5 MVA. So this load is connected 7.5 MVA. Okay, 7.5 MVA synchronous motor. So it is a motor. This is a motor, and this is a simple load. Okay, with subtransient reactance, that is 0.2. So you ignore the subtransient part, just understand the reactance of the motor is 0.2 pu. That's the reactance of the motor. What they are asking now? So the source is connected to the primary side of the transformer. Basically source is connected to here. So here the source is connected. Okay, and the loads are connected as follows, like we can understand from the voltage rating only. Determine the per unit impedances of the star connected equivalent circuit of the transformer referred to the primary base of this. So again I have to draw the per unit impedance, but this time all this loads are also connected. So already this is there. So this circuit is already there. We have already solved this. This will be there, but with this a source will be connected to the primary. So source will be there, and as it is rated voltage, it will be 1 pu. Okay, I don't know what is the angle they have not given me, and I know a static load is connected on the tertiary winding, between the tertiary winding here and the neutral wire. This is the neutral wire, right? And a motor load is connected over here. Okay, so this is a motor load, so it will have its reactance, and of course it will have its voltage. I don't know what is the voltage, EM I will write here, and the reactance they have given me is J0.2. Now remember, this J0.2 is in the secondary side, right? So this will not be same actually, because I have to refer this in the primary side. Again this will change, same rule, right? So what will be my XDPU in the primary side? It will be 0.2 old value into the new base, that is 15, divided by the old base, that is 10. So again it will be 3 by 2. So this will be 0.3 pu. So yeah, sorry for the interruption. Like the recording got stopped for a second. So this will be 0.3 pu. So this, right, refer to the primary side. Simply I'm just referring the reactance, right? If I have a reactance on the secondary side, if I refer it to the primary side, just the it will be changed with respect to the base MBA base. The voltage rating automatically gets uh, covered, right? Because that is the inherent property of transformer. Now let's solve it for this load, right? So they have given me that the load is a purely resistive load. If you see, it is a purely resistive load. So it is just a R. It is a purely resistive load. It is just a R. So it is just consuming 5 megawatt and 2.3. 5 megawatt at 2.3 kilovolt. So what will be the resistance, actual resistance value? So it is a purely resistive load. If it is a purely resistive load, I know the power consumed by a purely resistive load. And remember, it is a delta connected purely resistive load. So here it is a delta connected purely resistive load. So R R R. Okay, so this will be like I'm providing it the voltage. What is the voltage? Voltage is 2.3 kV, and the power basically is power they have given me, that is 5 megawatt. It all of this are consuming 5 megawatt. So basically each resistor is consuming how much? 2.3 V square by R, right? Megawatts. And I have 3 resistors, so it will be 3 times 2.3 V square by R will be equals to the overall power consumed, that is 5 megawatt. So this is kilo whole square and mega automatically gets cancelled. So this will be equals to, so my R I can directly find out here will be equals to 2.3 whole square divided by into 3 divided by the power consumed is 5 megawatt, 5 megawatt, right? So 5 megawatt. Okay, so this is the value of the resistor. Now if I want to write this in, this is the actual value. If I want to write this in per unit, what will be the per unit value? So the per unit will be very simple. It will be R upon Z base. So what is the Z base on the this delta on the tertiary side? On the tertiary side, what is the per unit impedance? So my Z base on the tertiary side, right, will be equals to Z base on the tertiary side will be equals to this S V base on the tertiary side whole square divided by S base, right? V base on the tertiary side divided by the rating of the tertiary side. So it is V base is 2.3 only, because on the tertiary side the voltage is 2.3 kilovolt and the S is 5 MVA. So 2.3 whole square divided by 5 MVA. So automatically I see that this factor is already there. So I have to divide by Z base, right? So automatically this will get cancelled if I divide. So automatically this value will be 3 pu on the tertiary side. Now I want to refer it on the primary side, because I have to draw the circuit in the primary side, right? That then only this value will be RPU. So this will be some RPU, right? So what will be this RPU on the primary side? Again, same relation we have to follow. RPU new will be equals to RPU new will be equals to RPU old multiplied by the S new, that is 15 MVA, by the S old, that is 5 MVA. Previous base, tertiary base was 5 MVA. Where is it? 5 MVA, and the primary base is 15 MVA. So this will be 9 pu. So the resistance referred to the primary will become 9 pu. I hope that is clear. So this will be 9 pu. on the primary. Okay, so yeah, this is the equivalent diagram basically. So I hope everything is correct here. V square by R, they are telling me it's a load connected 5 megawatt load. So yeah, V square divided by R into 3, because that's each per phase power into 3 will give me the overall power. So R will be 3 times this. Yes, correct. 3 pu will come. Yeah. So this is the circuit diagram basically. They have just asked you to draw the circuit diagram. We have drawn the circuit diagram. Actually, we don't know what is the potential of the this voltage source and the this motor. So we have just drawn the impedance, because they have asked, if you see, just draw the per unit impedances. So I have drawn all the per unit impedances. These were already calculated. We just drawn the other two parts. This is again from the Stevenson book, part 2 of the Stevenson book. Okay, you can go and have a check. I think I have mentioned in the starting of this course which books I am referring. Okay, so let's now move and solve this last question. So is this the last question? I guess no, few more. Okay, few important points are there, then we will wrap up today's lecture basically. So again, this is another question. So where a 3-phase star connected generator is rated at 150 MVA 11 kilovolt with a per unit impedance ZS is equals to this value. Okay, so if I draw the per phase equivalent right here, it has a per unit impedance ZS equals to 0.1 pu and reactance of 0.5 pu. Okay, it delivers a power output of PPU at terminal voltage VT equals to 1 pu. Okay, so it delivers, the terminal voltage here is 1 pu, 1 angle 0, and here it delivers the power. What is the power it delivers to a load? The power that it delivers is 0.9 pu. That is the power in per unit, active power. At 0.8 lagging, so the power factor is cos phi is 0.8 lag. Now what is he asking? Recalculate the following values in the new base. Okay, in 100 MVA and 9 kV. So if I want to recalculate everything in the new base, what will be the values? That is what they are asking. Okay, so the values, the base was 150 MVA and 11 kV. It is just a simple exercise to convert to new base, right? If I want to convert everything into new base, so okay, so can you tell me what will be my EG? Because here the terminal voltage is 1 angle 0. I don't know what is my EG. So I have to recalculate everything, recalculate the following. So recalculate the per unit impedance, the per unit real power and the reactive power, terminal voltage and the power factor. Okay. So they don't want me to find EG, so I will not find EG, but there can be also, like, the fifth point will be to calculate terminal voltage and the generator voltage. This is additional question. So first of all, let me find out what is EG. EG will be equals to what? EG will be, let me assume that here some current is flowing, I. So EG will be equals to 0.1 plus, like, I can write this formula, right? So my I will be equals to EG angle, let me assume this as some angle delta minus VT angle 0, that is 1 angle 0, divided by R plus J 0.5 pu equals to I. How do I find out I? This is a vector quantity, I angle theta, right? So I know the power, I know the voltage. Will I be able to find out I? Oh, definitely. So I will be equals to what? V P upon Vpu. Magnitude of I will be V upon Ppu, right? Okay, no, I made a mistake. So I know what is my power. Power is Vi cos phi. So in per unit, it will be Ppu, Vpu IPU cos phi, right? Power factor does not change, already have been proved to you, right? So I can directly find out what is my IPU. IPU will be, I'm talking about the magnitude only. So magnitude of IPU will be equals to PPU 0.9 upon cos phi, that is 0.8, into VPU, that is 1. So it is 9 by 8. 9 divided by 8. 1.125. 1 point. So this will be IPU. Okay. So this is the magnitude. So what will be the actual IPU value with phase angle? It will be magnitude 1.125, angle of, it is lagging. So cos inverse of 0.8, right? Cos inverse of 0.8, it is I think 36.86 minus, because it is lagging, right? So it will be minus from the terminal voltage, minus 36.86. So here this will be, so from here I can easily find out what is my EG. I can easily find out what is my EG. So my EG angle theta will be equals to, okay, this I can convert into polar format, 0.1 whole square plus 0.5 whole square whole under root 0.51. What is the angle? Angle will be 0.5 divided by 0.1 tan inverse. .69 degrees. Okay, so my EG angle theta, EG angle not theta, sorry, delta will be equals to this 0.151 into this value 1.125. So 1.125 into 0.51, this will be equals to 0.57375 angle. It is 78.69, it is minus 36. 78.69 minus 36.86, so it will be 41.83 degrees plus 1 angle 0, right? So this will be cos of this, right? So cos of this is 0.7451 into 0.57375. The real part comes out to be 0.4275 plus j. So this will be 41.83 sine into 57375, 0.82 3265 plus 1 angle 0. So this will be basically 3.3, so 1.4275 plus j 0.38265. So E angle delta, right? 1.4275 whole squared plus 0.38265 whole square whole under root. So 1.477. What is the angle? Angle will be 0.38265 divided by 1.4275 tan inverse. So it comes out to be 15 degrees. So this is my EG angle delta, correct? But now I am changing my base, right? I am changing everything. So I am changing everything, right? I am changing, the new base is 100 MVA and 9 kV. So what will happen to all these new values? So my angles will remain same. So I have already told you that angles do not change, but values will change. Okay, magnitudes will change, magnitudes will change, magnitudes will change. Okay, so now what will be my, so first of all what they are asking, first of all they are asking per unit impedance, new per unit impedance, new per unit impedance. So they are asking basically this impedance, right? New synchronous impedance. So ZS new, again I will use the same formula. ZS new will be equals to ZS old multiplied by S base new divided by S base old into V V base old divided by V base new. So V base whole square, V base whole square. Okay. So yeah. So now the thing is, so ZS old is 0.1 plus J 0.5 pu into S base new. S base new, S base new, S base new is where? S base new is given me is 100 MVA and the old S base was 150 MVA. So 100 upon 150 into V base old. V base old was 11 kilovolt and the new V base is 9 kilovolt. So 9 upon 11 whole square. So this will be difficult to calculate. Okay, so it is stressful, but I will try my best. So 100 upon 150 into 9 divided by 11 whole, okay, not 9 divided by 11 whole square into 100 divided by 150, that is 0.4463. This will be equals to into 0.1 plus J 0.5. So into 0.1, this will be 0.0 and divided by 0.1 into 0.5, so it is J 0.223. Okay, so roughly I will have my, so new EG, I will write the EG value, don't worry. The new resistance will be 0.04463 and the new reactance will be J 0.223. Okay, and what will be happening to the terminal voltage? So for the terminal voltage, what has changed? The base has changed, the voltage base has changed, right? So will it still be remaining same voltage or it will change? It will change, right? Because what was VTPU? VTPU was equals to VT actual upon V base. So this formula is applicable for impedances or reactances or resistances, right? But for voltage, what will be the formula? For voltage, VT actual will not change, base has changed. So if I again, let's say this is my old, right? VT old, this actual value will not change, this is VT base old, and I will have the same thing for the new base, right? New. So if I divide this, right, so VTPU or VPU new will be what? If I just don't try to mention this with respect to a terminal voltage only, any random voltage, if I'm changing the base of that, then what will happen? Basically VPU will become VPU new will be equals to uh, if I'm dividing, right, so VPU old into VPU old into V base old upon V base new. Okay, so this will be the result. So I know what is my VPU old, that is 1 into V base old. V base old base was 11 kV, new base is 9, so it will be 1.11 basically. So 11 divided by 9, sorry, 1.22. 1.22. So anywhere else, if you ever tend to forget the formulation per unit, just simply take out the ratio, that's it. 1.22 3 pu. Okay, now this is the this was actually the third part, right? Terminal voltage, this was the third part. Before that I had to find out the real power. Sorry, I just went off track. So the terminal voltage here is, the terminal voltage here will be, just give me 1 second, terminal voltage here will be 1.223. Now one important fact, does the angle change? So if I want to test the angle here, does the angle change? So what is basically the impedance angle? Tan theta z, tan theta zs, does it change? So tan theta zs will be equals to what? It will be 0.223 divided by 0.044628 tan inverse. So it comes out to be like theta zs from here, theta zs new comes out to be 78.68 degrees. Is it same as the previous one? It will be same. If you want to confirm, you can. So here this was the theta zs old, right? So theta zs old, so this will be 0.5 divided by 0.1 tan inverse, and you will get the same value, 78.69. so your angle actually will not change, angle will be same. Okay, angle will be same. I will prove it to you, don't worry. So here it will be 1.223 angle 0, angle will not change, this will be same here. And okay, now this is my VPU. Now I will, like, this was the second part actually, I will add a page here. This was the second part, this was the first part, this was the first part, this was the third part, and I will solve the second part now. In the second part they are asking me the power. So what will happen to the power per unit real power and reactive power? So what was the reactive power here previously? Real power I knew, PPU. What was the reactive power? So reactive power Q will be equals to what? It will be simply P upon, it will be P tan phi. Very simple, right? Because I know Q by P is S sin phi upon S cos phi. SS will get cancelled, it will be P tan phi. Like, I hope you know this, but if you don't know, just in case, Q is equals to S, this already has been taught in the network theory courses, Q sin phi, and P is equals to S cos phi. So my Q by P will be simply tan phi, right? So then you can directly write Q is equals to P tan phi. So if I want to calculate this, so cos phi is, so it is 36.86 tan of angle into P, that is 0.9. So reactive power comes out to be 0.69 and it is actually lagging, so it will be positive. Reactive power will be positive, it is lagging, right? So it will be lagging. Reactive power, it will be positive. Okay, this is my like old reactive power. I want to find out the new reactive power. Of course I will calculate that. Okay, so the new reactive power will be what? So let me first of all calculate the new power. What is the power? So power is simply Vi cos phi, right? So it is P actual upon S base, right? We divide by the base MVA basically. So S base has changed, it is not voltage dependent. So sorry, PPU is this, right? PPU old, actual power will not change upon S base old, right? Again, if I take the ratio, PPU new will be what? It will be the same value only, just the base will be new. So PPU new will be okay. PPU new will be PPU old. If I divide these two equations, this P actual will get cancelled. It will be into S base old divided by S base new. Now see, right, I am not telling you to remember any formula. No formula. Simply use concepts. Simply use concept. That's it. Okay. No formula. You just use concept. S base into S base new. So this value will be equals to, like I already know what is the old PPU, that is 0.9 into S base old. S base old will be S base old. What was the old S base? It was 150 MVA and the new S base is 100 MVA. So 150 by 100. So it is 3 by 2. 3 by 2. 3 by 2 into 0.9. So 1.35. Okay, 1.35 pu. So this is my PPU new. So now yeah, now yeah, this is my new PPU. What is the QPPU? QPPU also will, like, it will be same formula only. QPU old into this S base old divided by S base new. So QPU old was, we had just calculated, it was 0.67. So this will be 0.67 into S base old. S base old is 150 divided by 100, right? So this will be 0.67 into 150 divided by 100. So it is 1. It comes out to be 1 pu. So your Q comes out to be 1 pu and your new P comes out to be 1.35. Okay. So here the power, okay, what is the circuit diagram? So the power that the load will take, it will be 1.35. P will be 1.35 pu. Okay. And Q is what? Q is 1 pu. So let me again calculate the power factor, or let me calculate the tan phi, right? Tan phi will be what? Q by P. So this ratio will be same. Angle values will not change. This will be 1.35. So this is 0.744, which is tan inverse if I do the angle comes out to be same. Psi is same, 36.86 degree. So angle will not change. Angle will be same only. Angle will be same. Okay. Now what are they asking? Voltage we have already calculated. This is done. Generator voltage. Same formula for generator. I know the magnitude. Angle will not change, and I will prove it to you why angle will not change. I have already proven. Again, I will show you another result. So Eg comes out to be this 5.5735. So Eg new, right? Same formula I will use here. So VBS will not change. This will be Eg new. Okay, Eg new. So Eg old is this value, right? Eg old I have already calculated. It's point. Sorry, this is okay. This is the This is the Eg old, right? Sorry. This is the Eg old, not this. This is the Eg old. So it is 1.4779. 1.4779. That is basically 1.78, right? Into V base old, that is old is 11 kilovolt and new is 9, right? So this will be 11 divided by 9 into 1.478. So it comes out to be 1.8, right? So I will just bring the circuit over here so that you are able to understand this. What happened? Automatically this got deleted, huh? What happened? Okay, something got deleted. So it was 1.478 into 11 by 9. For some reason it got deleted. Okay, comes out to be 1.806. So this value is 1.806. Now you might have a doubt that will the angle be same, because delta, previously the delta that we calculated was 15 point something, right? Here the delta, where is the delta? It was 15 degrees, exactly 15 degrees. So I will paste it over here, 15 degrees. Now let me find out the I current and let me see the let me see what happens. What is I? So what will be I? I will be Eg new upon delta minus Vt new upon whatever the impedance that is shown here, that is Zs new, right? So if I write this in phasor, this thing in phasor, right, that will be easier for us. So this thing in phasor will be 0.223 whole square plus 0.04463 whole square whole under root. So this comes out to be 0.2274221. Angle is 0.223, 0.04463. So tan inverse, so it is 78. Point 0.68 degrees. Okay, 78.68 degrees. So this is the impedance basically. This I will replace here. So this will be 0.0227442. Angle is 78.68 degrees. And Eg angle delta is 1.806 15 degrees. 1.806 15 degrees minus Vt. Vt is this, right? 1.223 angle 0. 1.223 angle 0. So okay, so 15 cos into 1.806, sorry, 15 cos into 1.8, sorry, 1.806. So it is coming out to be 1.774744, right? And 15 sine into 1.806, so it is plus j 467.4 minus 1.44 minus 1.223, so so point, okay, this whole squared plus 0.4674 whole square point, okay, this is 5.521, right? So this comes out to be, okay, I have to under root, so point, how is it, okay, sorry, squared under root, this comes out to be 0.7 angle, so what will be the angle, 0.521, sorry, 0.4674 divided by 0.521 tan inverse 41.89 degrees divided by this, right, 0.2274 78.68. So this angle, if I subtract 78.68, so if you are observing that your angle is minus 36.86, it does not change, your angle, current angle does not change, right? Whatever you do, current angle will not change. Here also, previously, what was the current angle? Here, minus 36.86. So again I have proven it to you that current angle will not change no matter what, but the magnitude of the current will definitely change. Magnitude of the current will definitely change. So what will be the magnitude? Magnitude will be 0.7 divided by 0.2274. So it comes out to be 3.08 pu. Now can I without solving, this was the method 1 to find out the current. What is the method 2? Method 2 is simply reference, right? I know what is my IPU. What is my IPU? IPU is basically I actual upon I base. Now I base is what? I base will be I upon S divided by V, right? S divided by V. So V base upon S base. Right? Here root 3 will be there because it is root 3 VLIL, right? So root 3 into V. Right? Basically it is like, I know this relation, S is equals to root 3 into VL IL, right? So I am just replacing IL with S by root 3 VL. Okay, this is my IPU. This is my IPU. So I can directly say here what will be my this is my old IPU. Let's say this is my old IPU. So basically it is dependent on both voltage and the rating. So IPU old will be I into root 3 upon S base old. So I will be the same thing only. I'll just change it to the new value, right? So again I can take the ratio. So basically my IPU new will be basically IPU old. I'll add another page. IPU old into, now I'm taking the ratio, right? So okay, VB new upon VB old. VB, so first of all S will be there, SB old upon SB new into VB new upon VB old. I'm not telling you to mug up anything, just solving everything conceptually, right? Of course it is taking me time to explain, but for you it will not take much time. You will quickly able to do it. Okay, so now what is my IPU old? IPU old was 1.125. So 1.1, I'm just talking about the magnitude. Of course the angle will not change. So what is happening, man? What is weird bugs? Okay, IPU new equals to, this is like, this is already I'm very hectic and it is giving me more pressure. This thing, man, what is the bug? Okay, sorry about that. So yeah, is the voice and everything okay? Hello. Yeah, I'm just checking because it's been a while. I'm recording for a while. So yeah. Okay. So here this becomes IPU old. IPU old. Okay. IPU old is 1.125. S base old. It was old base was 150. New base is I think 100, right? And V base new is 9 and old is 11 if I am not mistaken. Yeah, new base is 100, old is 150, new is 9. So new base is 100. Oh my god, what is happening? Oh my god. Something like the iPad is also working, like the tablet is also working constantly, right? I think it has heated up. This is also not able to take the pressure. Only humans can take the pressure. The machines also they also tend to, like when they are overworked, they also give up. They are also giving up basically. Okay. Okay. So this is 1.125. Old is, yeah, 150, new is 100. So this comes out 150 divided by 100 into 9 divided by 11 into 1.125. So 1.38. 1.38 IPU new is 1.38. Is this what we calculated? 1.38. What is it? No, this is not what we calculated. So there is something wrong. What went wrong? Okay. Something went wrong. Something went wrong. Okay. Something gone wrong. I'm just trying to understand what went wrong. Angle is same. How the magnitude is different? Huh? This is minus here 0.5, so this will be 0.7 only. Yeah. Okay. This is 100 upon 150 upon 100. Okay. What is happening? 1.125. Let me do this once again. 150 upon 100 into 9 divided by 11 into 1.125. 1.38. Okay. So what I'm messing up here? So here the VT is 1.223. Angle will not change. This will be same. Angle will not change. So this will come out to be 1.806 into cos of 15. So 1.806 into cos of 15, it's 1.744, okay, minus 1.223, that is 5.21, exactly correct, whole square. So let me do sine of 15 into 1.806, it is 0.46 only, whole squared plus 0.521 whole squared whole under root 0.7 is coming. Okay, everything is correct, only what went wrong? Okay, okay. Did I calculate the impedances? Okay, what is happening? This machine is dying, right? Okay, let me just pause the video for a second. Okay, I'm extremely sorry. Here I made a big mistake. I know you guys were screaming at me. So this right here, Z base old should be there. So old base was 11, new base was 9. I'm sorry. But again, the angle will come out to be same. Why? Because I'm just multiplying a constant number. This defines the ratio, right? This defines the angle. So I'm just multiplying a constant. Multiplying constant won't change the angle here. Okay, I'm sorry. I'm extremely sorry. So it will change actually. This value will change. This will be 11 divided by 9 whole square into 100 divided by 150. So it is almost 1. It is almost 1 actually. This is almost 1. Okay. So the value per unit impedance does not change actually. This will be same. So basically the per unit impedance also is same only. So it does not change. So angle obviously will be same only. Okay, my bad. I am really sorry. Angle will be same. Angle will not change. Okay. So there is very slight small change, that is negligible, right? So this will be okay 0.1, am I correct? Yeah, 0.1 j 0.5. So this will be j 0.1 j 0.5, I'm sorry. So this right, if I calculate the values here, this will come out to be 0.1 whole square plus 0.5 whole square whole under root, so 1.15. So this will be 1.15 1.15 angle 78 degrees, 78.68, right? So this will be here, this will not be correct, this is not correct, this is 1.15 1.15, okay, 1.15. Am I absolutely correct here, or again I'm messing up something? So how is this 1.15? What am I doing? What am I doing? I'm sorry. 0.5 whole square plus 0.1 whole square whole under root. Sorry, it is point. What am I doing, man? So this is actually 0.51. This will be same 0.51. So this will be 0.51. So this will be this into 0.7. So it comes out to be almost 1.38. Okay. So this comes out to be the per unit value. So you can observe it is the same, right? This 1.38 and this 1.38 is same. I had mistaken. Okay, again this is doing. What is it doing, man? I have to restart. We're almost done. We're almost done. It will mess up my notes. Okay. I hope it is not messing up anything else. If I'm moving my screen, right? If you see previously the current was here. Okay, sorry. Previously it was 1.125. It here also should be 1.125 only. Why is it 1.38? It should not be 1.38, right? Just give me a second. 0.7 divided by 0.51. It is 1. It is coming out to be 1.38. Again, what am I messing up? This is 0.7 only. This will not change. This magnitude is coming out to be something else. Because from here, if I calculate the magnitude, right, current magnitude, this is coming out. So this is not okay. This is wrong again. This is 0.01, and this is this is 0.1. This is 0.5. But the voltage base has been changed. Everything base has been changed. I don't understand what is going wrong here. Oh, sorry. So sorry, we calculated the new I per unit, right? So the value of I per unit, it will not be the old one, it will be the new one, right? Because now the base has changed. So yeah, it is coming out to the same 1.38 here as derived, right? And here also, I'm really sorry. I was just in some other mind. So this question is long actually, and I've been recording since like 2-3 hours, and it's night at like I don't want to say, it's like 4 a.m. I have to finish this anyhow. So that's why. So I hope it's done. Okay. हो जाता है कभी, इतना स्ट्रेस रहता है, इतना कुछ तो हो जाता है. So this question is done. So I hope everything is crystal clear from this question. Everything we have done, I have proven it to you. How does the angle remain same? Okay. So I just want to end this lecture, and before ending, I just wanted to mention few important points. The first point already have been discussed in the machines, synchronous machine chapter, that the power flow, active power flow happens due to the angle difference. So if my generator will be at higher angle, whichever voltage source will be at higher angle, that will deliver power, and whichever voltage source will be at lower angle, that will receive power. Okay, this has been discussed in the synchronous machines chapter. So your power formula is V1 V2 by x into sine delta, but delta is the angle difference. So this will be used in many places, in fault analysis, everywhere this will be used. So that's why I am just giving you a quick recap. And reactive power, basically, so here not reactive power, let us first discuss about the active power only. So here, what will be the direction of the active power flow? So direction of the power flow will be from the voltage source to the motor. So this is a motor and this is a generator. So in this case, your delta angle will be positive, because this must be at higher angle, this must be at lower angle. In this case, as it is a motor, my delta must be less than 0, because my angle must be lower than the angle which is sending. So sending end angle must be higher than the receiving end angle, so that it can receive the power. So that was about the active power. What about the reactive power? So reactive power is control, like I can control, if I am able to control the reactive power, then I will be able to control the voltage difference. So reactive power flows from the higher voltage to the lower voltage. Okay, this already has been discussed. So roughly your reactive power is proportional to delta V. I have discussed this in synchronous machine, so I am not explaining the formula. All this I have derived in the synchronous machine chapter. Okay, so your reactive power transfer is proportional to delta V. Reactive power transfer is proportional to delta V. Okay, so I hope you have understood this point, that it is proportional to delta V, right? So these two things we will utilize everywhere in power system. So this is a very important point to understand. Now star and delta connection. So in star connection, a few important points you must understand, that your phase voltage will be at, let's say if I assume my phase voltage is at V angle 0, then my line voltage magnitude will be √3 times the phase, and it will lead by 30 degrees. Already has been covered in the basics of three-phase system. I have already covered this in the basics of three-phase system. Okay, so this is relation about the phase voltage for a star connection. And what about the current? So for current, I phase and IL are equal for star connection. So line voltage will lead the corresponding phase voltage by 30 degrees for star connection. If it is negative phase sequence, if it was positive phase sequence, then the line voltage leads the phase voltage by plus 30. If it is negative phase sequence, line voltage will lag the phase voltage by 30 degree. Again, why is this important? Negative phase sequence, this will be important in symmetrical or in unsymmetrical faults. Unsymmetrical faults. So please, these are just like short notes, few key points I am telling you. This will be utilized later on. Okay. Now why is star preferred on the HV side? Star is preferred on the HV side because the coil voltage reduces by √3. So the insulation requirements for the coil reduces by √3. That's why star is preferred in the high voltage side. That's why star is connected commonly in the high voltage side. Okay. By default, if nothing is mentioned, you will assume star. So assume star. Star on the HV side, if nothing is mentioned. Okay. Delta connection. For delta connection, it is just opposite. It will be just dual. So for delta, voltage is same. So V line voltage and V phase voltage will be same. But for delta, the line current will be √3 times the phase current. But this time it will not lag, it will not lead, it will lag. So for the positive phase sequence, it will lag. So the line current lags the phase current for positive phase sequence. So line current lags phase current by 30 degree for positive phase sequence. If it is negative phase sequence, line current leads phase current by 30 degrees. If it is negative. So star and delta are just dual of each other. But if you are in per unit, you don't have to worry anything. Everything gets converted into per phase equivalent. Okay. Line, star, delta, everything is converted. Transformer impedance. So I know that your ZPU is remains same on both sides. So basically your ZPU on the primary side, ZPU1 will be equals to ZPU2. So what is ZPU1? ZPU1 is basically equals to Z1 plus Z2 dash divided by Z base in the primary side, and ZPU2 equals to Z2 plus Z1 dash divided by Z base 2. So all this will remain same, it will not change. Okay, all this will remain same, it will not change. So this we have already discussed. I'm just giving you a quick recap. Okay, so and one more important formula about the impedance. So ZPU new, this, right, all these are useful, that's why I'm giving you a summary. I'm just summarizing the whole chapter, right? So ZPU new, this will be utilized everywhere. If you ever tend to forget the formula, you can always derive it, right? I have derived hundreds of times in front of you. Okay, so ZPU old into S base new divided by S base old into V base old. If you remember this, it will be actually good, because this can be utilized in many places, right? So that's why remembering it actually is useful. Whole square. Okay, so this is the formula. Basically this is one of the important formulas. Now few more important points are there. So inductor, we know it absorbs lagging reactive power, it delivers leading reactive power. I have discussed this in synchronous machines chapter, right? Synchronous machine subject. Capacitor, it absorbs leading reactive power and delivers lagging reactive power. Okay, this will be extremely useful while voltage control, while reactive power control, right? So for inductor, it will typically consume reactive power. For example, induction machine, induction machine, right? Induction machine is a lagging load, so it will always absorb the reactive power. And I can say overexcited synchronous machine. Overexcited synchronous machines can deliver lagging reactive power. Basically it absorbs leading reactive power. Overexcited synchronous machines. Okay, so this will be highly utilized in power factor correction and voltage support. We will discuss this in, I think, PSA 1. Okay, so with this I will end our lecture, but of course last question we will do and then I will end. So this is the last question that we will do. So a load of 60 megawatt at 0.9 power factor lagging is tapped from this 66 kV substation and the voltage is to be maintained at 60 kilovolt. So here the voltage is maintained at 60 kilovolt. Okay, voltage is maintained at 60 kilovolt. So now what they are asking, they are telling me the terminal voltage of the synchronous machine is. What is the terminal voltage of the synchronous machine? So what is the terminal voltage here? That is what they are asking. So we will solve this in per unit. We cannot solve this in simple three phase, right? So I will convert this circuit into per unit, right? So here I will have a generator, and generator reactance have they given? Yes, generator reactance they have given. And always remember, whatever this per unit reactance they have given always is with respect to its own base. Always is with respect to its own base. Okay, so choosing base is also very important. So this is the last question where actually I have not mentioned what base to choose. So always choose that base which is most common. Here I see 100 MVA, 100 MVA. So another important point is that choose, so that just don't choose base randomly, choose base that is actually useful. So choose base values that are most common. Okay, so here I see that 100 MVA is most common, and 11 kV if I choose on the generator side, then also the voltage will also be same, right? So base I will choose, V base will be 11 kV on the generator side, and S base will be equals to 100 MVA on the S base is common, right? It is common everywhere. So if I draw the per phase equivalent, first of all I will have the generator. Okay, then I will have the reactance. So reactance is given for the transformer. They have not given me any reactance for the generator. Okay, no reactance has been given to me for the generator, right? Okay, yeah, generator reactance is not given to me, so I will simply ignore it. Okay, I will simply ignore. Generator reactance has not been given to me. Okay. Okay, xg is not given, so I will assume xg to be 0. Now I have this transformer whose reactance is given to me, right? This reactance is given to me, that is 0.1, correct? But it is with respect to its own base, that is 100 MVA and 11 kilovolt, which is my base, right? So I will not have to change anything. It will be 0.1 pu only. Okay, now I have the transmission line. Transmission line is J150. So here what is the voltage level? 220 kilovolt. What is the S base? 100. So what will be my, so this formula also you must remember, right? ZPU. This formula you should also remember. ZPU will be equals to Z actual into S base upon V base whole square. This also you have to remember. Okay, so your X transmission line PU will be equals to X transmission line PU will be equals to 150 into this S base, that is 100 upon 11 kilovolt whole square. So this will come out to be 150 into 100 divided by 11 whole square. So okay, it is coming out to be quite large. Okay, it is coming out to be quite large. Am I doing this correctly? 150 S base is 100 MVA. Okay, 150 ohms. This is correct only, right? Yes, 100 MVA. I have made the same mistake. I just told you that here the voltage level is 220 and I am writing it 11. What am I doing, man? It's been a long night. It has been a long night. 220 whole square. Okay, 220 whole square. So now it will be correct. So 220 whole square into 100 into 150. So it comes out to be 0.31, right? So this will be J 0.31. Okay, so what will be this value? So this value again will be same, because here the voltage is 220 kilovolt and the base is same 100 MVA, right? It will not change. So this per unit impedance also will be same 0.08. Whenever they are mentioning, right, only 8%. It basically they are mentioning the reactance. They are only mentioning the reactance. If only 8% is written, they are mentioning the reactance. That's it. Now here this is very interesting actually. So they have told me that the voltage has to be maintained to 60 kV. So here the voltage has to be 60 kilovolt. The voltage has to be 60 kilovolt. It cannot be 66 kV. So in this bus, the voltage has to be maintained at 60 kV, right? And here the load is connected, right? So what will be the voltage in per unit? Voltage in per unit will be actual voltage 60 kV divided by the base. What is the base here? Base on this side is 66. So it will be 66 kV. So it is 10 by 11. So 60 divided by 66 is 10 by 11. So it is 0.9. 0.9. So this is 0.9 angle. Okay, what is the angle? Angle this will be 0 only because it is the terminal voltage. I will assume it to be angle 0. And what are they asking? And power factor is 0.9. So here it is taking load at 60 megawatt, right? So what is PPU? PPU will be what? PPU will be actual upon S base. S base is 100. So it is 0.6 PU. And power factor is 0.9. 0.9 power factor cos phi is 0.9. Lag. Have they mentioned it as lag? Yeah, lag. So now what they're telling me? The terminal voltage. So what will be the terminal voltage here? They're asking me what is the terminal voltage here because the terminal voltage of the synchronous generator. Terminal voltage of the synchronous generator will be here, right? Terminal. So synchronous generator actually generates a voltage EG, but they're not asking me EG. They're asking me the terminal voltage here, voltage at this node. Will I be able to find out the voltage at this node? Yes. What is the current here? This is ground. What is the current here? I know what is my PPU. I can easily find out what will be my IPU. IPU will be simply PPU upon cos phi voltage into cos phi, right? VPU into cos phi. It is simply VI cos phi, right? So IPU will be equals to PPU. PPU is 0.6 divided by VPU, that is 0.9 into cos phi, that is 0.9, right? VPU is here, right? The voltage across the load, that is 0.9. So this comes out to be equals to into 0.9 into 0.6. So this comes out to be 0.733 PU. And what is the angle? Angle will be very simple, right? Cos inverse of this. So cos inverse of 0.9, 25.84 2 degrees. Okay, that is what my IPU will be equals to. IPU will be equals to this value, correct? So now this is my IPU. I can simply find out my terminal voltage here. What will be the terminal voltage here? V1. So V1 will be equals to this voltage V2 angle 0 plus whatever this impedance is. This is 0.1 plus 0.08, that is 0.18. 0.18 plus 0.31. So this comes out to be this whole reactance comes out to be J 0.49. Okay, so plus I into J 0.49. So IPU into J 0.49. So V2 is 0.9 angle 0 degree plus IPU 0.733, 8.42, okay, into the reactance basically. So this is 0.4990, okay. So into 0.733, so this comes out to be plus 0.36. Angle will be this, okay, if I add this angle, right, oh sorry, this will be negative, right, it is lagging, sorry, this will be negative, lagging current, right, negative, it should be negative, it is lagging, so current should lag the voltage, it should be negative. So 90 minus 25.842, this comes out to be 64.16 degrees, and this will be 0.9 angle 0 degree, okay. So this value will be equals to, so yeah, now if I calculate 64.16 cos into 0.36, so 0.9 plus this, so 1.57 plus g into 0.36 into 64.16, 0.34, so whole square plus 1.057 whole square under root, so it is 1.1 pu. Angle will be what? Angle will be 0.324 divided by 1.057 tan inverse, it is 17.0 degrees. So of course angle, like it will go from higher angle to lower angle, okay. So this is my in per unit, this is my voltage in per unit, but they have asked the terminal voltage, right, in kilovolt. Actually they have not mentioned it is in kilovolt, so I have to convert this into actual value. So what will be V actual, V1 actual, right, it will be simply V1 pu into the V base, right. So V1 pu is 1.1, angle will not change basically, 1.117 degree into V base. V base we have assumed on the generator side the base voltage was supposed to be 11 kV, right, so it will be 11 kV. So this will be 1.1 into 11 comes out to be 12.1. So answer will be 12.1 kV angle 60 degree, angle 17 degrees. This will be an answer. Elegant question, and at the end I taught you what kind of base to choose, because I have not told you like what kind of base to choose. So with this question that is also clear, that what kind of base shall we choose. So I hope it is clear, I hope everything is clear. So one more key point I want to explain, like this is the last key point that we will do, okay, after that we will end our class basically. So here I am discussing about the line and phase voltage in per unit and actual. So let's say if it is represented in actual, it is in volts, all of these values are in volts, and here it is represented in per unit, okay. So this is in per unit, this is in per unit, this is in per unit, okay. So now the important factor is, if I calculate the line voltage here, what will be the line voltage? It will be, let's say this is my phase A, B and C. So VAB, the line voltage will be 100 angle 0. Let's assume that this is grounded, so this is also grounded. 100 angle 0 minus 100 angle, even if it's not grounded then also it's totally fine, like this will be still be same value because it is VAN minus VBN, so the common point anyways gets cancelled. So 100 angle 0 minus 100 angle minus 120, okay. So this value will be equals to 100 root 3 angle plus 30. How is it plus 30? You can understand, you can remember with phasors. So this is 100 angle 0, 100 angle minus 120 will be here, right? But it is negative, so it is actually here. So these two vectors I have to add. What is the difference? So this is 120, this will be 60. So this we have already discussed, right, in short notes, that if the magnitudes are same and if there is a difference of 60, then the resultant will be the perpendicular bisector, basically the bisector, and the value will be root 3v, angle will be plus 30. It will lead the reference from plus 30, right? The angle will be plus 30 because it is bisector. So that's why plus 30. So it is 100 root 3 plus 30. Now what will happen here? Now here, if I am calculating the line to line voltage VAB in per unit, VAB in per unit, you will get 1 angle 0 minus 1 angle minus 120 degree. So this will come out to be equals to root 3 angle plus 30, right? Root 3 angle plus 30. Okay, this is what this angle comes out to be. Now the important fact to note here is, what is the base? You will say the base is a line voltage base. So what is the line voltage base? It is 100 root 3, right, magnitude. So if I now compute the actual value of VAB from here, actual value, VAB actual, right, it will be the per unit value root 3 plus 30 into the base of the line voltage, that is coming out to be 100 root 3, right? The base of the line voltage is 100 root 3. So you will say from here, you will say that the actual value, right, VAB actual comes out to be 300 angle plus 30. Is it correct? It is incorrect, right? It is incorrect. So what went wrong? So you cannot do this. You add and subtract per unit values and then you use different base values. This is not applicable. So there is a bit of problem here. So I will always suggest you do the per phase analysis. Always do. So there are 3 key points. Per phase analysis should always be done in per unit method. That is the easiest, right? Now if you want to do 3 phase analysis, right, start delta analysis, then you convert everything back to actual. That is the best thing, right? You directly don't do this. Directly don't do this subtraction. What do? You convert this to actual. The actual value is here, it will be 100 root 3 angle 0. Sorry, not 100 root 3, 100 angle 0, because here the value is 100, right? That's why the base will be 100 only. Minus 100 angle minus 120. Then you solve it, you will get the correct answer. Okay. So then the normal analysis, right, for 3 phase analysis, 3 phase analysis should be done only on the actual values. Otherwise there will be a bit of confusion, right? You saw, right, this is, we are not getting the correct answer, actual values. So you basically you convert per unit value to actual value. Okay, that is what you do. So yeah, that's it basically for this lecture and for per unit method. In the next lecture we will start with symmetrical fault analysis. I hope you have enjoyed this lecture. If you did, make sure to hit the like button if you are enjoying all these new concepts, and make sure to comment down below how you are feeling about the lecture, and I will see you in the next lecture. Until then, happy learning.